Okay, welcome to this video looking at everything you need for AS Pure Mathematics. Now, of course, anybody that has studied AS Pure Mathematics will know that covering all of the content in a year, let alone in 7 hours, is very challenging. Now, what I have done is I have gone through all of the topics that you can see on the screen, and I have covered important aspects and teaching elements to do with all of them. So this is a long video, but as you will see in a second, it is split up so that you can use it effectively. Now, I have gone through every single topic on the AS Pure curriculum. So please do make use of this video. If it is useful and helpful, please do like the video, please leave me a comment, and don't forget to subscribe to the channel. As with all of these videos, there is all of the chapters down below, and I'm going to show you that in just a second. So please do make use of that, and don't forget to check in the description for any links to further videos for full lessons on any of these topics. So let's have a look at how to use this video. So anyone that has followed me from GCSE level should hopefully remember this video on the screen where I covered everything for a grade 6 to 9 in your Maths GCSE exam. Now, this video is going to follow a very similar format. So if you click into the description, you will see that every topic is time-stamped for you so that you know the name of everything that's on the screen, and therefore you can go and you can do some further revision, whether that be from a revision guide or whether from a textbook, or whether you use some of my lessons which will be next to each topic in the description. Now, if you want another way to scroll through the video as well, if you click onto the video, you can see in the bottom left it says the name of the topic. If you click on that, it will bring through all of the chapters down the side, and you can just scroll through and you can start and pick up from wherever you left off, or you can skip through particular topics if you know that you are comfortable with them. So hopefully the way that this video works should be really useful for you. Again, if you have already followed me, you will already know how my videos work, but just in case you're new to the channel, hopefully this just shows you how I set up my videos and how you can go about using it. So now that you've seen that, let's get started. We have a lot to get through. Okay, so we've got larger coefficients of x here. We've got the 2x and the 3x, and I'm going to start by expanding these two. So let's write that out. We've got 2x plus 3 and 3x minus 2. So we know we're going to get the 6x squared here when we do the first two. So 2x times 3x gives us the 6x squared. And let's have a look at those middle two. So we get minus 4x plus 9x and those middle two. So minus 4 plus 9 gives us 5x, so we're going to have plus 5x, minus 4 plus 9, and then we're going to get minus 6 at the end. There we go. So just save you a little bit of time if you can do this. And let's stick that in a bracket, and we're going to multiply it by the x minus 4. There we go. We can do it all from here now. So just following the same process as before, 6x squared times x gives us 6x cubed. 6x squared times negative 4 is negative 24x squared. And then moving on to the underneath, 5x times x gives us plus 5x squared, and 5x times negative 4 gives us negative 20x. And then on to the negative 6 to finish it off. Negative 6 times x is negative 6x, and negative 6 times negative 4 is positive 24, and then we just need to tidy all this up again. So we've got the x squareds there and the x pieces here, and let's just rewrite all that nice and tidy. So 6x cubed, negative 24 add 5 is negative 19, so negative 19x squared. Negative 20 take away 6 is negative 26, so negative 26x, and then plus 24 at the end. And there's how to do that one. So keep it all really nice and tidy, expand whichever two you want to start with, tidy it up with your third bracket at the end once it's been simplified, and then just go step by step really nice and carefully before you tidy it all up at the end. And remember what your answer should look like. You will get these cubes, the squareds, the x, the numbers. Sometimes they might cancel each other out, but in none of these they have. So when we're simplifying an algebraic fraction, we're looking for a common factor on the top and the bottom. And when it comes to algebra, to find a factor in algebra, we can factorise to find a factor. So if we have a look at the top, and we just need to factorise both of these. Now, the expression on the top there has an x in both. So we can factorise this by x. No numbers in both, but we can factorise it by x. So if we take x out of the bracket, we would have x, and then inside the bracket we'll have x plus 5. Okay, x plus 5. If we do the same on the bottom, we've got a quadratic on the bottom, so you need to know how to factorise quadratics here. But we've got 1 and 10, or 2 and 5 as our options to go in our double bracket. And in order to make 7 there in the middle, we want plus 2 and plus 5. And here we go, x plus 2 and x plus 5. There is a little bit of a hint there in terms of the factors we'd be using, because obviously we had x plus 5 on the top, but it's not always going to be the case that we'll get that, but obviously so we still need to be able to factorise, but there is a little bit of a hint there that there was going to be an x plus 5 in one of the brackets. Now there's an x plus 5 on the top and the bottom, so essentially what we can do is we can divide the top and the bottom by x plus 5, which would cancel out these brackets here. And if we cancel them out, we just need to write what's left. We have x on the top, and on the bottom we have the x plus 2, which you can either put in the brackets or leave without the brackets, it doesn't matter there. But our final answer is x over x plus 2. Right, let's have a look at another one. Okay, so we've got another algebraic fraction here that has already been factorised on the bottom. So actually, let's have a think about how we'd approach this. Now we want to cancel off a common bracket or a common factor, and the top and the bottom both divide by x plus 2. So actually, if we imagine what this would look like if we were to sort of expand that bracket or just write it as a double bracket, we'd have x plus 2 on the top, and on the bottom it's x plus 2 and x plus 2 as a double bracket. There we go. Right, so if we cancel off one of the x plus 2's top and bottom, we've just got to be careful this time because we can cancel that one off and it will disappear. But not to forget, we are dividing by x plus 2, so when we cancel the one off the top, it doesn't just disappear, but if we divide it by x plus 2, it becomes 1. So writing our final answer, we would have 1 on the top and x plus 2 on the bottom, which again, I'll just get rid of the bracket there. So 1 over x plus 2. So just watch out with these sorts of questions here when the factor is all that there is on the top. Obviously that does become a 1 there, it doesn't just disappear. Okay, so introducing some negatives. Same process though. We'll stick 2x in one bracket and x in the other, as we've got a 2x squared. And again, writing down the factors of 10, so 1 and 10, or 2 and 5. Now again, one of them's going to double, so we could have 2 and 10, or we could have 1 and 20. Are we going to be able to make 9 out of either of those? No. 2 and 10 we could make 8, we could make 12, but we can't make 9. And then 1 and 20 we could make 19 or 21, but we can't make 9. So it's not going to be 1 and 10, which means it's going to have to be the 2 and the 5. Got to be a little bit careful here because we've got negative 9 in the middle, so we are trying to make negative 9, but similar process to when we were factorising before. So let's double one of them, so we could have 4 and 5, or we could have 2 and 10. There we go, just doubling one of them. So again, we're trying to make negative 9, so it's going to have to be 4 and 5. We can't make 9 out of 2 and 10, but we can out of 4 and 5. We've just got to figure out, okay, well, which one of these needs to be negative? And actually looking at it, look, we've got a positive 10 at the end, so they're both going to have to be negative. So it's going to have to be negative 4 and negative 5. So I just want to make sure that that number above the negative 4, the 2, goes in the bracket that's going to be doubled. So on the right hand side there we want negative 2, that's going to allow us to get negative 4, and on the left bracket there we'll put the negative 5. And again you can just expand that to just double check, so 2x times x is 2x squared, 2x times negative 2 is negative 4x, negative 5 times x is negative 5x, and then negative 5 times negative 2 gives us the positive 10 at the end there. And tidying that up, look, these two here do make my negative 9. We get 2x squared minus 9x plus 10, and it matches what we were looking for. Now for this one here, it says simplify this fully, and inside the bracket we've got 32x to the power of 5, and then outside it's all to the power of negative 2/5. Now obviously when it comes to these negative fractional indices, the negative there is going to do the reciprocal, the 5 on the bottom does a 5th root, and the 2 on the top is a normal power of 2. And both of these pieces we have to do to that power. Now when it comes to the 32, we can think about the 32 on its own for the moment, and we can do 32 to the power of negative 2 over 5. Now we can sort that out and deal with that first. Now the negative obviously flips it over, but before doing that and doing the reciprocal, I'm going to do the 5th root of 32. Now the 5th root of 32 is 2. Okay, so 2 times 2 is 4, times 2 again is 8, times 2 again is 16, and then times 2 again for that 5th time gets us to 32. So to start with there, we'll do the 5th root. I'm just going to write this down here, fifth root. So that's 2. Then we're going to have to square it because we've got the 2 on the top, so we need to do 2 squared. So that becomes 4. And then if I do the reciprocal there, it becomes 1 over 4, and that's what that negative power does. So that 32 there is going to become 1 over 4. So if I write that down to start with, I can write down 1 over 4, and then we'll deal with that power. Now when it comes to the x to the power of 5, we can obviously multiply the powers when we've got brackets like this, so we're going to multiply these powers together. So we've got 5 lots of negative 2/5, and 5 lots of negative 2/5 will be negative 10/5, okay, just multiplying that numerator by 5, and negative 10 divided by 5 is negative 2. There we go, so my power is going to turn into negative 2. So I can write that out here. We've got then x to the power of negative 2. Now technically that is the answer, that would be fine, but there are other ways of writing this as well. And obviously we can write this in a slightly different way because x to the power of minus 2 can also be written as, I'm thinking about this over here, x to the power of minus 2 can also be written as 1 over x to the power of 2. Remembering that that negative power there does the reciprocal, so it's 1 over x squared. So, I mean, we could actually write this in a different way. If we imagine x to the power of minus 2 as 1 over x squared, we've got a quarter. Remember, these are getting multiplied together. So it's a quarter times 1 over x squared. And if we multiply those together, we get 1 over 4x squared. Now for this particular question here, it does just say simplify fully, so we can write it in either of these ways, but it might be for whatever reason we might want to just write it as a single fraction. So it's always good to be able to know how to write these in different ways. So there we go, we can also write it as 1 over 4x squared, or we could just leave it as a quarter x to the minus 2. But there we go, that's how we're going to approach some of these questions. Let's have a look at a slightly different one. Okay, so this question doesn't look very nice, but you're going to see we're going to treat this in a very similar way to what we did before. Now again, ignoring that x squared for the moment, let's just deal with what's in the brackets. Now everything in the brackets there is to the power of 2. So we've got the 4 that we need to do to the power of 2, and that's easy enough to do. 4 squared is 16, so we've got 16 there in the bracket. And then we can multiply these powers that are in brackets as well, we'll times them. And if you multiply negative a half by 2, you get negative 1. So that's going to be 16x to the power of negative 1. And again, obviously you can write that working out down to the side. You've got minus a half, and you're going to multiply that by 2, or 2 over 1, which comes out as minus 2 over 2, which is minus 1. There we go. So there we go, that's how we can get our power, obviously just thinking about negative a half times 2 is negative 1. And now we can obviously put that in a bracket and we can think about that x squared on the outside. There we go. So obviously when we are multiplying, obviously thinking about the fact that the coefficient of this x squared on the front is 1, and then we just multiply this bracket out. So 1 times 16 gives us 16. And then we've got the x squared times the x to the power of minus 1. And remember, obviously, when you're multiplying with powers, you add these powers together. So we're just going to add those two together. So x to the power of 2, add the x to the power of minus 1, obviously just the powers there, becomes x to the power of 1. There we go, so 16x to the power of 1. And obviously we don't need to write the power of 1, so we can just write that as 16x. And there we go, that would be our final answer for that one. There we go, so something that looks quite nasty actually simplifies down to something that's nice and simple for us. Okay, so this question here doesn't look very nice at all. But again, we're just going to treat it exactly like we have done in the previous questions. We're going to deal with the top, and then we'll have a look at the fact that it's a fraction. So that top bit there can simplify, so straight away let's have a look at this. So on the top we've got 2 to the power of 3, which is 8. And we're going to multiply those powers. Okay, so 3 lots of a half, and then again you can just write that as 3 over 1 times a half. And you get 3 over 2, or 3 halves, there we go. So that's 8x to the power of 3 over 2. On the bottom, nothing simplifies there, so we'll just leave that as 4x squared. There we go. And now all we have to do is simplify this down. So looking at the numbers, we've got 8 divided by 4. 8 divided by 4 is 2. And then we are dividing with these powers of x, so when we divide and we take away the powers. So we've got 2x to the power of something, we just need to figure out what that is. So obviously what we've got there is we've got 3 over 2. And we need to take away 2. So we're going to take away 2. Obviously 2 is 2 over 1. If we want to write that in terms of halves, we'll have to just change that denominator there. Just obviously that'll become 3 over 2. Take away, and if we times both of these by 2, there you go, that becomes 4 halves. And when you take those away, you get minus a half. There we are. So just taking away those powers there, and you might be okay just doing that without obviously writing all the fraction working out, but obviously just to show you there that you can just obviously apply a bit of written methods as well. But there we go, we get 2x, and our power is going to be minus a half. And again, you might be able to just do 3 over 2, take away 2 in your head, but there we go. So 2x to the power of minus a half, and again, that is a final answer there, and we can leave it like that, but there's another way that we can write this. And obviously this is going to be important for thinking about it in reverse as well. So x to the power of minus a half, well, x to the power of a half is the square root of x. So that would be the square root of x, but it's a negative a half, so that would be 1 over the reciprocal of that, so 1 over root x. So actually what we've got here is we've got and 2 multiplied by 1 over root x. There we go, and don't forget 2 as a fraction will be 2 over 1. So multiplying the top there, we get 2 on the top, and multiplying the bottom, we get the square root of x. So again, 2 different ways of writing your answer. You can either write that as 2x to the power of minus a half, or 2 over the square root of x. Either one of those is absolutely fine. Although I do think it's important to be thinking about how you can write your answers in different ways, purely because, as I said, sometimes they might be going the other way round, or you might have a square root on the bottom and have to rewrite it as a power. So it is important to be able to write them this way. Okay, here we go. So expand and simplify this. So slightly different look. We've got a number in front of this 2 root 3 here. And also, this is a slightly odd one, because we've got a surd in here which isn't fully simplified. Okay, we've got a root 8 there. Now you don't have to simplify it at this point, we can see if we can simplify it later on. You wouldn't be wrong to simplify it now, but I'm just going to leave it and see what happens. Okay, so just take note, there are some slight differences in this question, but let's have a look. 5 times 3 is 15, 5 times negative root 8 is negative 5 root 8, 2 root 2 times 3, remember numbers times numbers, surds times surds, so it's just 2 times 3, which is 6, so plus 6, root 2, and there's no root with the 3, so just root 2. And then finishing the last part off, it's positive times a negative, so I've got negative. I'm just going to work this out to the side. 2 times the 1 there is 2, and root 2 times root 8, so we get 2 root 16. Negative 2 root 16. And root 16 is 4, so that's negative 2 times 4, which is negative 8. Okay, well if we do that to the side here, look, 2 times 4, which is going to be 8. So let's just get rid of that working out there and put negative 8. Okay, we can start to tidy this up now. We've got 15 take away 8, which we can do, but these surds aren't gonna simplify now. So what I need to have a go at doing is first simplifying this, because we've got a 5 root 8 there and that can simplify. So again, I'm just going to do that to the side. 5 lots of root 8. So ignoring the 5, root 8 is root 4 times root 2, which is 2 root 2. And again, just remembering we did actually have 5 lots of that. So 5 lots of 2 root 2 is 10 root 2. So rather than writing this 5 root 8 here, I'm going to write 10 root 2. So I'm going to rewrite this question. I've got 15 minus 10 root 2 plus 6 root 2 minus 8. So 15 take away 8 is 7. And then minus 10 lots of root 2, add 6 lots of root 2, leaves me with negative 4 lots of root 2. Right, there we go. So slightly harder there. We've got little bits going on where we've got to just be careful to simplify. But there are little hints there that with spotting the root 8 to start with, that there's going to be some simplifying going on. Slightly harder ones here, purely because we've got this little 3 in front of the root 2 now on the bottom. But we're going to take the same process. So I'm going to times the top and bottom by what's on the bottom there, but flipping the sign. So I'm going to times the top and bottom by 5 plus 3 root 2. And then again 5 plus 3 root 2. So 2 plus root 2 on the top, multiplied by 5 plus 3 root 2. And then on the bottom, we have 5 minus 3 root 2, multiplied by 5, I don't want to put the multiply in there, because I'm speaking it as I say it, multiplied by 5 plus 3 root 2. And then again, just take this nice and slow. So 2 times 5 is 10. 2 times 3 root 2 is 6 root 2. Root 2 times 5 is 5 root 2. And root 2 times 3 root 2 is 3 root 4, or 3 times 2. Again, you can write that slowly. 3 root 4, which is 3 lots of 2, which is 6. And there's the top. And then the bottom, I'm going to apply that little shortcut. So 5 times 5 is 25. And negative 3 root 2 times positive 3 root 2 is negative. 3 times 3 is 9. Root 2 times root 2 is root 4. So it's minus 9 times 2, which is minus 18. And then we just need to tidy that all up. So the 10 plus the 6 on the top is 16. The 6 root 2 add the 5 root 2 is 11 root 2. And then 25 minus 18 is 7. And then neither of those simplify, nothing on the top divides by 7 there. So that would be our final answer for this one. So not got any negatives on the bottom this time. Question here, we've got a 2x squared. So again, I'll link in the description the video for obviously factorising harder quadratics. I will explain them a little bit, but I won't go into as much depth as I did in that video. So do check that one out if you're not sure on how to factorise these. Now in terms of a 2x squared, that means in one of our brackets here, we're going to have a 2x when we're factorising it. So if I set the brackets up, we've got a 2x and an x, it's all equal to 0, and we just need to figure out where the numbers go. Now if we've got a 1 at the end, our only factors can be 1 and 1, but one of them is going to be doubled. Okay, obviously when we expand our double bracket here, we've got a 2x and it's going to double that 1 in the other bracket. So as they're both 1s, we know they're both going to be 1s here. We just need to figure out the symbols. Now we want minus 1x or minus 1 in the middle. So in order to make minus 1, we're going to want positive 1 take away 2. So as this one over here is going to be doubled, we'll make that one become our minus 2. And this will be our positive 1 here. And obviously you can go about expanding that just to check that it matches, but there we go, that is going to match. We're going to get plus 1 on this expansion here, plus 1x, and we're going to get minus 2x when we expand that one there, and that will give us minus 1 in total. So in terms of obviously getting our solutions here, it's very similar to what we just looked at. If we just set them both equal to 0, this one here is just going to become x equals 1. Obviously we haven't got a coefficient there, and this one here, we're going to flip the sign, so x is going to equal minus 1, but then we're going to divide it by the 2. So minus 1 over 2, or minus a half. And there's our two solutions, x is minus a half, and x equals 1. And again, you could obviously draw your sketch of your quadratic there. Just thinking about what it looks like, it's going to go through 1 and minus a half. And you could draw that in, there we go, 1 and minus a half. And that's where our two solutions are. Now in this one, the process isn't any different, but we've got something that's going to change here. I just want to show you this, and it's negative 11 here in front of x. So if I write down my values of a, b and c, we have a equals 3, b equals negative 11, and c equals negative 13. And if I go ahead, plug in all these values in, I've got to have a look at what changes here. So the start of our quadratic formula is minus b, but b is already negative. So if b is already negative, that's going to turn into positive 11. So on the top there, we have positive 11. Now, I don't have to put the plus with it there, but I just want to emphasize for you, it's going to be plus 11. Okay, so minus b, if b is already negative, that's going to become a positive number there. So we have 11 plus or minus the square root of, and again I've got to be careful here because I've got to do b squared. Now when I'm squaring a negative number and subbing a negative number in, I should always really put it in brackets. So negative 11 squared. Reason behind that, and hopefully you've got your calculator in your hand, if you type in negative 11 squared without the brackets, you're going to get negative 121. And a negative times a negative makes a positive, so your calculator is not going to do it in the correct order for you. It's going to do the power before it does the minus there. Okay, so you just got to be very careful. It does the order of operations. So if you want to make sure it squares a negative number, stick it in a bracket. That's very, very important when b is negative. So we've got b squared minus 4 AC, so 4 times 3 times negative 13. Okay, let's just extend that, there we go. And that's all over 2a, so all over 2 times 3. Again, on this question, look, that and that was new this time. The minus b turning positive and the negative b in the bracket there when you're squaring it, so being very, very careful with that. But there are new bits that you need to be careful on this type of question. So let's type this in. Again, we'll do the positive and we'll do the negative. There we go, and we'll stick these values in. So fraction button, positive 11, so just 11, plus the square root of, in brackets, negative 11 squared, take away 4 times 3 times negative 13, all over 6, or 2 times 3. press equals and turn it into a decimal, you've got 4.607 219,496. And again, finishing that off by rounding it to three significant figures here again, we've got 4.61. There we go, and there's our first solution. Moving on to our next one, back into the calculator. Takes a little bit of a while to click back. There we go, swap it for a minus, and we get minus 1.5866 06875. There we go. And then finishing this off, rounding it again, that becomes negative 1.59 because it's a 6 there after the 8. And there's our two solutions. So when it comes to this question here, obviously this is what we're going to complete the square for, and we're going to find the turning point to start with and have a look at how we apply it for that as well. So when we've got this one here, now this is our quadratic that we have at the moment, 2x squared plus 16x plus 26. Now we can only complete the square, well I say we can only, we have to get the coefficient of x squared to be 1 first before going about completing the square. So what we're going to do is we're going to factorise it by a factor of 2, okay, so that as they all divide by 2 there, or just because x squared has a 2 in front of it, we're going to take a factor of 2 out. So if I factorise this by 2, I get 2 lots of, and then dividing everything by 2, we get the 1x squared, we get 8x, and we get 13 at the end. There we go. Now all I'm going to do is I'm going to basically ignore that 2 is at the front. So all I'm going to do is factorise or complete the square for what's in the middle here. Okay, obviously we've factorised it there, we've taken out a factor of 2, and now we're going to complete the square for what's inside. So normal process for completing the square, I am going to halve the coefficient of x. So in my bracket I'm going to have x plus 4, obviously halving the 8 there, and that is going to be squared. Obviously remembering why we do that, because when we expand that we get the x squared, we get the 8x, but at the end if we expand it we'd get plus 16. Now we don't want plus 16, we want the plus 13 there, so we're going to have to take away 3 to make this balance out. So I will have to put minus 3 at the end. And now if I did expand and simplify all of that, I would get the x squared plus 8x, I'd get plus 16, take away the 3, and that'd leave me with the 13 that I'm looking for. Now obviously we can't forget that 2 exists, that 2 is still at the front there, and we have to bring that 2 back in. Now what I'm going to do is I'm going to put all of this in a bracket, and rather than using a rounded bracket, I'm going to put it in a square bracket just to define, obviously it's a different set of brackets there, and I'm just going to put that 2 back at the front. Right, there we go, well we're almost done. All I've got to do now is reintroduce that 2, and that just means expanding out this square bracket by that 2. And that's easy enough to do. We've got 2 lots of the bracket there, so I'm just going to write this out. Let's see what we've got. We've got 2 lots of the x plus 4 squared. There we go. And then timesing that negative 3 by 2 will leave us with negative 6. And there we go, that's that completed in completed square form. All we have to do now is, obviously like before, we identify the turning point from what's in the bracket there. So just like before, the x coordinate is right here, but we flip the sign. So that is going to be negative 4 as our x coordinate, and our y coordinate is just at the end there, the minus 6. So there we go, our y coordinate is minus 6. There we go, and that's the coordinates of our turning point. So very, very similar to obviously normal completing the square, but obviously we just have this extra element there of factorising out that coefficient of x squared and then reintroducing it at the end and just multiplying that number at the end there, that what was normally our y-intercept, our y coordinate, and actually just multiplying that back out by the factor that we took out at the start. So this question, we've got 2x squared at the start, okay, and obviously when we're completing the square here, we do have to take that into account, and we are going to first complete the square. It then says hence solve the equation, so just like the last one, and giving your answer in the form a plus b root 3, where a and b are integers. So let's start with completing the square. So we'll take out that factor of 2, so we have 2 lots of x squared minus 4x minus 8, okay, and then let's complete the square for what's inside. I'm going to swap colours like I've done before, there we go. So half that coefficient of x, and we have x minus 2 in brackets squared, and that's going to make plus 4 at the end, and we want minus 8, so we're going to have to subtract 12 there to make that balance out. Reintroducing that 2, let's see what we get. There we go, reintroduce the 2, and we have 2 lots of x minus 2 squared minus 24. Now for the second part of this question here, it says hence solve the equation. So we're going to do exactly the same thing. We're going to set it equal to 0. So if I set this equal to 0, and I'll do it separately up here, we have two lots of x minus 2 squared minus 24 equals 0. Now it's completely up to you in terms of the steps that you do here, but there's a couple of things that we can get rid of from the start. Either we can get rid of this 2 at the start, we could divide everything by 2, or we can add this 24 over to the other side. Now personally I just like to add the 24 over first, but it's completely up to you in terms of which order that you do it. I'll show you why it doesn't really matter. But if I add the 24 over, let's have a look. We get two lots of x minus 2 squared equals 24. Now at this point I'm going to divide by 2, so that's going to turn that 24 into a 12. Now you could have divided by 2 at the start, it wouldn't obviously affect the 0 over here, so 0 would still be 0, but you've just got to remember if you do divide by that number you also have to divide the 24 by 2 because that's going to become 12 on the other side, and you've got to make sure you divide everything by 2 on that left hand side of the equal sign. So personally I just like to add it over first. I feel like it just helps you not to forget to also divide that by 2 as well. So if we go about dividing by 2 now, we'll get x minus 2 squared equals 12, and then it's exactly the same as the last question. Now we can square root both sides and we get x minus 2 equals plus and minus the square root of 12, and then we can add that 2 over to finish it off. And if we add the 2 over, let's see, we're running out of space a little bit here, but we get x equals 2 plus and minus the square root of 12. Obviously we do just need to have a look, and let's just bring this up here, we do need to have a look at obviously writing it in the form it wants, and it wants it as b root 3. So we need to think obviously about that root there, and that is root 12, and how does that simplify? Well, let's have a look. Root 12, the square number that goes into that is 4, so we can write that as the square root of 4 times by the square root of 3, and the square root of 4 is 2, so that's 2 root 3. So finishing this off then, we can write it in the form it's asking for, and that is that x equals 2 plus and minus 2 root 3, and there is our final answer, writing it in that Surd form that it's asking for in this question. Now just a very quick discussion of this before you maybe try and have a go, but you will notice that the coefficient of x for 1 is an odd number, so when completing the square that's going to form a decimal, although you can use a calculator for this question, but there is going to be decimals involved. And a little hint for you, this one doesn't factorise, and when a quadratic doesn't factorise you need to use the quadratic formula. So this is a calculator question, the rest of those could have been non-calculator, but this one here is explicitly calculator. So a couple of little hints there, but I would encourage you to have a go. This is our last little question, so if you pause the video and have a go, otherwise let's have a go at going through this one. So if I go about completing the square to start with, it wants us to draw a sketch showing the coordinates of the turning point and any intersections with the axes. So let's take out that factor of minus 1. So when we do that, we get x squared plus 3x minus 5. Now if we complete the square for this, it's not too difficult, particularly as we have a calculator, but we get x plus 1.5, or you could leave it as a fraction 3 over 2 squared. Now when you expand that bracket, 1.5 squared is 2.25, and we need to get back to negative 5. So you can do that on the calculator if you need to, but we're going from 2.25 down to 0 and then an extra 5. So we're going to have to take away 7.25 to get down to minus 5. Now we need to multiply that minus 1 back in, just like we have done before. So put that minus 1 back on the outside, and we get minus 1 lots of the x plus 1.5 squared minus 7.25, and obviously when we times that minus 1 in, it becomes plus 7.25. So there we go, we've got the coordinates of the turning point, not too bad there hopefully. Minus 1.5, the opposite in the bracket, and then 7.25 for our y coordinate. And again, we can solve it from here, and if we go about doing that, let's see what we're going to get. Now we could solve it from there, but we should really just solve it from the original quadratic. Once we've identified the fact that it doesn't factorise, we may as well just use the original quadratic, because it's not really going to matter which one we use there. So if we bring the original quadratic down and we solve from there, we've got our values of a, b and c that we're going to have to put into the quadratic formula. So a is the number in front of x squared, which is minus 1. B is the number in front of x, which is minus 3. And c is the number at the end, or at the start in this case, which is the 5. And if we plug all that into the quadratic formula, so obviously you need to know the quadratic formula for this as well, so I'll put that in the description. Don't worry, everything that's gone on in this will be linked in the description for you to have a go at. I'll try and put them in order for you as well for how they've occurred in the video. But if we put those into the quadratic formula, let's have a look. So we have minus b at the start, so that's positive 3 now when we flip that, plus and minus the square root of b squared, so negative 3 in brackets squared, take away 4 times negative 1 times 5, and that's all over 2a, or minus 2. Two lots of minus 1. Now if we type that into the calculator, obviously using the fraction button there, and just being careful how you sub all these numbers in, using the negative button for your negative 1, putting your negative number in bracket there for the b squared. For the version with the plus sign, we get, and I'm going to round these to 2 decimal places for this one. It doesn't actually say 2 in this question, but for the purpose of our sketch, we're not going to want to write all these decimals. It comes out as minus 4.19 to 2 decimal places. And if I go back into my calculator, change that plus for a takeaway, our version with the takeaway comes out as, and again to 2 decimal places, 1.19. So there we go. Obviously in a question like this we would just leave it as a full decimal if it didn't say how to round it, but for the purpose of this little bit of practice we're not going to worry too much about that. So obviously we've got a negative and a positive solution again, so if we draw our quadratic, again we're just going to do a little sketch, and it's going to go, let's have a look, minus 4 over to 1. I'm trying to make it as accurate as I can, or not over egging the whereabouts it is on the graph too much. But there we go, we've got minus 4.19. Over here we've got positive 1.19. We've got a y-intercept, which again we can get from our original equation of 5. And we have our turning point, which is just here. Not the best drawing there by me, but minus 1.5, 7.25. Just about get that on there. Okay, obviously just emphasising the fact that that turning point is to the left of the y-axis, as we have a negative 1.5 as the x-coordinate. So there we go, really tiny little sketch there at the bottom, but just showing you how this could obviously get a little bit harder, obviously with completing a square with an odd number as the coefficient of x, but if you have a calculator that's nice and easy enough, and then obviously using the quadratic formula as well, so it was a pretty tough question to finish on. Now the discriminant is something that you have met before, usually obviously from GCSE maths you'll have met the quadratic formula, and it's something to do with something within the quadratic formula. So if we have a look and just have a quick think about the quadratic formula, which is minus b plus and minus the square root of b squared minus 4ac all over 2a. Now normally, particularly at GCSE level, when you've looked at the quadratic formula, it's very rare that anything other than a positive number comes up underneath that square root. Although you will have noticed before, maybe you've typed it in incorrectly sometimes, and you may have found that obviously sometimes it came up with a maths error on your calculator when you type in something under here. And you've got to be very careful with the numbers that you type into there. But obviously, depending on whether it's a certain type of number, depends on whether we get an answer on our calculator or we don't. And that's what we're going to have a look at, and actually understanding this bit. Now that bit on its own, underneath the square root, that b squared minus 4ac is what we call a discriminant, and it determines, when we have a quadratic, how many solutions we have and whether we even have a solution at all. And we're going to have a look at why and how that happens, and a few particular questions here and the differences between them. But essentially, if we forget about the rest of the quadratic formula for the moment, we are just concerned with this bit, this b squared minus 4ac, and that is what we call the discriminant. Okay, so we're just going to be having a look at this bit. So I'm just going to write that up here. We've got b squared minus 4ac, and that is called our discriminant. Now, so grab a piece of paper, grab a pen, make some notes. We're going to get started with these questions here and just have a look at understanding why and how we get our solutions from this little bit under the square root. Now, if you think about the concept of numbers, underneath a square root, okay, we can have 3 different types of numbers. We can have a whole number, and let's pick something that actually square roots, something like 25, and the square root of 25 would give us 2 solutions. We can get plus 5, and we can get minus 5. So we get 2 solutions when there is a whole number under there. Sometimes it'll be an actual whole number, sometimes it might be a decimal, okay, but we always get 2 solutions with a whole number. We can also have the number 0, and if we get the number 0, obviously the square root of 0 is 0, But thinking about the rest of the quadratic formula, that would mean we'd only get one solution, because obviously in front of the square root there you have the plus and minus, and if both the plus and the minus are both 0, then both of our solutions are going to be equal. Or we could have, and thinking about when this arises, you could get a negative number under there, so something like -3, let's just put something random in, and you will get no answer on your calculator. It will normally say calculator error, and that's because we'll get no solutions, or in terms of a quadratic when we're solving that, we would call that no roots or no real roots, okay? No roots, there we go, I'll put that in there. So thinking obviously about the concept of the quadratic formula, and obviously I will link the video for that in the description if you need to touch up on the quadratic formula, but in terms of the type of numbers that go underneath that square root will determine what answers we get when we look at these solutions, and that's what we're going to have a look at with some of these questions. So this first one that I've got on the screen, I'm just going to get rid of all of this, is looking at a particular quadratic, and I have put a picture of this quadratic up here, and we'll see obviously that we get these two roots or two solutions here on the x-axis. So the equation for this particular quadratic is up here, x squared plus 4x plus 2. And in terms of actually figuring out the discriminant of that, and we're going to work out the value of the discriminant, we just need to plug in the values of a, b and c. Now a is the number in front of x squared, hopefully you're already happy with that, and a in this particular case is 1. B is the number in front of x, so b is positive 4, and c is that number at the end, and c is 2. And if we stick all of these numbers into the discriminant, so b squared minus 4ac, let's see what we get. So we've got 4 squared, our value of b, take away, and then we have 4 times a, which is 1, times c, which is 2. And if we just work out this calculation here, 4 squared is 16, take away 4 times 1 times 2, which is 8, we get 16, take away 8, and we get the answer 8. So the value of our discriminant is 8. And if we think about that, if it was put into the quadratic formula, we would have plus and minus root 8, which would give us our two values underneath the square root there. Again, that would give us our two solutions and ultimately determine these two solutions. Okay, so in terms of stating whether this, obviously without the graph, has two roots, two equal real roots, which we'll discuss in a second, or no real roots, we know that obviously with the positive 8 there, with the plus and minus square root of 8, we would have two roots, and we call those two distinct roots. Okay, but I'm just going to put two roots here for this particular example, and we can obviously see that from the graph as well. But there's two elements there. We've got the value of the discriminant and the fact that it has two roots, which obviously is also shown on the graph. So this question, it says 4x minus 5 minus x squared also equals or is equal to q minus x plus p squared, where q and p are integers. So obviously that there is highlighting the fact that it can be written in completed square form like that, which looks ever so slightly different to the way that we've been writing it in the earlier questions, but we're going to have a look at how to actually write it like that. So it says find the values of p and the values of q. And then it starts to ask us some other little bits here. It says calculate the discriminant, and then it also says sketch the curve showing any points of intersection. So we'll have a look at those points step by step. To start with, we're going to have a look at obviously finding the values of p and q and writing it in this completed square form just here. So let's write it out. So we've got negative x squared, and obviously this is a bonus because we've already discussed how to complete the square for this. Okay, but let's have a look. Minus 5. So if we take out that factor of minus 1 to complete the square, we'll get positive x squared minus 4x plus 5. And completing the square for that, let's obviously halve that coefficient of x. So we get x minus 2 in brackets squared. And when we expand that, we get plus 4. We want plus 5, so we need to add in an extra plus 1 there. And then again, not forgetting to reintroduce that minus 1, because that affects that y coordinate at the end there. So minus 1. And we end up with minus 1 lots of x minus 2 squared. And then that turns that into minus 1 at the end. Now obviously it wants it written in this form up here. Okay, q take away those. So all that means is putting minus 1 at the start there. Okay, and just shifting this minus 1 from the end and putting it here at the start. And if I write it out like that, we have minus 1 take away the 1 lot of that bracket, so I can get rid of that 1. There you go. And there it is. Minus 1 take away x minus 2 in brackets squared. So now it's in the format that we want. We can write out what the value of p and what the value of q is. So q is at the start, so q is the minus 1 there at the start. And p is negative 2 inside the bracket. There we go. And I always dislike that when they write it like this. Look, they've written plus p just here, and actually p's come out as a negative there, p is -2. So do just watch out for that. Just because they put plus p there doesn't necessarily mean it's going to come out as a plus or a positive number. So the next bit, right, it says calculate the discriminant of this. Okay, now when we're looking at the discriminant, and again I've linked the video for that in the description, we're looking at the value underneath the square root in the quadratic formula, that b squared minus 4ac, which is called the discriminant. And it determines for us how many roots this is going to have. So rather than getting us to actually factorise this, if it does factorise, and finding out whether there are two distinct real roots, two equal real roots, or no real roots, we're actually working out the discriminants, okay? So if we'll put these values in, then let's see what we've got. So obviously we need to get the values of a, b and c from here. Now I'm going to take it instead from up here where I've rearranged it. So the value of a is that 1 in front of x squared there. So a equals the -1 in front of the x squared. We've got b, which is in front of the x, so the +4. So b equals 4. And then we've got to forget c as well, which is the number at the end, which is -5. So there we go, c equals -5. And if we sub all these values into b squared minus 4ac, let's see what we get. We get 4 squared, take away 4 times -1 times -5. There we go. And if we work that out, let's have a look, just multiplying all these bits together to start with. 4 times -1 is -4, times -5 is +20. So we have 16 take away +20, or 16 take 20, which is -4. So my discriminant has a value of -4. Now obviously what we know about the discriminant, obviously hopefully you've already checked that video out and you know about the discriminant. If we get a negative number, that means we have no real roots. So in terms of this quadratic that we're going to draw, it's not going to cross through the x-axis, and that's what that tells us. And obviously if we were asked to draw this curve and we weren't asked to calculate the discriminant, we might be sitting there trying to factorise it, we might be putting it into a calculator, trying to get it in the quadratic formula, but actually very quickly we can tell using the discriminant whether it does actually have any roots. So it's a nice quick way for us to figure that out. And obviously this question asks us to do it anyway, but just thinking about another type of question, if it didn't ask us to calculate the discriminant, you know, it would be a nice quick way just for us to see whether it does factorise or not, and that's quite nice about the discriminant as well. So if we go about actually drawing this, if we want to sketch this curve, showing clearly any points of intersection with the axes, let's have a think about what it would look like. We know that it's going to be an upside down or an N-shaped quadratic curve here. So if I just draw a little basic axes, one thing we do need to get is obviously that y-intercept, which we've got up here. The y-intercept is -5. So that's going to be down here somewhere. So I'll probably want to draw this a little bit better actually. Let's get rid of that. Let's draw it so we can get actually down the bottom there. So we know it's going to be -5. We know it doesn't even reach the x-axis. There we go. The only thing we need to figure out is whereabouts we're going to put it. Now we can think about where the maximum point is because we've completed the square up here. So we've completed the square and we have got from that just here we've got +2 and -1 as our turning point. And if we go back actually finding that, let's imagine 2's there, -1 is there, so it's around here. There we go. So if I try and draw this in, then we've got it crosses through at -5. Got a maximum point there, and it never touches the x-axis. And obviously just labelling this on, we've got -5 there, and that's all we need to label. Doesn't ask us to label the maximum point there, we could put it on if we wanted. But there we go, there is a sketch of what this curve actually looks like there. We got the -5, the y-intercept up from our equation up here. Okay, well, let's write that in, y equals -5. There we go. And we got the fact of where the turning point was going to be positioned, just here from completing the square again, and then using the discriminants we figured out there was going to be no roots, so we know it wasn't going to get up to the x-axis there. So there we go, that's how we go about all of these points, obviously completing the square to find the turning point to get an idea of whereabouts it's going to be positioned. Obviously then getting the y-intercept from our equation and using the discriminant to figure out whether it was going to touch the x-axis or not. Okay, so on to our next question. Now again, there's a lot of words here, so I would advise you pause the video and write this all down and have a good read through, but I'm going to assume that you've done that now, so we're going to carry on and have a look at this question. So it says an arena has 25,000 tickets. They know from past events they're only going to sell 10,000 if the ticket costs £30. They also expect to sell an extra 1,000 tickets for every time the price goes down by £1. And the number of tickets sold given by t can be modelled by this linear equation, t equals m minus 1,000 1000p, where p is the price of each ticket in pounds there, and m is a constant. And for starters here, it wants us to find the value of m. It then goes on to want us to write it in completed square form and use that completed square form to think about that turning point again, looking at the maximum amount of money they could charge, or the most that they could charge in order to maximise their amount of money. So obviously I'm hoping that you've written this down, you've had a good read, so we're going to move everything to the side. And here we go, now we can get on with answering the question. So looking at this one then, for starters we've got to find the value of m, and we're given this equation t equals m minus 1000p, and it says that, let's make sure that's 1000, and it says that m is a constant. So we've just got to find out what that number is really, so we need a value of t and a value of p in order to solve that. And if we read our question here, we've been given one of those values. T is the amount of tickets they expect to sell, and we've already been told they know that they're going to sell 10,000 tickets, but on the basis that each ticket costs £30. So we have a value of p as well. So all we actually have to do to find the value of m is sub those values into our equation. So if we put them in, t is 10,000, so 10,000 is going to equal m minus 1,000 multiplied by, which I'll put in brackets, 30. So let's just look at that and expand that. So 10,000 is going to equal m take away 30,000. And hopefully you can spot straight away there that value is going to have to be 40,000, because 40,000 take away 30,000 will equal 10,000. So for part A, I'm going to write this over here so it stays on the screen. M is equal to 40,000. There we go. So we've got our value of m. Okay, so moving on to part B, it says we have the total revenue R can be calculated by multiplying the number of tickets sold by the price of each ticket, and this can also be written as R equals P brackets M minus 1000p, this information just there. Obviously we can expand that, it's just given to us in a bracket to start with, and it wants us to rearrange it into the form, and then it wants it in completed square form. So in order to do that, we just need to expand that bracket and go about rearranging it into that completed square form. And if we do that, let's get started and move all of this out of the way. First of all, we just want to expand that bracket. So let's go about expanding the bracket. So we'll get R is equal to MP, and again you could put the P first, but we've got the P at the end on the next piece, so I'm just going to keep that consistent. MP minus 1000 P squared. Now we already know from part A that m is 40,000, so we can put 40,000p rather than mp. I'm going to get rid of the r equals for the moment, just so we can actually look at completing the square for this. So at the moment we've got 40,000p minus 1000p squared. And notice that we obviously no longer have a constant here, so when we complete the square we just need to watch out for that as well. So let's rearrange that so that the p squared is first. So we have minus 1000p squared plus the 40,000p. There's a lot of zeros here. There we go, 40,000p. And to complete the square, we need to take out a factor this time of negative 1,000. Not forgetting you've got your calculator, so that's not too bad. So we'll start off by taking that factor out. So if we do that, we've got minus 1,000 outside the brackets. And in the inside here, we've got p squared. That's now going to be minus, and 40,000 divided by 1,000 is 40p. There we go. So now we just need to complete the square. So go about completing the square for that. We're going to introduce a new set of brackets. So minus 1,000, and then we'll complete the square. So halving minus 40 gives us minus 20. In brackets squared. If we were to expand that bracket, we would have plus 400, and we obviously want to get back to 0, so we just want to minus that 400, and that's going to balance out and complete that square there, and then closing off our bracket. Okay, so we've pretty much finished. All we actually have to do now is multiply that 1,000 back in, and if we multiply that back in, let's see what we get. We get minus 1,000, lots of the p minus 20 squared, and then negative 1,000 times the negative 400 gives us plus 400,000. There we go. So we've got it in completed square form. Obviously the question wants it written slightly differently, though. It does want that 400,000 at the start. So in order to do that, let's get rid of all of this, and we'll just write it in the correct way, and then we can have a look at part C without all of this information everywhere. So that is our second to last step. We just need to write it in the correct form, and that correct form is going to be 400,000 minus the 1000 p minus 20 squared. There we go. So that is part B. It's in the form that it wants, and we could say that A is 400,000, B is 1000, and C is 20. And now we can actually look at part C. So let's just label that as part B, and here we go, part C. So it says using your answer to part B, or otherwise work out how much the arena should charge for each ticket if they want to make the maximum amount of money. And again, you don't have to draw a quadratic for this, but it fits in nicely, just obviously thinking about what a quadratic looks like, and it just helps us to visualize it. So if we think about this, we have t going up here, which again, always refer back to the question. T was given to us at the start, and it says, where is it? T is the amount of tickets sold. So the amount of tickets sold is up the top, and along the bottom here is going to be our price, which is obviously what we're looking at right now, the price of the ticket. So we already know that in our completed square form, we've got our constant right there, and we have our 20. So that gives us the coordinates of the turning point. So if we think about what this would look like, we'd have some form of quadratic. We're going to have to sell some tickets. But again, we could sell 0 tickets if the price was incorrect. But if we were to draw a quadratic, we don't know exactly what it's going to look like. Let's just imagine it looked like this. And we would be looking at this particular point just here, where the amount of tickets is maximized and it's not going to start going back down because we've put the price too high. So for this one here, let's have a think. We've got 20 there as our x coordinate, not forgetting to flip the sign. So 20 and 400,000 for our y coordinate. There we go, so 400,000. There we go. So on the y axis, we'll just about fit that in, 400,000. Just about fit that in, and the price down here is going to be 20, and that is where we maximize the amount of profit that we're going to get, or they maximize the amount of money for each ticket right at that turning point. So the price that we've got there is £20. So the price that we want to sell our tickets for is £20. After that, the amount of tickets that we sell is going to start to go down. Okay, obviously the quadratic isn't going to look exactly like that, but it's just a visual example of looking at the turning point and thinking about obviously the point at which it starts to go back down again after the price has increased too much. Obviously, if we put the price as 0, we'd expect to be having a lot of tickets sold, so it wouldn't look exactly like that, but it's just a nice little visual reminder. So there we go, that is how to complete these sort of questions and how to just draw a little diagram just to help yourself visualise the turning point. So let's label it equation 1 and 2, and you've probably noticed in equation 2 there we've got this negative 5.5 here, so we're not going to get a very nice answer here, but we'll treat it in exactly the same way. So we're going to get the y coefficient to be 6 here, so with 3 and 2, so let's times the top one by 2 and the bottom one by 3, and we'll rewrite them. So 8x becomes 16x plus 6y equals 2 times 2 is 4, so 4 times the bottom one by 3, so 9x minus 6y equals negative, and let's times that by 3, we get 16.5. And now we can just go about adding them together because we've got our different signs there, so we're going to add them together. So 16 add 9 is 25, so 25x, and that's going to equal, let's add 4 to negative 16.5, we get negative 12.5. Well, that's not very nice there, but 12.5 is half of 25. But if we just go about dividing by 25, what would it look like? It would be x equals negative 12.5 over 25. Not very nice at all, but if you do get this scenario and you don't spot that 12.5 is half of 25, you could times the top and bottom by 2 just to remove the decimals, and we would get negative, what would that be, 25 over 50. That's a little bit easier to spot there, that simplifies down to a half. Okay, so that also equals negative a half, which we can write as a decimal if we want as well. We can write it as minus 0.5. Okay, so I'm going to leave it as negative 0.5. It's not a very nice one here, but we get x equals negative 0.5. Now let's sub that in. I'm going to sub it into equation 1 just to avoid using that negative 5.5. I'm going to sub it into 1, and let's hope we get a nicer value here. So negative 0.5 into equation 1. We could do that working out to the side. You've got 8 lots of negative 0.5. Now 8 lots of a half is 4, so 8 lots of negative a half is going to be negative 4. So we get negative 4, add 3y equals 2. Add 4 to both sides, so add this 4, and you get 3y equals 6, and then dividing by 3, you get y equals 2 as your final answer there. Now, just thinking about what we're actually finding here. Now, this first equation, we're going to be having a look at all these sorts of equations here, where one is a circle and one is a straight line. And if we think about that, what that would actually look like without drawing a full graph, if we had a circle and a straight line went through it, there would be two solutions there. There'd be one where it crossed over here and another where it crossed over here. That is, of course, unless the straight line is a tangent, which is going to be quite hard for me to draw, but if it was a tangent, it might just touch the circle at one point there. So it could actually only have one solution, but the majority of the time these are going to have two solutions. Now let's get rid of that. Now, in order to solve a simultaneous equation, we have to think about eliminating one of the variables. So eliminating either the x or the y, just like when we have a look at normal simultaneous equations, but there's a different process when it comes to these harder ones here. So grab a piece of paper, grab a pen, make some notes. We're going to have a look at some of these questions. Now for this first one, it says x squared plus y squared equals 13. And the second one says, well, x equals y take away 5 or y minus 5. So essentially, if we can substitute, which we can substitute this y minus 5 in place of the x, because it says x equals y minus 5, then we can actually eliminate one of the variables there. Now the way to do that is if I just stick a bracket around this y minus 5, I'm just going to put that in place of the x up here, and let's see what we get. So getting rid of the x and putting the y minus 5 would leave us with this. We'll have y minus 5, and that is x squared, so that's going to be squared, plus y squared, and that equals 13. Now we've got an equation that has no x's in. Now as long as we've only got one variable in there, we can definitely solve it. Okay, but it's going to form a quadratic, okay, with y's in, but we can actually definitely solve that. So if I just go about expanding this bracket to start with, obviously I'm going to take my time with the first one here, but I might skip a few steps as we move on. But that y minus 5 squared is a double bracket, so if we work that out first, we've got y minus 5, y minus 5. And if we expand that, let's see what we get. So y times y is y squared, then we get minus 5y, minus 5y again, plus 25. I'm obviously assuming that you are quite comfortable with some of the topics in this video here, so expanding a double bracket, and later on we're going to have factorising quadratics as well, and substitution, and a few other bits of maths. So I'm going to assume that you're quite comfortable with those if you are watching this video. If not, obviously check out the algebra series in my playlists. Okay, everything's there. Obviously don't forget those playlists are there because there's quite a lot going on in those now. But if we have a look, if we simplify this, we get y squared minus 5y makes negative 10y, and then plus 25. So if I rewrite this equation here, let's bring it over here, we'll rewrite this, but rather than the y minus 5 squared, I'm going to obviously write that expanded version. So we get y squared minus 10y plus 25, and then we've got the plus, I've not actually written y squared there, let's fix that. I should say y squared there, plus that y squared, and that equals 13. Right, there we go. Right, so we can tidy this up because we've got those two y squareds there. So we can add those together and simplify that. So we'll have 2y squared. So 2y squared minus 10y plus 25 equals the 13. Now when it comes to solving a quadratic, we need to make this equal 0. So we need to subtract 13 from both sides. So if we get rid of that 13 from both sides, let's see what we get. We get 2y squared minus 10y. Take away the 13 from the 25 leaves us with 12, so positive 12, and that equals 0. Right, now we can solve this. Now we can do this in two ways. I can solve it from there, or I can have a look at all these numbers. Now all these numbers, or all these coefficients of y squared, the coefficient of y and the number at the end, they're all even. So if they're all even, we can divide both sides of this equation by 2. And if I divide everything by 2, both sides, obviously 0 divided by 2 is still 0 on the right hand side of the equal sign. But if we divide all of these by 2, we get y squared minus 5y plus 6 equals 0. Again, I've just divided everything by 2 there. Now, this is quite nice and easy for us to factorise. So we can factorise this as it is now. So 6, the factors are 6, we've got 1 and 6, or 2 and 3. So going into our double bracket there, we've got y, and we just need to get the right pairing here that's going to equal -5 in the middle. And that's going to be -2 and -3. Now just be careful, obviously, because you can make -5 out of +1 and -6, but we have got a +6 at the end there, so it's going to have to be -2 and -3. And that makes -5 in the middle and +6 at the end. Right, so we've got our two solutions for y. I'm going to bring those up to the top. In fact, I'm going to get rid of all this working out on the left. Let's get rid of all of this. Right, so we have, for y, our y minus 2 in the bracket gives us y equals 2, +2. And our y minus 3 in the bracket gives us y equals 3. So we've got two of our y coordinates there, thinking about obviously what I mentioned at the start, that crossover point of the circle and the straight line. So we've got y equals 2 and y equals 3. Now we just need to find what x equals for both of them. So we've got this equation here, this second equation. I'm going to get rid of those brackets. We've got x equals y take away 5. So if x equals y take away 5, then I can find x for both of these coordinates. All I have to do is take away 5 from both of them. So when y is 2, we get x equals 2 take 5, so x equals -3. And for the one on the right there, we've got x equals 3 take away 5 when y is 3, so that gives us x equals -2. Right, so we've got our solutions there. So we've got y equals 2 and x equals -3, and the other one we've got y equals 3 and x equals -2. Obviously thinking about how you could write those as coordinates, so the coordinate for this one on the left here would be -3, 2, and the coordinate for this one on the right would be -2, 3. And there we go, there's our solutions for this simultaneous equation. Obviously we can pair up the values there. We could just say when x is -3, y is 2, and when x is -2, y equals 3. So it just depends on how the question's asking you to write your answer there, but we could also write it as coordinates, thinking about what that looks graphically. Okay, so looking at a different type of simultaneous equation here, only in the way that it looks, and it says here obviously solve the simultaneous equations. We have y plus 4x plus 1 equals 0, and y squared plus 5x squared plus 2x equals 0. So this looks a little bit different to ones that we've seen obviously previously. Now again, I'm going to take the same approach. I want to make one of these equations y equals or x equals, and looking at that first one there, we can see that obviously there is a coefficient of x. We've got a 4x there, so I'm going to avoid making x a subject and making a fraction out of this, but I'm going to go with making y the subject. And it's not the nicest here, because when I do move those to the other side, I get quite a lot of negatives here. So if we make that y equals, we'll minus the 4x to the other side, so we get minus 4x, and minus the 1 over as well, so we get minus 4x minus 1. Now that's not the nicest, because that's what I'm going to substitute into the next equation, and obviously just bearing in mind here, it's a nice one to pick as well, because if we had have made it x equals, we'd have had to have subbed it into this 5x squared, and we'd have had to have subbed it into the 2x, and neither one of those would have been very nice to sub this fraction into. So as it stands, we're going to substitute it in place of the y squared here, so let's go about doing that. So obviously our y now is -4x minus 1, so we have -4x minus 1, and that's all in brackets squared. And we're going to add to that 5x squared, and we're going to add the 2x to that as well. There we go, let's just rewrite that because that's a bit messy. There we go, 5x squared, and we're going to add the 2x, and it all equals 0, so that's quite nice. We don't have to move anything over at any point. So if we go about expanding this bracket, and as it's not as nice a bracket, I might just write it out so I can just see it. So we've got -4x minus 1, and we're going to times that by another -4x minus 1. So -4x times -4x makes positive 16x squared. Then we have -4x times the -1, which makes positive 4x, and the same below, another positive 4x. So that makes 8x's in total, so plus 8x. And then -1 times -1 makes 1. And again, we're going to add to that the 5x squared and the 2x. There we go, and that all equals 0. Now if we tidy this all up, we've got the 16x squared and the 5x squared, and that makes 21x squared. We've got the 8x and the 2x, and that's going to make 10x. And then we've got the plus 1 at the end. There we go, and that equals 0. Now that's not the nicest there, but in terms of our brackets, to make 21, it's unlikely going to be 21x and x. It might be, but it's more likely that it's going to be 7x and 3x in order to make that 21x squared. And obviously, as it's a 1 at the end, our only factor options are 1 and 1. So it's got to be 1 and 1 in both of these, and as it turns out, look, that's going to make a nice 10 in the middle there. We'll we've got 7x and a 3x when we expand that. So it's 7x plus 1 and 3x plus 1. Now again, we can get our two solutions from this. So x is going to equal, for the first one, negative 1/7. And for the one on the right there, we've got x equals negative 1/3. There we go. And there's our two solutions for x. Now we just need to go about substituting that back in and finding out our y values. But again, these aren't very nice values to substitute in. But we have our equation up here, y is equal to negative 4x take away 1. So y equals negative 4x take away 1. So we've got negative 1/7. So for that first one there, we've got when x equals negative 1/7, y is going to equal negative 4 multiplied by negative 1/7, and then take away 1. Obviously, nice and easy if you have a calculator. Negative 4 times negative 1/7 is positive 4/7. So we have 4/7 take away 1. And 4/7 take away 1, well 1 is 7/7. So if you take away 7 from the 4 on the top, that leaves you with negative 3/7. And there's our first one. For the next one, if we sub in x equals negative 1/3 and just follow the same process, then we have to do y equals negative 4 multiplied by the negative 1/3, and then again take away 1. Negative 4 times negative 1/3 is positive 4/3. Take away 1, 1 is 3/3. So 4/3 take away 3/3 leaves us with 1/3. And there's our two solutions. So we had when x is negative 1/7, y equals negative 3/7. And for the other one there, we had when x is minus 1/3, y equals positive 1/3 there. Okay, so there's our two solutions for that question. Just obviously showing you that obviously if they're written slightly differently, if they're not arranged in a way that we've seen before, we can still take the same approach and obviously just forming and solving that quadratic and subbing it back into our equation. Okay, so for this question here, something slightly different. So obviously do make some notes on this. Again, it's going to be very difficult to draw this particular graph, but in terms of the bits of algebra that we're going to look at in this question, it would be worth writing down the question and worth writing down part A here with our first equation, which we're going to read through, and part B with our second equation. Okay, so writing this down, making some notes on this, because you're going to have a go at this in a sec. So it says here the graph of y equals x squared minus 4x plus 2 is drawn on the grid, and again we can see that, and again we've given that as it's been labelled on the graph there. So if we're going to actually go about this, just obviously read the question, make sure it is all labelled, make sure you know what you're looking at. So for part A here, it says use the graph to find estimates to the solution of the equation, and then it says x squared minus 4x plus 2 is equal to 4. So when it says this, this means that two equations have actually essentially been set equal to each other. And if you've done solving quadratic simultaneous equations, which again I'll link in the video, you'll know that when you have two equations, particularly when one's a quadratic and they're both y equals, you can set them equal to each other. So instead of this equaling 0, this time it equals 4. So if we were to split this up into two equations, so for part A here, we could say, okay, well, we've got the graph of y equals x squared minus 4x plus 2, which is matched on the left-hand side. But on the right-hand side there, we have another equation, and that would just be y equals 4. Okay, and this is saying, where does it equal 4? Okay, where obviously if you look at the original equation, y is at the start, and we're kind of saying, where does it equal 4 on the y-axis? So what we mean by that is we actually have to draw this graph of y equals 4. And if we go to y equals 4, which is on the y axis there, we're just going to draw that exact line. So the line y equals 4 is a horizontal line that just passes through every single point where y equals 4. And if we were to draw that in, I'm going to do it with a slightly dotted line to try and get it a bit straighter. Again, because you need to do this with a ruler and a pencil. But there we go, you want to draw a nice straight line across. And from that, we're just going to actually read the coordinates of intersection, where it crosses over, and that's going to be our estimates. So again, you want to read this nice and carefully. You know already that the y coordinates there are 4, so we just want to give the x coordinates here. So the x coordinates, and again, we just want to read those nice and carefully, because we're looking for the solutions to that equation. There we go. So we can go down, read them as carefully as we can, and it looks like on the graph there we have minus 0.5 in the middle, and we have 4.5 just there. So for part A, we would say x equals negative 0.5, and the other one, x is equal to 4.5. And there would be our solutions to that equation. They are the two numbers that you can substitute into that equation to get the answer 4. Now again, you are just giving estimates, so as obviously you need to draw this as carefully as you can, but it might be that your numbers are just slightly different to mine. Maybe you got minus 0.45, or you're trying to be really, really accurate with that. So you just need to be very, very careful, okay? But that is how we're going to go about solving it. Now part B is a little bit more complicated, because if you look at this particular question, it doesn't match on the left and there's nothing on the right. So we're going to have to think about what's actually happened here. Now what's happened is it has been set equal to an equation, but it's been rearranged to make it equal 0. So what I mean by that is it could have been, let's just make it up, x squared minus 4x plus 2. Maybe they set it equal to, I don't know, let's go with 2x plus 3. Now if it was equal to 2x plus 3, this would be the line that we'd have to draw. We'd have to plot the graph of 2x plus 3 and draw it onto our grid. But we don't know what it's equal to. But if it was equal to that, in order for them to make it equal 0, they would minus 2x from both sides and minus 3 from both sides. And if you did that, you would have x squared. If we minus 2x, we'd have minus 6x, which obviously doesn't equal what it is in the question. And if we took away 3, we would have minus 1. And that's how it would equal 0. So I could get rid of this part, and I could imagine that I'd given you that question, and you would have to find out what it is that I've taken away to make it equal 0. So we're going to try and figure out how we can make the left-hand side say x squared minus 4x plus 2 again. So that's the concept of what we have to do here, and this is where it does step up, and obviously this is the hardest type of question, in my opinion, that we're going to be looking at. So let's have a look. Now we want it to say x squared minus 4x plus 2. So what would have to be on the other side? Well, at the moment we've got minus 5x. So to get from minus 4x to minus 5x, we'd have to take away an x from both sides. So instead, let's add an x to both sides. So let's stick an x on the right. And if we were to get rid of that now, it would be minus 5x on the left. So that's the x part done, but we also notice there's no number in the equation there that's highlighted. And at the moment we've got a 2. So in order to get rid of that 2, we would have to take away 2 from both sides. So we need to put a 2 on the right, because then if we took away 2 from both sides, the number would disappear. And we can just test this out. So if I take away x from both sides, let's see if it matches what we've got in the question. We would have x squared minus 5x plus 2 equals 2. That's a very bad 2 I was about to draw there. Let's get rid of that. Equals 2. And then for the final step, we take away 2 from both sides. And you probably can already see, hopefully, that we get x squared minus 5x equals 0. The 2's disappear. So that does match what we've got. So we are correct in saying that we need to draw the graph of x plus 2, or y equals x plus 2. So obviously you need to draw the graph of y equals x plus 2. And in order to do that, you need to draw a little table. So again, up to you where you draw it. I'm just going to squeeze it in up here. I'm going to plot some x values, some y values. And let's just go with negative 1, 0, 1, 2, and 3. So if it's x plus 2, negative 1 will equal 1, 0 will equal 2, and then we've got a pattern, it's going up in 2s, so 3, 5, 7. And again, you just need to plot that. So let's get rid of all this writing from part A, and let's have a go at just finishing off part B here. There we go. So, drawing this in, negative 1 was at 1, which is just there, again being very careful of the axes. 0 was at 2, 1 was at 3, and you can probably see a pattern here. It starts to go up. It's across 2 of those squares and up 1. And we can extend that line. Again, you can do it with a ruler. And just be very careful when you join those up. And there we go. Perfect. So this one here is actually quite nice, because it does actually fall on whole number coordinates. So this one just here gives us x equals 0. And y equals, let's have a look, I can't see the number under there, I think it's 2. Yeah, y equals 2. And for this one just here, we've got x equals, and again just trace your finger down, x equals 5, and y equals, trace your finger across, y equals 7. And there we go, there are two solutions. So obviously that one there we were able to give whole numbers. Again, if your line was quite difficult to draw, again you would have to give estimates for that, but this one was quite nice, it gave us whole numbers. So that's how we're going to approach these questions. That is probably one of the most difficult ones that you could probably do, because you actually had to rearrange the equation. The concept behind that is quite tricky, but I've got a question for you to have a go at. So you can have a go at this one. You can pause it, you can rewind it, you can have another look, but here is one for you to have a go at. Now very quickly, before you do have a look at your question, it is worth noting that for this particular question, because those solutions there were whole numbers, you could have actually taken a slightly different approach, but it does say to use the graph. Now for the majority of these questions, they're not going to go through whole numbers, so this was slightly unique, but I thought it was quite nice because it was easy for you to read. But of course, if you did want to find the solutions to that equation, what you could do is factorize it and solve it. Of course, we wouldn't be using the graph, and for questions where we are finding estimates, of course, we wouldn't be able to do that on a non-calculator paper, but potentially, unless we were to give answers in Surd form and things like that, and potentially our solution might take a little bit longer to find. Now for this particular one, I know we've given the x and the y coordinate, but in order to find the solution of the equation, or the solutions of the equation, we actually have two solutions. Our answer would be x equals 5 and x equals 0. So when we're finding the solution to that equation, we are not finding the solution necessarily to the simultaneous equations, so you just need to be careful of the language. So for this particular question then, it says use set notation to describe the set of values of x for which, and then it gives us these two inequalities. So we have 3x minus 5 is less than x plus 7, and 5x is greater than x minus 8. So first of all, we actually need to go about solving these, and then we'll have a think about how we write the set of values that are represented, and also how we apply set notation to that. So let's go start by solving them. So for the first one there, 3x minus 5 is less than x plus 7, we need to subtract x from both sides. So we're going to get 2x minus 5 is less than 7. Adding 5 to both sides gives us 2x is less than 12, and then solving that to finish it off, x is less than 6. So that's our first inequality. For the next one, we need to again subtract x from both sides, so we get 4x is greater than negative 8, and dividing by 4 we get x is greater than negative 2, and there is our second inequality. Now we need to go about actually thinking how this is drawn on a number line. Now again, I mentioned you do need to know about inequalities, so again, don't forget to check the link in the description if you are not sure on this next step. So let's get rid of these inequalities here, because these are the two solutions that we need to focus on. So we've got x minus 6, and we've also got the x is greater than negative 2. So if we draw a little sketch of a number line, and it only needs to be a sketch because we're just going to visualize what this actually looks like and how we would go about putting it on a number line if we needed to. Now it needs to have at least negative 2 on there, so I'm going to write it up to negative 3, and it needs to go up to 6. So hopefully I've drawn enough dashes there. There we go, perfect, it goes up to 7. So if we were to draw these on the number line, we'd put an open circle, as it's less than, not less than or equal to, above the 6, and we would point that arrow to the left, all the numbers less than 6. But we've also got this inequality where x has got to be greater than negative 2. So what I'm going to do is I'm going to put another dot, but I'm going to put it above this line, and that is greater than negative 2, so that would point to the right. So what you can see here is we've actually got an overlap, okay, or in other words, these inequalities on the graph actually intersect. So we have to write a set of values for this particular inequality, and it's between these two values. So as you know, and hopefully you remember this from GCSE, when we're writing a set of values that overlap like this, we'll put it in one of these joint inequalities. So we are going to write this as, and you can use any letter here, x is in the question, so we'll have x in the middle, arrows on either side. We have the smaller number on the left, negative 2, and the larger number on the right, which is 6. And that right there is our final answer in terms of writing the set of values for these particular inequalities. Now the only thing is that we are also being asked to write this using set notation. Now set notation just means that we're going to write it in a different way essentially. So we're just going to have a look at how we write this. Now obviously you hopefully have got that written down, so I'm going to get rid of this linear scale that we've drawn there, our little number line, and we're going to look at actually just changing this into set notation. Now, in order to do that, when we write these things in set notation, we put them in little curly brackets. So all we're going to say for this is that for our set, and here's our start of our curly bracket, for all values of x that we're looking at, we put a little colon there, they are between -2 and 6. And then we close our little curly bracket, and that is literally it for set notation. Now, some of these bits never change. They're always going to be in a curly bracket, and we're always just going to put this little for values of x here at the start, and then we write our inequality. And that would be it writing this in set notation. So very hopefully nice and simple. A tiny little step up there from GCSE in terms of the way that we write it, but it's just a different way of writing the inequality there, and that is writing it using set notation. Now again, the question looks very, very similar. It says use set notation to describe the set of values of x for which, and then we have our two inequalities. But there is one very big difference. This time it says or. And if you noticed on the last questions, it said the word and. So this relates to set notation. It gives us a big hint here that we're going to have two different inequalities in this case, as it says the word or. If you remember from GCSE level, there is a symbol that can be used instead of the word or, and it is the little U for union that we met when we did Venn diagrams at GCSE level. So we are going to be using that symbol when we get to the point in the question of writing our set notation, but in terms of actually getting to that point, it's very similar to the last one. So we're going to solve both of these inequalities, and then we're going to draw that on a number line, and we're going to then have a look at how to write our final answer. So focusing on the first inequality, this one here, we are going to get the x's on one side. So let's add x to both sides to get rid of that negative x. So that would give us 1 is less than 2x minus 5. Add the 5 would give us 6 is less than 2x. And then we would get, dividing by 2, 3 is less than x. Now it's probably a bit easier just to swap that over. Remember, if you want to swap the sides of the x and the 3, you just have to move the inequality to be pointing the other way. So that would just say x has got to be greater than 3, which is always just a little bit nicer to look at. So x is greater than 3. On to the second one. Let's add 3x to both sides. So for this one here, we have 5 plus 5x is less than 15. Take away the 5 from both sides. 5x is less than 10, and divide by 5 both sides, x is less than 2. Right, there we go. So we've got our two inequalities. So again, we can get rid of some of this working out. We can just focus on our two inequalities there and how we're going to write those in set notation. So if we think about this, we've got x has got to be greater than 3 and x has to be less than 2. And if we draw this on a number line, and again, we've only got a few numbers there, so we'll just go from 1 to 4 or something like that, or 0, 1, 2, 3, 4. And if we were to draw our inequalities on here, again, open circles because it is less than or greater than without the equal to, we would have x has got to be greater than 3 pointing this way, and x has got to be less than 2 pointing this way. So as you can see, there's no crossover, so we're not going to have one of those joint inequalities, but we are going to have two separate ones because we do not want to include any numbers between 2 and 3. So in order to write this, again, in terms of our answers, we've actually got them both just here. We've got x has got to be greater than 3 and x has got to be less than 2. So all we actually have to do is put this straight into our set notation. Now it looks very similar. We still use our curly bracket. So we're going to say for the x values where x is, and it doesn't matter which one we put first, let's just put x is less than 2 for the start. And there we go, close our curly bracket. And then we come back to this word or. So or, using our symbol there, or, okay, we can also have the set where the x values are greater than 3. There you go, so it looks very, very similar to the last one. And that's our final answer. So this answer, if we read it, we've got for the x can be less than 2, or x can be greater than 3. And that's our set notation, how we would go about writing it here when there isn't a crossover and there's not an overlap. Those inequalities on the graph do not intersect at any points. Okay, so this question's slightly different. It says find the set of values of x for which both 2x squared minus 5x minus 3 is bigger than 0 and 8x minus 7 is less than 5x plus 5. Now this one on the left here, we have actually just solved that, obviously just to save a bit of time here, but when we have two different inequalities like this, we need to just have a look at the two different solutions and try and come up with a sort of an answer that makes sense here, and we'll have a look and have a think about what that could be. Now for that first one there, we've already solved that. We got our two solutions. So very, very quickly, obviously when we factorise that, we got 2x and x, and we had 1 and 3, and it was minus, which way was it? It was minus 3 here and plus 1. We got our solution, which was negative a half and positive 3. And then we wrote our two inequalities, so we had x had to be less than negative a half, and x had to be greater than 3. Now with our other inequality over here, if we go about solving that, let's have a look. We've got 8x minus 7 is less than 5x plus 5. So getting rid of the smallest x from both sides, we get 3x minus 7 is less than 5. Add the 7 to both sides, 3x is less than 12, x is less than 4. So we've got three separate solutions here. Now what we've got, and we need to have a look, because we've got x is less than minus a half, and that's okay, that fits in with my x, it's got to be less than 4 over there. But this one here, we've got x has got to be greater than 3. But over here it says x cannot be less, x has got to be less than 4. So in terms of our solutions here, these two are quite important. Now x being less than minus a half, that's okay, that fits in with this one, so we don't need to worry about those two. But these two obviously contradict each other. We can't have values that are greater than 3 and less than 4, apart from the values that are between 3 and 4. So what we can do is we can combine these together, and we can say, okay, well, we can't be, we got to be bigger than 3, that's okay, but it stops at 4. And that's what that would mean just there. That means the x values can be between 3 and 4, and also we've got the one over there, x is less than minus a half. So if I get rid of that bit, and that is our final bit of the solution there. Obviously just thinking about what that means, values can be bigger than 3, but given that one on the right, they also have to be less than 4. So our solution there is, okay, well, they can be between 3 and 4, and also less than minus a half over there. So there we go, you just got to watch out when you have these two here and thinking about what values actually satisfy those inequalities. Right, okay, so 3 more here. On the grid, shade the region that satisfies these inequalities. So for the first one, we've got y is less than 3x, or y equals 3x is the one we're going to plot. So that doesn't have a y-intercept, so that y-intercept is going to be 0. I should be careful with my language there. It does have a y-intercept, it's just that it's not a whole number there. We've just got the 0 as the y-intercept. So we're going to start at 0, it's got a gradient of 3. So I'm going to go across 1, up 3, across 1, up 3. I'm going to follow that pattern going backwards, so left 1, down 3. Left 1, down 3. And there we go, and that's our first line there. Y is equal to 3x, and it's going to be a dotted line. As we've not got the extra ink on the inequality, it's going to be less than 3x. There we go. So let's just draw that in as best you can, obviously using a ruler and a pencil. Now we've got the next one. So y equals 0. That's an interesting one. Y equals 0 is actually the x-axis. It's just another name for the x-axis. So we can go across here. That's the line going through all the points where x equals 0. Sorry, y equals 0. There we go, going across. There's our second inequality. And our last one here, which isn't the nicest, we've got 4x plus 3y equals 12, and we need to draw that. Now again, one that looks a bit dodgy, so I'm going to apply that same logic. I'm going to go when x is 0, so we've got 0 plus 3y equals 12, because 4 lots of 0 is 0 there, so 0 plus 3y equals 12. Well, 3 times the number has to equal 12, so y has to equal 4 for that one. There we go. So when x is 0, y is 4, so we just need to find that coordinate. So 0, 4 is there. And the next one, let's do that the other way around. So when y is 0, what's x going to have to be? So we have 4x plus 3 lots of 0, so 0 equals 12. Well, 4 times the number has to equal 12, so that has to equal 3, so x has to be 3 there. So when y is 0, x is 3, and that is there. I'll draw a bit of a bigger cross so we can actually see that. There we go. So we can draw that in, taking that logical approach there. Not the easiest one for me to draw on the screen here, so I'm going to do my best, but obviously you will have a ruler and a pencil, so all you have to do is join those two together and draw a nice straight line. There we go, going through that. Right, there we go. Obviously I've just extended a little bit past the line, past the graph there, but that doesn't really matter. Let's get rid of that. Right, okay, so we've got a basic outline of what it would look like. Obviously yours would be a bit more accurate here when you're using a ruler and a pencil, but that is that last line drawn. Now you could have taken a different approach for that one again. You don't have to take this approach. Just remember, to get that into the form y equals mx plus c, we'd have to take away the 4x from both sides. So we'd have 3y equals negative 4x plus 12. And then we'd have to divide both sides by 3, so we'd end up with y equals negative 4 over 3 divided by 3, x plus 4. There we go. And you could actually plot the graph from there, just remembering what that means. It means there's a y-intercept of 4, which we already have, and then that gradient there just means we've got a rise of 4 and a run of 3. Obviously it's going downwards, so we could go along 3, down 4, along 3, down 4. Obviously just reversing the idea of the gradient there. But again, obviously, if you want to look into these gradient bits a little bit more and understanding these line equations, do check out those videos in the description and look at that coordinate geometry series. That's going to really help with understanding that. But there we go. I quite like just taking the logical approach and imagining one of the coordinates is 0 and finding the other coordinate that matches and then just joining them up with a ruler. It does work for all of these. Right, so let's get rid of all of these. We need to find our region then. So let's have a look. Now we've got a nice little coordinate inside. We've got 1, 1 there. So let's go for that inside the triangle. See if it works. So 1, 1, so x is 1, y is 1. So we've got 1 is less than 3 lots of 1. 1 is less than 3. Again, that's correct. So we can tick that off. The next one, we've got 1 is bigger than 0. Y is 1, sorry. So 1 is bigger than 0. That's correct. And on to the last one. 4 lots of 1 is 4. Plus 3 lots of 1, which is 3. So 4 plus 3 is less than 12. And that's obviously 7 is less than 12. And that's correct as well. So we can tick that off. And there we go. That is our region. Definitely correct there in the middle. Again, this little triangle in the inside. Right, there we go. So that is obviously how to draw inequalities on a graph and how to find the shaded region. Now, as I said, I've linked in the description a link for the worksheet for this these next 4 particular questions. So make sure you've got that either printed off or just follow along with me, or you could even draw it out yourself if you've got squared paper. They're not particularly difficult to draw. I do actually tend to draw these myself anyway, just to get a good understanding of obviously drawing the axes and getting it all plotted to scale, okay, and making sure that you're aware of that. Sketch the graph of y equals x cubed minus 6x squared plus 9x, showing clearly the coordinates of the points where the curve meets the coordinate axes. Now at the moment, obviously we've got the full equation here that needs factorising first. So we have x cubed minus 6x squared plus 9x. Now these are the nicer versions of the cubics, because these are nice and easy to get a nice little quadratic out of them in order to factorise quite nice and simply. If we went much more complicated on these, we'd have to use the Factor Theorem, and obviously that sort of starts incorporating quite a lot of maths. So we get quite a large question if we were to do that. But obviously check out the Factor Theorem if you want to have a look at factorising some of the harder cubics here. But we're going to just focus on some of these slightly easier cubics for drawing these, as it can get quite complicated otherwise. But let's have a look. Now, in order to factorise this, we can take out a factor of x to start with. And when we take x out, as there's no number at the end, we get inside a nice quadratic here. We get x squared minus 6x plus 9. Okay, so that obviously gives us our first solution there. We've got x equals 0 for that x on the outside. Now we can go about factorising this quadratic. So obviously if we turn this into a double bracket, our factors of 9, we can have 3 and 3, or 1 and 9. And if we want to make negative 6 in the middle, it's going to be minus 3 and minus 3. So x minus 3, x minus 3. There we go, and we've got that x on the outside. So there is the equation of our graph if we factorise it. And then obviously again that gives us our 3 solutions. So we get x equals 0 for that one there. We get x equals 3 for this one here, and x equals 3 for this one here. And again, we know there's no y-intercept because we have no number at the end of this equation here. So we know the y-intercept is going to be 0, which we've also proved just via this solution here of x equals 0. So we can go about just drawing it just like we did before now. So draw your axes, it's positively sloping, it goes through 0, then it goes through 3, and it's just going to touch on 3 as well, as we've got those 2 solutions here of 3. So in actually just drawing that, and not forgetting, this isn't the nicest one to be fair, because we've got, 2 solutions at 3, so you just need to watch out, obviously, the fact that it's sloping up, and it's going to go up through the origin. Oh, let's do that again, up through the origin, down, just touching at 3, and then sloping back up again. Right, there we go. So no y-intercept, well, the y-intercept of 0, and obviously those 2 solutions on 3, so just touching on the 3 point there. Okay, so this question says sketch the graph of y equals, and then we have our equation there showing clearly the coordinates of the points where the curve meets the coordinate axes. Now if you look at the equation that we've been given, you can see that if we were to expand that out, our highest power would be a power of 4. So this is going to be a quartic graph. And when we have a quartic graph, there's 2 different ways that it's going to look. We could have a positive quartic graph, which is going to have this sort of shape with a little wiggle, or we could have a negative quartic graph, which is going to have this sort of shape. And again, those wiggles that we have in the graphs are going to be slightly different depending on our roots. So we know this is going to be a negative one, so it's going to look like my graph on the right. So we know which way it's going to be sloping, we just need to figure out those roots. So to start with, we have the pieces at the beginning. So the x at the beginning, just here, represents a root where x is equal to 0. So we know one of our roots already. For the second one, we have 3 minus x, and again, if you're not sure on the root there, you can set it equal to 0 and solve it. So if we say that 3 minus x is equal to 0, and if we add x to the other side, we get 3 is equal to x, or of course we could write that as x is equal to 3. If we move on to our quadratic there, we're going to want to factorise that to find our roots, and if we factorise this final quadratic, we get in double brackets x plus 2 and another x plus 2. Now that could be written in a slightly different way, of course. We could write that as x plus 2 in brackets squared. Now when we have that going on, that means we have a repeated root, which means our curve at some point is going to bounce off the axes. So if we go about drawing a sketch of this and we draw an axis, we obviously have all our roots. We have x is equal to 0, which we can label on there. We have x is going to be equal to 3, which we can label over here. And we just need to get our root for that x plus 2 in brackets squared. So the root for that is going to be x is equal to negative 2. And of course that's a repeated root, so we don't have to draw that twice, but we're going to want to label negative 2 over here so that we can make sure this curve looks correct. So we know the shape that it's going to be in, and it can help to draw the shape just to the side of the graph if that helps, just so that you can remember what it's going to look like. So for a negative one, it is going to have this sort of shape, and we're going to need to draw that onto our curve, or onto our axes. So for this particular one here, when we draw this one on, the first thing that you're going to notice when we go up is that straight away we have that repeated root. So as we come up to the negative 2, it's going to bounce off the axes. It's then going to go up through the 0, as that's our next root, and then it's going to go up a certain distance and it's going to come down through the 3. So you can see we have that negative quartic shape, and again the first thing we had to be aware of was obviously that bounce there for our repeated root, but 0 and 3 were distinct roots, so it does pass through those points. Okay, so this question says sketch the graph of y equals 3 over x with a minus 1 at the end, and we'll have a look at that in a sec. It says showing any points at which the curve crosses the coordinate axes and writing down the equations of the asymptotes of the curve. So let's have a look at this line equation to start with. Now we know from graph transformations that if we change the x value, it will move it left and right, and if we change the y value, which is what this does at the end here, it moves it up and down. So minus 1 at the end, thinking about a graph transformation, and from GCSE we'll have sometimes seen it like this. We might have seen f of x, there we go, with a minus 1 at the end. And that there is outside the bracket, it affects the y coordinate, and minus 1, it does what we expect, it moves it down by 1. So if we draw a little sketch of this to start with, I'm just going to have a look at, to start with, the graph of y equals 3 over x. So y equals 3 over x, and what does that look like? Okay, and we're going to draw this on pretty much all these questions, and it goes into this area here. Now if I then do this transformation, so I'm going to do this function here, I'm going to take away 1 at the end, which moves it down by 1. We'll have a look at a basic sketch of what that looks like. There we go. So if I move it down by 1, then this part here is going to go down below the axes, and this part here is also going to move down as well. And that's what our graph there is going to look like as a basic sketch. Now thinking about those asymptotes, obviously on the first one here that I've drawn, 3 over x, and let's just label that other one there. So this one here is our y equals 3 over x, but with minus 1 at the end. Originally, as we mentioned on the first bit, our asymptote across this way, which has the equation y equals 0, has now moved down by 1. So it's going to move down 1 here. There we go, and that's going to move down to minus 1, so y is going to equal minus 1 for that asymptote. There we go. Now obviously the graph here has moved downwards, it hasn't moved left or right, so our original asymptote over here, which goes down, which has the equation x equals 0, it's not going to change. Okay, so that is going to stay exactly where it is, and we've still got that asymptote there where it never touches the axes. There we go. So x equals 0 is going to stay exactly the same. Now there's one more element that we need to have a look at, because obviously on our first graph it never crosses over the axes, but now we've moved it down, this one on the left does cross the axes. Okay, it crosses over just here at that point. So we need to find out what is that coordinate just there. And there are two ways of doing this, because it either crosses over the x-axis or the y-axis, and at that point there it crosses over the x-axis, and if a graph ever crosses the x-axis, the y-coordinate there is 0. So for that point there, I know that y is equal to 0. And all I need to do is sub that into my equation and solve for what x is going to be. So if I put that in, obviously we're looking at this equation here, y is equal to 3 over x minus 1. So if I put 0 into there, we have 0 equals 3 over x minus 1. And I just need to solve that. So if I add the 1 over to the other side, we get 1 is equal to 3 over x. There we go. So 1 is equal to 3 divided by something. Now logically we know that the answer for that is 3. 3 divided by 3 equals 1. But I also just need to keep going with this and obviously just solve it in a normal way, because some of them aren't going to be quite as obvious to see. So I can multiply the x over to the other side. So I get 1x, or x equals 3. There we go. So I'm actually just multiplying it over. That's quite a nice one, because it straight away gave me the solution there as x equals 3. But there we go, that's the point at which it crosses over the x-axis. So I'll just get rid of this and I'll label that on the graph there on my sketch, and I'll put that as 3. There we go. It says here on the same axes, sketch the graphs with equations, and then we have these two equations to draw here. So we've got y equals, we have x brackets x plus 1 brackets x minus 4, and we also have this other graph, y equals 2 over x plus 1. It says to indicate all the points where the curves meet the x-axis, and hence write down the number of real solutions to this equation here. And yeah, as you can see, they've set those two equations equal to each other. Okay, so we have the x with our brackets here, and we have our other graph, 2 over x plus 1 on the right. So we're going to have a look at obviously doing that and drawing these graphs and seeing how we approach them. Now first things first, we need to be aware of the different types of graphs that we could be looking at drawing. Obviously forgetting about straight line graphs for the moment, just thinking about our curves as both of these are, we can have a quadratic, a cubic and a reciprocal. Okay, and there are other graphs as well, but throughout this video they're the main ones that we're going to be focusing on, with a little bit of straight line graphs thrown in there as well. But at each of these points we're either going to have, and I'm going to draw these to the side, we could have a positive quadratic which makes a U shape, or a negative quadratic which makes that N shape. We can have a positive cubic which makes this sort of shape, or a negative cubic where we have a negative x cubed. And then as well as that we can have our reciprocal graphs as well, which depending on how we draw our axes, we can have our positive reciprocal which has a little bit, well, looks a little bit like that, or we can have our negative reciprocal which looks just the other way around in those two. Okay, so we're going to be mainly drawing these 6 graphs here, and obviously as I said, you need to make sure that you're happy and aware of these sketches here, so obviously do check out sketching quadratics, cubics and reciprocals in the videos in the description. So let's have a look at this first one then. Now the first graph there, we have 3 x pieces, they're going to be multiplied together. There is the x, there's the x there and the x there, and they're all positive. So that's going to make a positive cubic graph. Now the solutions are given to us in this particular one here because it's already been factorised. So when we've got that one there, we've got the first x at the start, which gives us one of the x interceptions, and that's going to be x equals 0. So I'm just going to write this down. We've got x equals 0 as our solution for that one. We have the x plus 1, okay, and that's going to be x equals negative 1. Okay, remember you just flip the signs, or you just set it equal to 0. Remember if there are any difficult ones, you can just set it equal to 0, so we can say when does x plus 1 equal 0, and then minus the 1 from both sides, we get the x equals negative 1, which is why you can just flip the signs, but don't forget you've got that process there if any more difficult ones come along, which they will. And then we've got the last one there, where x minus 4 in the bracket, and that gives us x equals positive 4. So there's our 3 solutions, and we already know the shape of the graph. It's going to be a positive cubic, so it's going to look like that. So if we start to draw our axes, let's just draw it in. And I'm not going to actually draw this graph just yet, but I am going to put these points where I know it's going to cross over. So we have -1 and 4, and remember it is just a sketch, so it doesn't have to be absolutely perfect. It's more about where it crosses over and the shape of the graph that we're getting correct here. So there we go, I know it needs to be around about that big for the moment. Now we have our other graph there. Now that one below is a reciprocal graph. Whenever you're getting a divide by x, that's going to form a reciprocal graph. Now it's a positive x, so it's a positive reciprocal. So we know in terms of just a little basic idea what it's going to look like. It's going to look something like that. But this one here also has a +1 on there. And hopefully you'll remember that with a +1 at the end, that's going to change the y-intercept. Okay, or in other words, with not obviously we don't have a y-intercept with our reciprocal graphs, but with a normal graph, it changes the y-intercept, it moves it up 1. So in terms of our reciprocal graph here, that is going to move up 1. And if I draw just over the top of my sketch there, it just means it's going to be up a little bit higher. Okay, so it's going to cross through the x-axis in that negative region there. Now in terms of actually drawing this, before I draw the sketch, again, I just want to know where it crosses the x-axis, okay, because I don't want to have to redraw my sketch twice. So let's figure out where it crosses the x-axis, and that's easy enough to do because we can just set y equal to 0. Okay, remember that from coordinate geometry. If you ever want to find where a graph crosses the x-axis, just put y equals 0 in. So if we sub that in, let's do that down here, we get 0 equals 2 over x plus 1. And just remember, the reason I'm doing this is because any position on the x-axis, the y-coordinate is 0. So if we sub that in, and now we just need to solve it. Not the nicest one to solve, just because we have a little bit of movement to do. It looks like it should be nice and quick, but we have to minus 1 from both sides. So we get -1 is equal to 2 over x. Multiply both sides by x, so we get negative x, or negative 1x equals 2. And then divide by -1, and we get x equals -2. There we go. So there we are. We know it's going to cross over at x equals -2, and I'm going to write that down up there. X equals -2. I'm just going to mark that on the graph as well. There we go, -2 there. And now we can go about drawing these in because we know where it's going to cross over all these different points. So if I draw the reciprocal in to start with, so my reciprocal is going to look something like this. And the other one on the right there is also moved up, so something like that. Again, it's not perfect, okay, but you just have to draw these as best you can. Just extend that axis there. And there's our first part of drawing the reciprocal. And I didn't have to draw that one first. I could have drawn the cubic first, but as I've just finished that one, we'll draw that one in. Now the second one that we need to draw here is the cubic. And like we said, we already know what it looks like. We've drawn a little sketch of it up here. So it's going to go up through that -1, back down through the 0, and then up through the 4. So if we go up to the -1, back down through the 0, and then up through the 4, and again I can probably just extend that reciprocal graph a little bit. Again, it is only just a sketch, so you are going to have these little situations where you're drawing them where they don't quite meet, or you haven't quite drawn it big enough, or maybe you've drawn it too small. Okay, so if you do that, obviously just make sure you're always drawing it in a pen with a pencil and ruler, and you can always just rub it out and go again, or just draw a second sketch. Okay, it's all about just a little bit of practice with these and just perfecting your graphs as you draw them. But there we go, there's our sketch. If we actually put this onto a graphing calculator, we'd probably see that it's not perfect. Okay, and these little dips and within that cubic graph could potentially be a lot more stretched out, but as it's only a sketch, we're not going to stress too much about that. And actually we'll have a look at what it looks like in a sec. But before we do that, it says here, hence write down the number of real solutions to the equation, and then what they've done here is they've just set them equal to each other. Now if you remember from GCSE, if you want to solve two sort of graph equations algebraically, all you have to do, as long as they're both y equals, you just set them equal to each other and find the x coordinate, okay, solving them simultaneously, and then you sub the x coordinate back in to find the y coordinate. But this question here has said, hence, obviously using our diagram there, write down the number of real solutions to this equation. It doesn't want the solutions exactly, it just wants to write down how many there are. So as we can see on the graph here, we've got one here where they cross over, and we have another one just there. So in total, we have two solutions as the graph crosses over, the graphs cross over at 2 points there. Okay, so we would obviously just say two solutions as the graphs cross over at 2 points. I'm just going to write that in there, two solutions, and there we go. Okay, so that's the end of our first question. Obviously there was drawing reciprocal graphs, so there's a little bit of graph transformations there as well with the +1 moving it up by 1. And we actually also had drawing a cubic graph, and we had some solving equations. So as you can see, there's a lot of different topics in here, even though once you've got the hang of drawing these, the topic is actually relatively straightforward, okay, once you've done quite a few of them. But you can see there's quite a lot of topics involved here, so do make sure you check out any of those videos on previous topics obviously relating to this. But that's our first question, and before we move on, let's just have a look at what this would look like. Okay, so if you use this app, and it's a great little app to use, it's called Desmos. So all we actually need to do to have a look at that graph there is just type in the equations for these two graphs. And it's a really good tool when you're doing topics like this, just for having a look at what these graphs look like. So if we type them in, we can have y equals x, and then what was it? It was brackets x plus 1, close brackets, and then it was x minus 4 in the other bracket. X minus 4, there we go, and that's going to give us just a little overview or kind of little look at what it actually looks like. If we put our second graph in then, which was y equals, we had 2 over x, so 2, and we'll put divide by x, there we go, come out of the fraction, and then we'll put the plus 1 there, and that shows it obviously moving up slightly. Now it's really good look because obviously we can see that our graph wasn't too far off, the reciprocal looked good, and the negative part of the graph on the left there looked good, but obviously this dip was a lot bigger, well, a lot smaller on the sketch that I drew. Okay, but as I said, it is just a sketch, but it's a great little opportunity just to have a look and actually see if your sketch is correct. And as we can see, there's one crossover point just there, and there's another crossover point just there. And as well as that, we can also see where it crosses through the x-axis. We can see the -2 over here that we had. We can see these solutions here, the -1, the 0 and the 4, and we can pretty much check everything that we had on that question. So just a little thing for you to have a look at. It's called Desmos. It's a great little app. You can get it on your phone or on an iPad or on a computer. It doesn't really matter what device you use, and you should be able to access this on anything. So there we go, just a little thing to show you along the way. Let's have a look at our next question. So this is the diagram, shows the part of the curve with the equation y equals f of x, and here it is in the diagram. The maximum point of the curve is 2, 3, as we've already seen. Write down the coordinates of the maximum point with these different equations, and I've got quite a lot here, all the different scenarios we could actually have a look at. So for part A there, okay, it says f of x minus 2. So that's inside the bracket, so it affects the x coordinate, and it does the opposite of what we'd expect. So it doesn't subtract 2, it adds 2. Okay, so it just does the opposite. So the x coordinate being 2 there, we would add 2 to the x coordinate, and that would make it 4. And the y coordinate's not going to change, so that would stay as 3. Okay, so that's the opposite of what we'd expect, and we add 2 to the x coordinate. Looking at the next one, let's try to change to a different colour here. Right, so f of x minus 1. Now that minus 1 is outside of the bracket, so it's outside the bracket, it affects y, and it does exactly what we'd expect. So minus 1, we would expect that to subtract 1 from the y coordinate, which it does. It just changes the y-intercept actually. If you're familiar with your equations of lines and your coordinates, coordinate geometry, you should hopefully know that number at the end is the y-intercept there. So it's taking away 1 from the y-intercept, essentially just moving the graph down 1, but we'll have a look at that again a little bit later. But minusing 1 from the y-coordinate, the y-coordinate currently is 3. So if we take 1 away from that, the x-coordinate doesn't change, so 2. But the y-coordinate's also going to drop down there to 2. It's going to subtract 1 from that. Okay, so that's how we could have different scenarios there with just adding and subtracting numbers, and how that affects the x and y coordinate. Now we're going to have a look at question C, part C there. So y equals f of 2x. So 2 times x. Normally when you're timesing by 2, you'd expect that to double something, but as it's inside the bracket affecting x, it does the opposite. So rather than multiplying by 2, it divides it by 2, or halves it there. So if we look at the x-coordinate is currently 2. So half of that, halving it because it's inside the bracket, and changing the x-coordinate, but does the opposite. So half of 2 is 1, and the y-coordinate remains unchanged, and that remains as 3. There we go. So that's that one. Let's have a look at the other scenario where it's outside the bracket. So 3 lots of f of x for part D here. Let's have a look at what this does. So it's outside the bracket, it affects y, we're multiplying it by 3. So it does what we'd expect, it makes it 3 times bigger, but it affects the y coordinate this time because it's outside the x bracket. So 3 lots of that y coordinate, the y coordinate's currently 3, so the x coordinate is unchanged, and the y coordinate gets multiplied by 3 and becomes 9. Right, there we go. So that is our scenarios where we are multiplying by a number. So in terms of the x there, inside the bracket 2x does the opposite, so divided by 2, but outside the bracket it multiplied the y coordinate by 3. Okay, and onto these negative ones here, which don't really follow the same trend, but partly it does. So we'll have a look at this one here. So when we've got minus x in there, now it doesn't do the opposite of what we'd expect, because the opposite of minus x would just be nothing. Okay, we wouldn't actually change anything at all, it'd just be positive x, it'd be the same equation. Okay, but we follow the rest of the rules for this one. It's just that it goes a little bit out the window when we look at our minuses here. So when we've got a minus in there, all that does is it swaps the symbol of the x coordinate. It's still affecting x, it's inside the bracket, it just doesn't do the opposite this time, okay? So it just changes the 2 as the x coordinate to -2. So the x coordinate's going to change, it becomes -2, and the y coordinate remains unchanged, stays as 3. Okay, so this when there's a negative in there, that's the only scenario where it doesn't actually do the opposite or anything like that. We just have to worry about, is it next to the x or is it changing the y, and it just flips the sign. So the last one here, we've got y equals minus f of x, and again the minus there is outside the bracket, so it changes the y coordinate, and again it just swaps the sign, so instead of being +3 there as the y coordinate, it's going to be -3. So we have +2 still, and -3. Okay, so again, just following all those little rules, is it next to x or is it next to the y or outside of the x bracket? And that tells us which coordinate it affects. When it comes to adding, subtracting, multiplying, okay, we can think about the opposite or whether it does what we'd expect. The only scenario where it doesn't is where we've got this little minus symbol in there, and that just changes the positive or negative symbol of the corresponding coordinate, whether it's x or y, whether it's inside the bracket or outside the bracket. Okay, so it says the diagram shows part of a curve with equation y equals f of x. Draw a sketch of the graph with these two equations. So I'm going to do 2 on 1 graph just to save a bit of time here. So part A says to draw y equals f of x minus 4. Now we know that x minus 4 here is going to plus 4 to all the y or to the x coordinates. So add 4 to x. Okay, now all we've got to do is make sure that we find any whole number coordinates on this graph, and they're the key ones. So I can see quite a few, and I'm going to highlight them here. So we've got 1 here, we've got 1 here, and we've got a few down the bottom here that go through actual whole number coordinates. So they are the coordinates that I need to make sure I move perfectly when I'm drawing my little sketch. The rest, we can just do it as accurately as we can. So if we're going to add 4 to the x coordinate, well, let's look at this one here to start with. That coordinate there currently is 0, 4. So when I add 4 to the x coordinate, that is going to become 4, 4, okay, adding 4 to the 0. So 4, 4 is the coordinate here. And you can see there, that's moved it right 4 spaces, and that's what that transformation there actually does. Okay, so when we actually add 4 to the x coordinates, they're all going to move right 4, and therefore it's going to be translated, okay, to the right. Okay, so we're translating it 4 to the right. Now looking at the other one, this one here, if I move that 4, that's going to land on top of that 0, 4 coordinate, so I can't draw over the top of that, but that's where that's going to move. The one down the bottom here, this -2, that if we move that right 4, that's going to go to here, and then moving the others right 4 is going to place them there and there. There we go, and that is how they would move. Now if I just get rid of some of these bits here, because we're going to do another one in a sec. Let's get rid of all of them, and let's just sketch that in. And you've got to just do this nice and neat, okay, as best you can, drawing a nice smooth curve, making it look as best as you can, like the one on the graph there. There we go. So not perfect with my lines there, but just moving it right 4 and showing that it goes through those whole number coordinates. And let's have a look at part B here. We've got y equals f of minus x. Now minus x, we know, changes the symbol on the x coordinates. So again, if we pick a coordinate, and let's pick this one to start with. Okay, so this one here, and let's label this over here, that coordinate there is -2, 0. Okay, so if we swap the symbol on the x coordinate there, that's going to become +2, 0. Okay, so +2, 0. Again, let's get rid of this first graph. +2, 0 is here. There we go. So let's have a look at another one. Let's pick this coordinate here. There we go. So that coordinate there is -1, 0. And if we change the symbol in front of the x coordinate, that becomes +1, 0. So +1, 0 is there. And let's have a look at one more down here on the bottom. We might be able to figure out where the rest are going to go afterwards. This one here is -3, 0. And again, swapping the x coordinate there, that becomes +3, 0. Which is just here. So hopefully you can see it. Actually, this curve is going to end up in exactly the same place as the last one. But what's actually happening here, let's have a look, let's just get rid of all this so we can see it a bit better, is something slightly different to the last one, because that last one was a transformation. It was actually moving right 4. Whereas if you have a look at, and I'll try and do them in a different colour here, this coordinate here, the purple one, moved to this coordinate here. So actually it's not being moved in the same way, because as well this coordinate here is moved to this coordinate here. What this is actually doing is reflecting the shape in the y-axis. Okay, and you might actually be able to see that this coordinate here as well would move to, just make sure I do this carefully now that I'm not writing down the coordinates, it would move to there. And the coordinate which is here on the axes is not going to move anywhere, it's going to stay where it is. So actually what's happened is the curve has been reflected, but all you've got to do is reflect those or change the symbol in front of those x coordinates. And again, just sketching it in nice and neat. So it's quite unique there because, oh, there we go, not very good there. Make sure you do go through the coordinate points. But although there were two different transformations there, two different changes in the function, the graph did end up in the same place, but there were different transformations. One's a reflection and one was a translation. Okay, but as it turned out, they ended up in the same place for that one. Okay, so this question says find the equation of the line that passes through the coordinates 5, 7 and 3 and -1. So when we are finding equations of straight lines, there are two formulas that we need. One is to find the gradient, which is that m is equal to y2 minus y1 over x2 minus x1, or the change in y over change in x. And the second thing that we're going to need is our equation of a line, which is y minus y1 is equal to m brackets x minus x1. Of course, you can use y equals mx plus c still, but this equation is just a little bit quicker. But again, you can use y equals mx plus c whenever you like. So if we plug these values in, and we'll have this as our first coordinate and 3, -1 as our second coordinate. Okay, so if we find our gradient to start with, that is going to be y2 minus y1. So we will have -1 take away the first one, which is 7, over 3 take away the first one, which is 5. So on the top that comes out as -8, on the bottom that comes out as -2, so we have a gradient of 4. So we can just say that the gradient is equal to 4. We can then put that into our equation of a line, so we're just going to substitute that into y minus y1 equals mx minus x1. And if we sub these pieces in, and again I'm just going to use the first coordinate there, so 5 and 7, and if we substitute those in, we get y minus 7 is equal to 4 lots of x minus 5. And all we have to do is expand this and make it y equals, and we will have our line equation. So we have y minus 7 is going to be equal to 4x minus 20, and then you just need to add 7 to both sides, so we get y is equal to 4x minus 13. And there we go, we have our line equation done. Okay, so find the equation of a line perpendicular to y equals 2 minus 3x that passes through the point 6, 5. So first things first, let's get the gradient out of this. Now it's written in a slightly different way because it's got a negative gradient, but our gradient there is -3, the number in front of the x. So let's write that down, m equals -3. Straight away we're finding a perpendicular line, so let's find the perpendicular gradient. So mp, change it to positive, flip it over, it becomes a third. Right, so we just need to put a third into our line equation, so writing down y equals mx plus c. And then let's put this gradient in. So we get y equals a third x plus c. Right, from there, same process again. So we're going to sub this coordinate in, 6, 5, as that coordinate is on our line. So 5 equals y, so 5 equals 1/3 times the x coordinate, which is 6, plus c. Right, let's expand that little bracket out. So we get 5 equals now 1/3 times 6. You can treat this in two different ways. You could do a bit of working out for this if you want. If you times a third by 6, remember 6 is 6 over 1, so you can just treat it like normal fractions. You get 6 over 3, and 6 over 3 equals 2. And when you times a fraction by a whole number, it just multiplies the numerator. So 6 times a third is 6/3, and 6/3 is 2. Okay, but you can also just think when it's a fraction times 6, if it's a nice one, a third of 6 or a third times 6 is just 1/3 of 6. So 6 divided by 3 equals 2. So you can do it in two different ways there. Just depends how confident you are with your fractions here. But you can always just treat it in this sense up here. So 6 times a third is 6/3, and simplify it down. And in this case, it does become a whole number. So 5 equals 2 plus c. And then again, if we solve that for c, subtract 2 from both sides, we get 3 equals c, or c equals 3 as our value of c there. There we go, so we've got our y-intercept now. We can put it back into this line equation, and we get y equals 1/3 x plus the 3 there that we've just worked out. Okay, so this question here says that the straight line L1 has equation 4x minus y equals 0, and L2 with the equation 2x plus 3y minus 21 equals 0 intersect at point A. Work out the area of the triangle AOB, where B is the point where L2 meets the axes. So if we were to draw a sketch of this just to imagine what it looks like, which can help with these questions, we could imagine what these graphs are going to look like. Now for the first one, that's quite easy to rearrange. You get y is equal to 4x. So for that first one, y is equal to 4x has a y-intercept of 0, and it has quite a high gradient, so it looks something like this. For the next one, again, we can make that as 3y at the start. We could make it as y equals as well. But if we just move the 2x and the minus 21 over, we'd have that 3y is equal to negative 2x plus 21. Now if we divide it all by 3 and have a think about what that equation would be, we'd have y is equal to negative 2/3 x plus 7. So we could draw that on as well. That has got a negative gradient and it has got a y-intercept of 7. Now it's not very steep, but it is negative 2/3, so it would maybe look something like this. And again, this is just a sketch, and again the y-intercept there would be 7, and it was 0 down here. So you can actually see the triangle that we're looking at. We've got our point B over here that we need to find. We have our point A here where they intersect, and then you can see the triangle AOB is just here, that is created via all these lines in the x-axis. So if we're going to go about working this out, first of all we want to find that point A. So the first thing that I would do is I would rearrange that first equation, which we've already done, and we have got y is equal to 4x. Now we know what y is equal to, we can substitute it into the other equation, rather than setting them equal to each other, which you could also do as well, but we can also just sub it into the other equation. So if we sub it into that first equation that we have over there, if y is equal to 4x, then 2x plus 3 lots of 4x minus 21 is equal to 0. And now we've got an equation that just has x in it that we just need to solve. 2x, and this is going to equal 12x, so that would be 14x, which is equal to, and add the 21 to the other side, 14x is equal to 21. We can now solve that by dividing by 14, and we get x is equal to 1.5, or you could leave that as 3/2. So we've got our x coordinate of where they intersect, and obviously the equation there is y equals 4x. So y is going to equal 4 lots of 1.5, so y is equal to 4 times 1.5, and that is y is equal to 6. So we have our coordinate where the points intersect, and that coordinate is 1.5 and 6. And there we go, that is the first part of this question. We now know the height of the triangle. As the y coordinate there is 6, the height of that triangle must be 6. Now we just need to know the length of the base. So we need to know the coordinate of B, and once we've got the coordinate of B, we can just do the area of a triangle. So moving on to the next stage here, we're going to work out the coordinates of B. Now of course, to work out the coordinates of B, all we actually need to do here is find the x coordinate, as we already know that the y coordinate is 0. So if we think about the line equation that line is meeting down here, the line equation was that second one. So if we're going to substitute in a value, we can just substitute y equals 0. So if we do that, we get 2x plus 3 lots of 0. And again, that'd just be 0, so we don't even need to write that. You can do if you want, but we could just leave it as that becomes 0. We're just going to get 2x minus 21 is equal to 0. Again, I'm just going to write here y equals 0, so you know that that's where that y piece has disappeared. We can add 21 to both sides, so 2x is equal to 21, and then dividing by 2, x is going to equal 10.5, or of course you could leave that as 21/2. So the x coordinate at that point B, we've got x is equal to 10.5, which means that from 0 to 10.5, the base of our triangle is going to be 10.5. So we've got all the pieces that we need to finish this off. An area of a triangle is half base times height. So we would just do, for area, half times 10.5 and multiply that by the height, which is 6. And if we type that into our calculator, it gives us a value as a fraction, 63/2, or of course you could write that as a decimal, and there we go, we don't need to give any units as we are looking at the area problem on a coordinate grid. So our final answer would just be 63/2, and there we go, that is the final answer for this one. Okay, so when we're modelling with straight line graphs, we just need to take the coordinates from the context of the question. So this question here says that a container is leaking with water at a constant rate. The water remaining is recorded at certain intervals. It says at the start, so we'll highlight that, the depth was 19.1, and after 100 seconds, the depth was 6.1. So you can see it's going down over time, and it says deduce an equation in the form d equals at plus b, and interpret the meaning of the coefficients of a and b. So d in this case is our depth, and t is our time, and we're going to make an equation using those. So d equals at plus b. So in order to do this, we obviously need to get the gradient between those points. So if we are looking at the points, bearing in mind the start time there, s will equal 0. Or we could write that as t equals 0 as we are using t, so we'll have t is equal to 0. We've also got t is equal to 100 seconds here, and then we have our other numbers, so we have the depth here is equal to 19.1, and we have the depth over here is equal to 6.1. Now if we were to draw a little sketch of this, we could imagine what it looks like, and maybe we would have our depth going up the top, which would be the most logical, and time down the bottom. So the depth starts at 19.1, which we could draw up here, and then it is going to go down over time to the point where it's empty. So if we think about doing this, to get our gradient, we're going to do y2 minus y1 over x2 minus x1. So our y coordinates here will be the depth, so we will do, and we can pick the 19.1 if we wanted to start, but we'll go with our second coordinate there, which is 6.1, so we'll have 6.1 take away 19.1, and that's going to be divided by the x coordinate, the second one, which is 100, so that'd be 100 take away 0. Now on the top there, that comes out as 13 or negative 13, and on the bottom we have 100. So we can simplify that, or we could just type it into our calculator, and that comes out as negative 0.13. So there we go, we have our gradient. Now we can put that into our line equation, and again we can use our other coordinates, but we know that our gradient is going to be minus 0.13 t. So in order to write our equation, we could substitute our coordinates into our line equation, or for this particular question, we can actually get our y-intercept from the graph. And you can see here that at 0 seconds, it started at 19.1. So if we're going to write our line equation, we may as well just take the coordinate from there and write y is equal to, and in fact, we should keep our letters the same as the question has said, because it does say to give it as d is equal to. So we would say that the depth is equal to minus 0.13 t plus the 19.1. So there is our linear equation, and there we go, and we've given it in the format that we've been asked. Now it does say to interpret the meaning of the coefficients. So if we look at the coefficients, we have the minus 0.13 in place of a. Now that is representing the change in the depth of the water every second, as we know it's in seconds. So we could write that down, the change in depth, we could say per second. There we go, the change in depth per second. And we have our y-intercept at the end in place of b, and that is the depth at the start. Okay, as given to us in the question. So depth at the start. So there we go, that is part A. Now part B has asked us something else. It says use the model to find the time when the container will be empty. Or in other words, we want to know when d is equal to 0. So for part B, if we just put 0 in place of d, then we've got an equation that we can solve. So if we say that 0 is equal to minus 0.13t plus 19.1, We just need to solve that. Now the easiest way to solve that would be to add the minus 0.13t to the other side. So we would have positive 0.13t, which is equal to 19.1. And then we would just divide both sides by 0.13, and we get a final answer which will give us our time, and that time comes out as 146.9. So 146.9, and that is in seconds. So we would just write seconds at the end of that, 146.9 seconds. And there we go, that would be our final answer for finding the time when the depth is going to be 0, or in other words, when the container is empty. Okay, so when looking at midpoints and perpendicular bisectors, this is quite a common type of question. So it says the line segment AB is the diameter of a circle centre C, where A is -1,4 and B is 5,2. It says the line L passes through C and is perpendicular to the line AB, which is the diameter. Find the equation of line L. So we want to find the perpendicular bisector of this diameter. And obviously the perpendicular bisector is going to be perpendicular, so we have all our stuff to do with perpendicular gradients. So if we start by finding the midpoint of these two, we might be able to draw a little sketch of this a little bit better. So to find the midpoint, you take the coordinates and add them together and divide it by 2. So if we focus first on the x-coordinate, to get the midpoint of the x-coordinate, we would do 5 plus -1, the two x-coordinates, and divide that by 2. And the other coordinate would be 2 plus 4, and again dividing that by 2. So for that particular coordinate there, 5 add -1 is 4, divided by 2 is 2, and 2 plus 4 is 6, divided by 2 is 3. So we could probably draw an okay sort of sketch and think about what this looks like. So A is -1,4, so -1,4, let's just imagine that's here. And then our coordinate in the centre is 2, 3, so that is to the right obviously, and just a little bit lower than the 4. And then we've got another coordinate which is 5, 2, which is to the right again, and just a little bit lower. So it's going to look something like this. Now obviously you're not going to be able to draw a perfect sketch of this, but you can just have something to help you visualise it. So if we imagine it looks something like that, although that wasn't very good as my centre doesn't look fantastic, so you can always get rid of these coordinates and just put them back on so it suits your diagram. So let's say it's there, there, and there. So now we have the coordinates of the centre. So we could also draw in this line AB, and let's label that up. So that would be A, and this would be B, and we have our centre point there, and we are going to find the perpendicular bisector. So if we if we draw that in and imagine what it looks like, it's going to look something like that. And it'd probably be also worthwhile labelling on that centre point 2, 3. So how do we go about finding a perpendicular line? Well, first of all, we want to find the gradient. So if we find the gradient of AB, well, then we can go about doing that to start with. So for finding the gradient, y2 minus y1, so that is going to be the y-coordinate of B, take away the y-coordinate of A, over the x-coordinate of B, which is 5, take away -1, the x-coordinate of A. So that comes out as -2 over 6, which is -1/3. So our gradient of AB is -1/3. Which means our perpendicular gradient is going to be our negative reciprocal, and that comes out as +3. So that is the first thing we need, that is the gradient of our perpendicular bisector here. So now we can use our line equation, so y minus y1 equals mx minus x1. And it is going to have to pass through that coordinate through the centre, which we can see here, 2 and 3. So we would have y minus the y-coordinate of 3 is equal to m, which is 3, I was about to draw the bracket, let's get rid of that, equals 3 lots of x minus the x-coordinate, which is 2. So if we expand that out, we get y minus 3 is equal to 3x minus 6. And then of course, to finish this off, we want it just to say y equals, so add 3 to both sides. There we go. And we get y is equal to 3x minus 3. And that is the final line equation, and that is the equation of our perpendicular bisector passing through the midpoint of AB. In terms of actually the equation of the circle, I'm always just going to write that down. So I've got x minus a, which is the first coordinate, or the x coordinate within the centre, squared. Add to that y minus b, which is obviously the y coordinate of the centre, squared, and that's going to equal the radius squared. So if we plug these numbers in that we've been given, 3 and 1, let's just put them into the equation. Let's see what we get. So there we go. We've got x minus 3 squared, add y minus 1 squared, and that is equal to the radius squared. Now I'm going to do this in two different ways. So if you've seen this before, you might have only used one of the ways, so I'm going to show you both. But in terms of what we'd have done at GCSE, maybe at this point, we'd have imagined these two coordinates. Okay, so if I imagine the point 3, 1, which is the centre, it does always help if you can draw a little diagram of these, but if we imagine 3, 1's the centre, and then negative 2, 5, let's just have a little think, it probably looks something like this. There we go. And negative 2, 5 is somewhere over here. Let's have a think. Negative 2, 5 is maybe over there somewhere. There we go. But in terms of looking at these 2 points, we would find the length of the radius by using Pythagoras, like we've just talked about, and we would look at the base, or the rise and the run there, or the change in x and the change in y, and then we just use Pythagoras to work out the radius. So in terms of the base length, it goes from negative 2 on the left there over to 3, which is a length of 5, and going up it goes from 1 up to 5, which is a length of 4. So you can use Pythagoras to work out the length of the radius there, and we can just do that quite nice and easy. We can do 4 squared plus 5 squared, which is 16 plus 25, which is 41. And then you can just square root that for the radius. So r equals the square root of 41. There we go. But obviously we want to know what the radius squared is. So when it's in a nice little square root like that, we can just take away the square root and it'd be 41. So we could finish off our equation here. It'd be x minus 3 squared plus y minus 1 squared equals the radius squared. The radius is root 41, so 41. So it says the circle C has equation, and then we have the equation here in lots of pieces. We've got x squareds, y squared, x, y's, and a number, and it all equals 0. It says find the coordinates of the centre of C and the radius of C. And then we've got another question here that says find the coordinates of the points where C crosses the y-axis. So we'll have a look at that in a sec, but this actual equation here has to be rearranged in order for us to get it into the format that we want. Obviously we know what the format looks like. We've got x minus a in brackets squared, and then we've got y minus b in brackets squared, and that equals r squared. So we have to rearrange this. We need to get all those numbers on the right hand side, and then we need to get these x parts into brackets. And if you hopefully recognise this, you should recognise that this looks very similar to completed square form, and this is where we're going to use a bit of completing the square to get it into this format. Now if we have a look at the pieces that we have in our equation, we've got some x pieces here. We've got, and I'll highlight this in that colour there, we've got the x squared and we've got a minus 6x. Now if we just forget about everything else there and we group those together, we'll have x squared minus 6x. Okay, now if we were to complete the square on that, okay, just on that part there, we would obviously halve the coefficient of x, so it would be x minus 3 in brackets squared. And obviously if you're not sure on completing the square, don't forget I've linked that in the description below, so check that out first. And then obviously we need to get that back to 0 because there's no number after this. So to get that back to 0, thinking about what that would expand to, well, negative 3 times negative 3 would give us positive 9. So I'd also have to take away 9, and that obviously that expression there would give us x squared minus 6x. So that's just writing that in completed square form. We also have the y pieces. Now if we have a look at the y pieces in there, let's just highlight those. We've got y squared and a plus 2y. Now if I put those in, we've got, so I'll put a plus here as well, we've got y squared plus 2y. Now if I complete the square just on that, and let's keep the plus there as well, we would halve the coefficient of y, so I'd get y plus 1. There we go, in brackets squared. And when we expand that, that gives us plus 1, so we have to take that 1 away to make it balance to the expression above, the y squared plus 2y, and that would obviously complete the square on that part. So far, what we've done, we've completed the square there, that's given us the little bit below, and we completed the square for the x parts there, again for that bit below as well. Then we've still got that minus 15, so I need to bring that minus 15 back in. There we go, and it all equals 0. So let's add the minus 15 in. There we go, and that all equals 0. Now if we have a look at just the numbers that we've got there, we've got a minus 9, a minus 1 and a minus 15. Now if I group those all together, and I'll probably skip a few steps on the next question here, but if I group all the numbers together and I'll put them all at the end, let's see what we've got. We've got x minus 3 in brackets squared
plus the y plus 1 in brackets squared. And then all of those numbers, so we've got minus 9, minus 1, that's minus 10, minus another 15 is minus 25. There we go, and that all equals 0. And obviously, just to finish this off, we just need to move that 25 over to the other side, and that'll get it into the equation of a circle, the format that we've looked at throughout the video. So if we plus 25 to the other side, just to finish this off, and then we can get the centre and the radius from that. So we've got x minus 3 in brackets squared, plus y plus 1 in brackets squared, and that equals 25. Now from there we can get the coordinates of the centre, and we can also get the radius. Now the easiest part there, well, I think they're both relatively simple once you've got to this point, but it's nice and easy just to square root this number at the end to get the radius. So we know that the radius is going to equal the square root of 25, as that is r squared at the end, equals the square root of 25, and in this case that becomes a whole number, that becomes 5. Okay, obviously the square root of a number is positive and negative, but we can't have a negative radius, so it's just going to be 5 there for the length of the radius. Now in terms of actually getting the equation of the coordinates for the centre, now obviously we know it's minus a and minus b on these parts here. So a is going to have to be that 3 right there, so the centre. And there we go. We know it's going to be 3, we've taken away 3, and on this one here we just need to be a little bit more careful because we've got a plus 1 there, so we must have taken away negative 1 in order for it to turn into positive 1. And there we go, that's our radius and our centre taken from that equation. Okay, so there's our two key parts for part A. We've got our radius, which is 5, and our centre, which is 3 and minus 1. Just need to be careful there when there is a positive number in the bracket like the y plus 1, that you remember therefore it must have been negative 1 that we took away in order for it to become positive. Now the second part here says find the coordinates of the points where C crosses the y-axis. Now in terms of actually thinking about this logically, in terms of a coordinate graph, if we had a circle, let's think about what this would look like. Let's have a think. The centre is at 3 minus 1, which is somewhere there. And if I was to draw a circle in, which I always don't really like doing on the screen here because it's not the easiest to draw, but it would look something, and it's a really rubbish circle, but there we go. It looks something like that if I was to draw a basic sketch. Let's get rid of that centre point because that really does not make it look good. There we go. Let's imagine the centre. There we go. 3 minus 1. Not to scale, but there we go. We have these two coordinate points where it crosses through the axes, so here and here. Now the logical thing about this question is that any point on the y-axis there, the x coordinate down here is always going to be 0. So effectively, if we want to know what the y coordinates are, where it crosses through the y-axis, all we have to do is sub in x equals 0. So let's get rid of that sketch there because it's a little bit of an embarrassing sketch. There we go. But just to give you a sort of an idea as to what we're actually looking at, we're looking at when x equals 0. So if I sub that into my equation, and my equation's there, I just want to know what does it equal when x equals 0. Let's put that in. So when x equals 0, what do we get? And I'm subbing it into this equation just here. So we get 0 minus 3 in the first bracket, so we get negative 3 squared, plus, we don't know the y coordinates, so we've got y plus 1 squared, and that equals 25. So we just need to rearrange this. Now negative 3 squared is 9, so actually I could just think that that's 9 there. And if I take away 9 from both sides, we get y plus 1 in brackets squared equals 16 when you take away that 9. Now if I square root both sides, obviously we want to get y, find out what y is. So square root both sides, we get y plus 1 equals this plus and minus the square root of 16, so it could be plus and minus 4. And obviously then we just need to take away 1 from both sides, and we get y equals minus 1 plus and minus 4. And that there will give us two values, okay, because you could have negative 1 add 4, so y could equal 3, or we could have negative 1 take away 4, which would equal negative 5. So we've got 3 or minus 5 in terms of where it crosses the y-axis. They are the two coordinates there. So obviously you could draw a bit more of an accurate sketch now you know where it crosses through the y-axis. But there we go, that's how we're going to go about solving these two parts of the question.
So for this question, looking at intersecting circles with lines, it says show that the line x minus y minus 10 equals 0 does not intersect with the circle, and then we have our circle equation. So we've got our two pieces, and obviously the process to solve this will be using simultaneous equations. So although we looked at quadratic simultaneous equations before, this question is slightly different as it says this fact here does not intersect. And obviously in this relation we are actually looking at the actual circle. So the process to do this is substituting that first equation in, so we want to make that x or y equals. Now look at your circle equation, because there are two x's in that equation, but there's only this one y squared piece. So it would be easier for us if we can make it say y equals. So if we take our first equation and add y to the other side, we get x minus 10, which is equal to y. Of course you could write that as y equals x minus 10. So if we take that and substitute it into our circle equation, just put in a bracket around x minus 10, when we substitute that in, we get x squared minus 4x plus, and then we have our x minus 10, which is going to be squared, and that is equal to 21. So now we have an equation that is going to be a quadratic that we're going to need to make equal to 0, and then to show that it doesn't intersect, we're going to have to show that it has no real roots. So having a look at this then, let's first expand that double bracket, and obviously if you are quick at expanding your double brackets, you can obviously just write the answer to that, which is x squared minus 20x plus 100. So if we write that all out and simplify it, we've got 2x squared, so 2x squared. We've got a minus 4x minus 20x, which is going to be minus 24x. We have a plus 100 at the end, but we're also going to have to minus this 21 to make sure it equals 0. So we can simplify that straight away, which is 100 take away 21, which is going to be plus 79. And that is now equal to 0. Now obviously if they did intersect, at this point we would want to solve this equation. We would want to find our x coordinates, and then we would substitute them back in to find our y coordinates. But this says does not intersect, so we will look at the discriminant. So for the discriminant we are going to look at b squared minus 4ac, and then identify our a, b and c. So a is 2, b is negative 24, and c is 79. And again, it's always worth writing them down. A is equal to 2, b is equal to negative 24, and c is equal to 79. Okay, so putting that into b squared minus 4ac, we are going to have negative 24 squared, and take away 4 times 2 times 79. And if we type that into our calculator, and let's just type that in, we get negative 24 squared minus 4 times 2 times 79, and the answer comes out as minus 56. So we know that when b squared minus 4ac is less than 0, that less than kind of looks a little bit like my c there, but that means it has no real roots. Okay, so because we've got an answer of negative 56, we have no real roots, and therefore these do not intersect. Okay, so when looking at tangents to circles, we just need to remember that the tangent is going to be perpendicular to the radius. So for this question here where it says the point P, which is 1 minus 2, that lies on the circle with a centre 4, 6, and it wants us to find the equation of the tangent to the circle at that point, we can start by finding the gradient of the radius. Now what you can do on a question like this is to draw a little diagram which might help you to visualize it, and that's fine to do as well. It says the center of the circle is 4, 6. If we imagine that that is just there, and there is a point which is across 1 minus 2, let's imagine that's here, and obviously you could draw a sketch of the circle. Again, it doesn't have to be perfect, but it might help you to visualize it. So we are going to find the gradient of this radius that I've just drawn in, and that is between the point 4, 6 and the other coordinate down there, which is 1 minus 2. So obviously you don't need the actual drawing to do that, because we can just use our y2 minus y1 over x2 minus x1. So y2 would be 6 take away minus 2 over 4 take away 1. So 6 take away minus 2 is equal to 8, and 4 take away 1 is equal to 3. So the gradient of the tangent is 8 over 3. That means that the gradient of the gradient of the radius is 8 over 3. Now we are going to find the gradient of the tangent, because the tangent there is going to have a perpendicular gradient. So we are going to find the perpendicular gradient, which is the negative reciprocal, which is going to be negative 3 over 8. Now we can take that and we can put it into the equation of the line, given that we know it passes through the point 1 minus 2. Okay, so putting that into the equation of a line, we will have y minus y1, which is y take away minus 2, which is going to be y plus 2. So y plus 2 is equal to negative 3 over 8 x minus x1, and x1 is 1, so x minus 1. We can now expand that, so we have y plus 2, which is going to be equal to negative 3 over 8x minus 1 times minus 3 over 8 is going to be minus 3 over 8, but it was times a negative, so it'd be plus 3 over 8. Now we can take away 2 from both sides, or what we could do here, just to make that actually a little bit easier for us, is we could just multiply everything by 8 to remove those fractions, and that's fine for us to do. So we would have 8y plus 16 is equal to minus 3x plus 3. That makes it a lot easier for us to rearrange that, and as now we can just minus 16 from both sides, or we could move everything to one particular side, which doesn't really matter. But if we bring this up here, in fact, if we just move everything to the left, then we would have 8y plus 3x when we move that 3x over, and also minus the 3 over would give us plus 13, and that is equal to 0. Of course, you could write this as 8y equals, or you could make it y equals if you wanted. The question might ask you to write it in different ways, but it didn't ask us to write it in a particular way, so just having it equal to 0, 8y plus 3x plus 13 equals 0, is probably the easiest way for us to write that answer. Okay, so when it comes to triangles in circles, there's a couple of different methods that you could use. Now you might be asked to find the centre of the circle. Now this particular question says to show that AB is the diameter of the circle. So of course that we could just find the midpoints of the point A and B, but if it wasn't the diameter of the circle and we were wanting to find the centre, then you could actually use the perpendicular bisectors of the chords. So if we looked at the perpendicular bisector of the chord AC, we would find the midpoint and then find the perpendicular line equation, which would go through the circle like this. We could then do the same with CB, finding the midpoint, and again the perpendicular bisector would cross through like this. Now those perpendicular bisectors do cross at the centre of the circle, so if you found the equation of those two lines, you could set them equal to each other. And of course we've already discussed looking at midpoints of lines and perpendicular bisectors, so that additional step there wouldn't be too much work. Now this particular question is slightly different. It's actually telling us to show that AB is the diameter of the circle. Now because that is the diameter, we know via circle theorems that if it is, this angle here must be a right angle, and therefore we could use Pythagoras to show this proof. So in order to use Pythagoras, we would have to find the lengths of these lines, so A to C and C to B. We could then use Pythagoras to show the length that it matches the length of A to B. So if we go about doing that, you can see from A to C, the length there goes from minus 8 to minus 4. Now that is a distance change of 4, so we would do 4 squared, and 1 to 9 is a change of 8. So if we did 4 squared plus 8 squared and square rooted our answer, that comes out as 4 root 5. So the length of that line there is 4 root 5. We can do the same from C to B. Now that goes from minus 4 to 4, which is a change of 8. And 9 to 5 is a change of 4. So 8 squared plus 4 squared for that length, using Pythagoras again, would give us 4 root 5. So that length there has a length of 4 root 5, which matches the length of A to C. So they are our two lengths, and if we do Pythagoras with those two to find the length of the diameter, that should match the length we get when we use this same process. So if we just do the same process using Pythagoras between these 2 points, then for A to B, you can see it goes from minus 8 to 4, which is a change of 12, and it goes from 1 to 5, which is a change of 4, and if we do that using Pythagoras again, we get the length 4 root 10. So that comes out as 4 root 10, and now we can have a look at showing our proof. So they are the definite distances. If this triangle is right angled, then if we were to square both of these sides and square root the answer, it would have to match the length of the diameter. So if we go about doing that, 4 root 5 in brackets squared plus another 4 root 5 in brackets squared, and if we square root all of that and we type that into our calculator, we get the answer 4 root 10. So as you can see, it has matched the length of the diameter, therefore it is definitely a right-angled triangle, and therefore thinking about circle theorems, angles made in a semicircle form that right angle, that 90-degree angle that we've shown, so it must be a right-angled triangle, and therefore A to B must be the diameter. Okay, so in this question we've got a slightly harder quadratic on the top and a different sort of quadratic on the bottom. So on the bottom there, hopefully you recognise that it's a difference of two squares. When there's no x piece in the middle there, it's because the numbers are the same and they've cancelled each other out. So if I start with the bottom, I just think it's the easier one there. The factors of 16 that are the same are 4 and 4. So our difference of two squares there is x plus 4 and x minus 4. There we go, and that's that factorised on the bottom. That gives us a little helpful hint for the one on the top there, which is slightly harder, because our factors of 4 are 1 and 4, or 2 and 2. Now because we've got that little hint here that we know we're going to have a 4 if it's going to simplify, we know it's going to be the 1 and the 4, but now we just need to have a look and figure out which way it goes round. So we've got 3x in one bracket and an x in another. That'll allow us to get the 3x squared. Again, obviously, check out my video on factorising these quadratics or harder quadratics if you're unsure on these. But in order to make 11 there, we're going to want the 4 to get multiplied by 3 to make 12. So we want plus 4, that'll make positive 12. And we want to take away 1, so we'll put the minus 1 over here in the other bracket. And again, now we've got it factorised, it's nice and easy for us to cancel off these x plus 4s and just write what we've got left. On the top, we've got 3x minus 1. And on the bottom, we've got x minus 4. And there we go, that is our fraction there, fully simplified. Okay, so we've got f of x equals, and then we have our cubic, and it says use the factor theorem to show that x minus 2 is a factor, which we've just done, and then hence factorise fully the cubic. So let's have a look. So the first bit's nice and easy, we've just looked at that. For that one there, x has to equal 2. So if we sub 2 in, and we'll do this up here, we get 2 cubed minus 9 lots of 2, let's have a look, 9 lots of 2 squared, minus 9 lots of 2 squared, plus 20 lots of 2, and then minus 12. I'm just going to type that into the calculator as I've written it. So 2 cubed, take away 9 lots of 2 squared, let's have a look, plus 20 lots of 2, which is 40, and then take away 12. There we go, and it equals 0 on the calculator. There we are, so that all equals 0. So therefore it must be a factor. Now obviously the new bit that we're going to have a look here is showing that x minus 2 is a factor and using that to factorise it. So now we know that x minus 2 is a factor, we're going to have a look at how we actually get this cubic. So if x minus 2 is a factor, there we go, we'll have a look what must be in the other bracket, and in the other bracket we're going to have the quadratic. Okay, so let's have a look. Now we know we need to get an x cubed up there, so if we need to get an x cubed in this bracket here, we're going to have an x squared. Okay, thinking back to obviously expanding your triple brackets back from GCSE, we know that when we multiply this out, we've got x times the x squared, which gives us the x cubed that we want, and then we've got the negative 2 times the x squared, okay, and that would give us a negative 2x squared. I'm just going to write that down underneath here because at the moment we've got negative 2x squared, but whatever piece we put next in the quadratic is also going to give us an x squared in a second, so we don't have our completed amount of x squareds or coefficients of x squareds just yet. So let's have a think. Now we've got negative 2x squared at the moment, and we need to get to negative 9x squared. Now that means I need an extra negative 7x squared. So next in my bracket there, I'm going to have to put a negative 7x. And that's going to mean that when we expand it now, look, we get x times the negative 7x. That gives me my extra negative 7x squared. And it completes my negative 9x squared. There we go, which is what we're looking for in that cubic. Now on to the next bit, because we also need to do the negative 2 times that negative 7x, and that gives us positive 14x. Now again, I'm going to put that down here, so plus 14x, because we've not quite completed the x part yet. So let's get rid of those and let's have a think about that. Now we need to get to, let's have a look, plus 20x. So we need to get to plus 20x, and at the moment we're at plus 14x, so we need an extra 6. So that means I need to put a plus 6 here, so we'll put plus 6 in. Let's have a look, let's do that back in the other colour. There we are, so we need plus 6 in there, and let's have a look at what that gives us. So that gives me the extra plus 6x that I was looking for. There we are, so we've got that plus 6x, so that gives me the plus 20x in total that we need. And then also we've got the negative 2 times the 6, which gives me the negative 12 at the end. There we go, so that is definitely
factorised at the moment. Okay, obviously we need to factorise this fully though, so we have got another step to go about, and that's because we need to factorise this quadratic here. Okay, so we need to have a look at this one. So obviously thinking about factorising quadratics, and again I'll link the video for that in the description, but we need to factorise this quadratic. So for 6 we can have 1 and 6, or we could have 2 and 3. And in order to factorise that, let's have a think. We need -7 in the middle and 6 at the end, so that's -6 and -1. So that bracket there is going to factorise into -6, -1. So x minus 6 and x minus 1. There we go. Right, okay, so obviously we haven't quite finished. Well, we just need to actually write the final answer. So obviously we've got our first bracket up here, x minus 2. So we've got x minus 2. And then our two brackets here that we've just got for that quadratic, x minus 6 and x minus 1. There we go. And there that is fully factorised into our three brackets. And that is how we go about using the factor theorem. Okay, so this question says the equation x squared plus k minus 3 in brackets x minus 4k equals 0, and it has two distinct real roots. Show that k satisfies this inequality and hence find the set of possible values for k. Now obviously the little hint here on the topic we're going to have to use is when it says has two distinct real roots. Obviously when we're looking at distinct real roots or roots at all, we're looking at the discriminant. Okay, so when we're looking at this, we need to figure out what the discriminant is, which is b squared minus 4ac. And if it says it has two distinct real roots, we know that b squared minus 4ac is going to be bigger than 0. Okay, and that's what that means there. We're going to set that bigger than 0. So if we actually plug these values in and see what we have. So a is our value in front of x squared, so a equals 1. B is our value in front of x, which in this case is a bracket. We've got k minus 3. And c is our value at the end, so c is negative 4. Now if I plug these all into b squared minus 4ac, let's see what we get. So b squared is going to be our k minus 3 squared. So I've got k minus 3 in brackets squared. Take away 4 times 1 times negative 4k. Well, 4, let's just write that down. 4 times 1 times minus 4k is going to equal negative 16k. But we are taking that away, so if we're taking away negative 16k, that's going to become plus 16k. So plus 16k is bigger than 0. Obviously we just need to expand that bracket there, so I'm not going to write it all out, I'm just going to expand it as it is. So k times k will give us k squared. We've got negative 3k and we've got two of those, so minus 6k. And then plus 9. And then we've got that plus that 16k at the end there, and that's all bigger than 0. And then obviously we've got two pieces we can tidy up. We've got the minus 6k, the plus 16k, and if we tidy that all up, we get k squared plus 10k plus 9 is bigger than 0. And there we go, we've got that there, what it was asking for, show that k satisfies this inequality, and there we go, it matches. So all we have to do to finish this off, it says hence find the possible values of k. So basically we're just going to solve that quadratic inequality. And if we go about factorising it to start with, let's think what we get. We've got k in the brackets. There we go, that's bigger than 0. And obviously the factors of 9 there, we can have 1 and 9, or we could have 3 and 3. If we want 10 in the middle, 1 and 9 is going to work, so k plus 1 and k plus 9. So our two solutions, we've got k equals negative 1 and k equals negative 9, and it's asking about greater than 0. So again, we could think about this in terms of a quadratic. We've got negative 9, negative 1, so we've got two negative roots there. Let's have a look. Negative 9, negative 1, and we are looking at the bit above 0, so this line and this line. So our two solutions, we've got k has got to be less than minus 9, and k has got to be greater than minus 1. And there we go, there's our two solutions there. They are the set of possible values. K has got to be less than minus 9 and k has got to be greater than negative 1. Okay, so looking at some algebraic proof. Now it says here, given that n is a natural number, which means that it's going to be positive and then it's going to be odd or even, prove that n cubed plus 2 is not divisible by 8. So what we're going to have a look at is we are going to substitute in an even number and an odd number, and if we can prove that neither of them are divisible by 8, then that would prove that given our restraints here,
it is not divisible by 8. So given that n is already in the question, rather than using n for my proof, I'm going to say that an even number is 2x, and I'm going to say an odd number is 2x plus 1. So what I'm going to do is I'm going to substitute them in separately into n cubed plus 2, and hopefully we will show that neither of them are divisible by 8. So it doesn't matter which one we start with. I'm just going to start with our even number, as it's probably a little bit easier to substitute in, and let's just see what we get. So for an even number, and we'll just highlight that we're doing an even number here, we would substitute that in, and that would be 2x in brackets cubed plus 2. That's easy enough for us to do because 2 cubed is going to equal 8, so that is going to be 8x cubed plus 2. Now for that particular question there, obviously if we were showing it was divisible by 8, we would want to factorise it by 8. And if you look for this particular one, the only way to factorise it by 8 would be to put 8 outside of the x cubed, and then we would have always the plus 2 at the end. So therefore, an even number is going to be always 2 more than a multiple of 8. And we'll write that down, 2 more than a multiple of 8. There we go. And we are now going to move on to an odd number. So there we go, we have disproved that an even number works. If we can also disprove the odd number, then that is going to finish off this question, and we would have disproved that, given these restraints that it has to be a natural number, that it could be divisible by 8. So if we move on to the odd number, which is going to be a little bit longer for us to work out, as we're going to have a triple bracket, if we substitute that in, we're going to have 2x plus 1, and that is going to be cubed, and then we're going to have plus 2 at the end. So we'll start by expanding a double bracket. So if we do 2x plus 1 and we do that squared, again you could write your double bracket out, but that is going to be equal to 4x squared plus 2x, so plus 4x plus 1. We now need to expand that by the final 2x plus 1. So if we do that as well, times that by another 2x plus 1. So if we do 4x squared times the 2x, that gives us 8x cubed. 4x squared times the 1 is 4x squared. Moving on to the 4x, times that by 2x is 8x squared, times by the 1 is 4x, and then onto the 1 times 2x gives us 2x, and 1 times 1 gives us 1. Now of course all of that also has, not forgetting, the plus 2 at the end, so it's up to you when you add that in. You could simplify this, but we don't want to forget to put the plus 2 at the end, so we may as well just put that in now. If we simplify all of that, we have 8x cubed. If we join together the x squareds there, we have 12x squared, and adding together the x's, we have plus 6x, and the 1 and the 2 makes 3. So looking at that, we can't actually factorise it. We could actually take out a factor of 2, but obviously not out of the full piece. We would always have that plus 3 at the end. Of course, you could actually split the 3 into 2 and 1, but we don't really necessarily need to. I mean, we could obviously change the plus 3 into plus 2 plus 1, just so that we can factorise it with the plus 1 remainder, but again, it doesn't actually matter either way. We could factorise it here, which would be 2 lots of 4x squared plus, 4x cubed, didn't write that 3 very well, plus 6x squared plus 3x, and then you could have the plus 1 there, but again, we're going to have this plus 1 on the outside. So for this particular question, this is always going to be an odd number, as we have the plus 1 at the end. So for this one here, obviously it's going to be a multiple of 2. We could write therefore, this is going to be always an odd number, as we are adding 1 to an even number, and therefore not divisible by 8.
So there we go. What we've actually done is we have subbed in an even number and we have subbed in an odd number. We have our proof here that this is always going to be 2 more than a multiple of 8 for an even number, and for an odd number it's always going to be an odd number and therefore not divisible by 8. And we have shown our proof for this particular question. Okay, so when we're looking at binomial expansion, essentially, if we're thinking about from GCSE level where we've looked at expanding and simplifying a triple bracket, we're going to look at sort of how this all sort of interlinks with then higher powers when we have sort of a bracket to the power of 5 or to the power of 8, and how we go about finding those powers using this process. Now when it comes to binomial expansion, it's all sort of interlinked with sort of the separate powers when we've looked at brackets. Now if we think about sort of a nice easy one, something like x plus 5 in brackets squared, we get a certain pattern that sort of comes out of these, and when we expand one of these we get the x squared, we get that first piece there is always to that power of 2, then we get the 2 in the middle, we get plus 5x, and we always get these 2 there, and then you get that 5 at the end which is squared as well to make 25. And then obviously those 2 in the middle are added together, but we get this sort of little pattern, and it's all linked to Pascal's triangle. And Pascal's triangle is nice and easy to draw. We get a 1 at the top, then you add together the numbers either side of it to get the ones below, and obviously 1 at the top's got a 0 either side, so we just have 1 and 1 below that. But then when we add these together we get 1 on the left, those 2 1s add to make 2 in the middle, and then we get 1 on the end, and we can just keep following this process and making this pattern, so always 1 on the outside, then the 1 and 2 above this next one makes 3, 2 and 1 makes 3, and 1, and we can keep on going, 1, 3 and 1 makes 4, 3 and 3 makes 6, 3 and 1 makes 4 again, and then 1 at the end, and we can keep on going basically with this. Now when it comes to this double bracket that I've drawn here, that is this row here, so 1, 2, 1. So we get 1 of the pieces at the start, the x squared, we get the 2 pieces in the middle, okay, which we've obviously just shown there, we get the 2 in the middle, and then we get the 1 at the end, and following that little pattern of 1, 2, 1. Now if I come away from that and we have a look at this triple bracket, which is what we're going to have a look at to start with, that is obviously linked to the next row down. Now that next row down is 1, 3, 3, 1. Now it's not as easy to spot the pattern with this one, but obviously if we were to expand this all and have a look at all the pieces, we would see we get the 1 at the start, we always get an x cubed at the start, we get the 1 number at the end, which is going to be that 3 cubed, which we'll have a look in a sec, and we get these 2 lots of the 3 pieces in the middle, and we're going to have a look at those now. So if we have a little think, when we were to expand this at GCSE, obviously what we would do is we'd expand 2 brackets to start with. So we'd do x plus 3, and we're going to fully expand this. I'm going to do it nice and quick though. And x plus 3, we'd expand that, which gives us x squared plus 6x plus 9. And then we expand that by another x plus 3. There we go. And we do that, and we expand this all out. We get the x squared times x gives us x cubed. The x squared times the 3 gives us 3x squared, and then we go on to the 6x, and we just keep following this process. So 6x times x is 6x squared, the 6x times the 3 is 18x, 9 times x is 9x, and 9 times 3 is 27. Okay, and we simplify this all down, so eventually we get x cubed plus, and we've got those 2 lots of the x squareds there, which gives us 9x squared. The 18x and 9x gives us 27x. There we go, plus the 27. And we end up with these 4 pieces here. And as you can see in that line, we've got those 4 pieces. Now it's not quite as clear with the triple bracket here, or with the bracket to the power of 3, as to how we got those 2 lots of 3 in the middle. But essentially we kind of got, and let's have a look, we got the x squared here, 1, 2, 3 pieces of x squared. And we also got 3 pieces of x. We've got the 18x, the 9x, the 6x. And then obviously we've got the numbers on either end as well. We've got the x cubed and the 27. So you can kind of see where this pattern comes from. You've got the 1 lot of the x cubed, the 1 lot of the number at the end, and then the 3 of each piece coming in the middle there. Obviously eventually we got to x cubed plus 9x squared plus 27x plus 27, but we're going to have a look at how we can actually get to that using binomial expansion and using this process within Pascal's triangle. Now obviously we don't want to have to always draw this triangle out every time, and thankfully there's a nice little button that we can use to get that on the calculator. And if you have your calculator, this is a calculator topic, it's a button that looks like this, and it tends to be that you've got to press shift to get there first, but it says NCR. It's normally behind the divide button, so you still normally have to press Shift Divide, and it gives you this NCR. Now, in order to get these numbers here, which was what we're going to use for the first one, we have to press, obviously it's a power of 3, so we press 3, Shift, that NCR button, and you'll get a C, and then we press 0 for the first one, so 3C 0, and that always gives us a value of 1. We always get that 1 for the first one, which is just there. Now for the next one, we press 3 again, 3, C1, and we get 3C1, and that gives us 3. Then we do it again, so swap the 1, but I go for 2 this time, so 3C2, and that gives us, let's just have a look, we get 3 again. And then for the last one, we're going to do 3C3, which gives us 1. So make sure you know what that button is in your calculator. It's normally just behind the divide. So 3, Shift NCR, and then whatever number we're looking for. We start with 0, and then 1, 2, 3 for those next ones. So we can actually find out what the pattern's going to be just using this button on our calculator. I'm going to be using that throughout the video, so this is going to be a very important little button. I'm going to be using that every question, and I'm mentioning that as we go. But as I said, you've got to press Shift first to get there. So let's have a look at how we can actually use that on this question, making sure that we can obviously expand this triple bracket using binomial expansion before we start looking at higher powers. So if we get rid of this, obviously we can get rid of all of this. We know what answer we're trying to get to, and that's this one here, x cubed plus 9x squared plus 27x plus 27. Okay, so we obviously know that from GCSE level that that's going to be the answer. And let's look at using binomial expansion to get there. So once we've got the pattern then, and we've got NC0 is 1, and we've got 1, 3, 3, and 1, and that's going to be our pattern. Now all we do is we look at the two pieces within our bracket. So we have an x as the first one, and a 3 as the second one. Okay, and let's just actually just highlight that in different colours. We've got an x, and we have a 3. So that first piece, that 1 there, the x, is obviously the first piece in our pattern, and we have one of those. So we have one lot of, and that's going to be x, and everything here is going to have to be up to a power of 3, so that's going to be x to the power of 3, and we have one of those. So all of these little pieces we're going to write now, we need to make sure there's always a power of 3 in all of them. Now the next one, we're going to have 3 lots of this next piece, so we're going to add to that 3 lots of, and the next piece is ever so slightly different. Now x, the first one, we're going to drop down that power now because we only have one of those x cubes in there. So that x piece is now going to go down to a power of 2. So 1x to the power of 2. But we need to make sure we balance out these powers, and the next piece that we're going to throw in there is that 3. So we have then a 3, and that's going to be to the power of 1. Not that we need to write the power of 1 there. Okay, so all we're going to do is reduce that first piece, which in this case is x, so that's gone down to a power of 2, and introduce that next piece in the bracket, which is a 3. And we're just going to swap these round now, so the x is going to keep reducing, and that number, the 3, is going to keep going up in powers until we get to a power of 3 for that one as well. So the next one, and again we've got 3 lots of this next piece, so we're going to add to that 3 lots of, and we have x to the power of 1 this time, that's going down to the power of 1, and that 3 is going to go up to a power of 2. There we go, that's our third piece in that pattern done. And then on to the last piece, we have one of these, so we're going to add to this 1 of, now x is going to go down to the power of 0, so that's gone, and we just have this 3 at the end, which again has to balance out to that power of 3, so 1 lot of 3 cubed. And if we expand these all out and see what we get, 1 lot of x cubed is x cubed. There we go. Then we're going to have 3 lots of x squared times 3. Well, let's just do the 3 times the 3 to start with, which is 9. So that's 9 lots of, and then we've got x squared with that, so 9 lots of x squared. Then for the next piece, let's have a look. We've got 3 lots of 3 squared. 3 squared is 9. 3 times 3 squared, so 3 times 9 is 27. Again with that x to the power of 1, so plus 27x. And then at the end there we have 1 lot of 3 cubed. 3 cubed is 27. So plus 27 at the end. And there we go, that matches obviously what we got from expanding our triple bracket at the top. We've got x cubed plus 9x squared plus 27x plus 27. So that's all we're going to do for binomial expansion. Obviously it gets a little bit more complicated as we start to go further down Pascal's triangle and start to get larger numbers involved. But basically that's all we're going to do. We're just going to write down what the numbers are obviously in that line of Pascal's triangle that we're going to be looking at. And obviously just balancing that out with our powers sort of moving through. But let's have a look at another one and see how we can apply this to a slightly harder question. Okay, so this question says, find the first four terms in ascending power of x of the binomial expansion of 3 minus a third x to the power of 5, giving each term its simplest form. So let's have a look at this one. Now we've got a power of 5, so before we start dealing with the fractions and having a look at how we're going to deal with that, we'll find the first four terms in the pattern here. So we'll go for 5c0, 5c1, 5c2 and 5c3 and just work out what that pattern actually is. Now obviously we know the first one's 1, so we go for 5c1, which is 5. The next one, 5c2, is 10, and the next one, 5c3, is also 10. There we go. So that's how many lots of this pattern we're going to have. Now this time the first piece in our pattern is a 3, that's okay, and the second piece in our pattern is negative a third x. Now obviously that's okay as well, but we're just going to have to be careful when we're typing this into the calculator. Another way that you could write this here is you could write negative x over 3, so you could leave it as that as well. I might actually write it as negative x over 3 instead, just to sort of make the terms a little bit easier to write. But let's go for this then. So we have one lot of the first piece, which is 3 to the power of 5. So we've only got 3 more to do now, and we're going to add to that. We've got 5 lots of for the next piece. Let's just highlight these as we go. So now we're on this 5 lots. So we've got 5 lots of, and we have 3 to the power of 4, and then we've got this negative x over 3 as well. So negative x over 3. There we go. On to the next piece. Again, so we have 10 lots of this one. So we've got 10 lots of. So we've got 10 lots of, and we've got 3 getting down to the power of 3. And then we've got this negative x over 3, which is now being squared. There we go. And then for our last piece here, again, we've got 10 lots of this. So we have 10 lots of 3 now going down to a power of 2. And we've got the negative x over 3, which is now going to be cubed. Right, so let's deal with all these pieces. The first one's okay. We've got 3 to the power of 5. We can work that out nice and easy. That's 243. So we have 243 as our first one. You can always tick these off as you go, so that's done. The next one, 5 times 3 to the power of 4. Well, let's work that out to start with. That's 405. So 405, and that's going to be multiplied by negative x over 3. We'll come back to that and deal with that in a sec. On to the next one. So we have 10 lots of, so 10 lots of 3 cubed. So we have 3 cubed, which is obviously 27. Times that by 10 is 270. So we have plus 270 lots of, and let's have a look, negative x over 3. Well, if we square that, it's going to become positive. So we're going to get x squared on the top, and on the bottom, 3 squared is 9, so x squared over 9. There we go, and that's that pieced out with. And on to the next one, obviously just being careful with those when you're squaring that, remembering that that's going to make it positive. So we get the x squared on the top, positive x squared, 9 on the bottom. On to the next one, 10 times 3 squared is 90, so we've got 90. And that's going to be, and we've got negative x over 3 cubed. So when we cubed, it's going to stay negative. So we're going to have negative x cubed on the top and 3 cubed, which is 27 on the bottom. There we go, and that's the last piece dealt with. Right, now simplifying all of this then. So we've got 243 at the start, that's all good. And then we've just got to be careful on this next bit. Now negative x over 3, just obviously we could have had the negative a third there. We basically just want to do a third of 405. So if we do a third of 405, we have 405 divided by 3 is 135. And obviously it's negative there, so it's going to be negative 135x. There we go. On to the next piece, we have 9 on the bottom there, so we want to divide that 270 by 9. Obviously it's positive this time, so we'll divide that by 9. 270 divided by 9 is 30, so we get 30x squared. On to the next piece, 90 divided by 27 is not as nice, it gives us a fraction here, and got to be careful because it's negative, so that's not going to be plus there, it's going to be minus. So we get minus 10 over 3, which is what 90 divided by 27 comes out as, with an x cubed. There we go, and that is those first four terms finished. So obviously just be careful on this, because obviously sometimes you can get these fractional pieces, or these fractional coefficients here, and that is quite common on these questions, so you just need to be nice and careful. And obviously just watching out for any pieces here that are negative, like the 2 there, just making sure that you show those with your negatives here as well. When you do have these fractions involved, just remember obviously you're just finding a fraction of that coefficient there. Again, it's just like 405 multiplied by negative a third in terms of actually getting these coefficients. So here we've got the 135, a third of that, and 1/9 of 270 gives us the 30. Obviously our fractional piece at the end as well there. So just being careful, there's the first 4 terms in ascending powers of x, and we've simplified each term. Okay, so this question says find the first 3 terms in ascending power of x of the binomial expansion of 1 plus px to the power of 10. It says where p is a non-zero constant and give each term in its simplest form. So obviously p is an actual number that we're going to find. And obviously it hasn't asked us to find that yet, it's just asking us to find those first 3 terms. In the next part of the process though, or the next part of the question, it says given that in the expansion the coefficient of x squared is 9 times the coefficient of x, find the value of p. So we're going to find that value of p later on in the question. And then it says hence write down the coefficient of x squared, and we're just going to follow this step by step and have a look at how to approach this, and then you've got one to have a go at. So finding the first 3 terms then, we've got a power of 10, and just bearing in mind our first piece is a 1, which is always nice, and our second piece is this plus px. So as we've got a power of 10, we need to do 10c0 to start with. So we've got 10c0, which is 1. We're only finding the first 3 terms, so we've got 1, 10c1 is 10, and then we have 10c2, which is 45. There we go. So that's how many lots of each we're going to have on this particular one here. So for this one then, we've got 1 lot of, and then that's 1 to the power of 10, the first piece. We're going to add to that, we've got 10 lots of, and it's now 1 to the power of 9, and then px as our second piece. And then for the final one, we have 45 lots of, 1 to the power of 8, and then px to the power of 2. There we go. Right, so if we simplify this down then, 1 to the power of 10 gives us 1 for our first piece, 10 times 1 and then times the px gives us 10px, so we have 10px for the second piece, and then for our final piece there, 45 times 1 is 45, and px in brackets squared squares both those letters, so we get p squared x squared. There we go, squaring both of those letters. So 1 plus 10px plus 45p squared x squared. And there's our first 3 terms in ascending powers of x. Now it says, given that in this expansion the coefficient of x squared is 9 times the coefficient of x. Well, the coefficient of x squared, let's have a look and let's highlight that, is 45p squared. That's what's in front of the x squared. And the coefficient of x is 10p. So what it's saying is, okay, if one is 9 times the other, it's saying if we multiply this coefficient here by 9, it would be equal to this coefficient here. Or in other words, 9 times 10p is going to be equal to 45p squared. Or you could do it the other way around. We could do 10p is equal to 45p squared divided by 9. Completely up to you which one you do. Obviously 45 nicely divides by 9, so that would be quite a nice way to do it. But I'm just going to follow this process as I've written it down this way now. It doesn't really matter which way. It's probably easier actually to divide it by 9, because I think we're going to divide it by 9 anyway in a sec, but let's have a look. So if we times that by 9 anyway, we get 90p equals 45p squared. And then we just need to solve that as an equation. So dividing both sides by p would obviously remove the p from the one side, so we'd get 90 equals 45p, just dividing both sides by p there. Then we could divide both sides by 9, or we could actually divide both sides by 15, completely up to you, or we could just divide both sides by 45, and that'll tell us what p is. So if I divide both sides by 45, just write that down, divide by 45, as we've got 45p there, we get 2 equals p, or p equals 2. And there we go, there's our answer for that part. So p equals 2 or 2 equals p. Then it says hence write down the coefficient of x squared. Well, the coefficient of x squared is 45p squared. There we go. And we now know that p is 2, so that's 45 multiplied by 2 squared, which is 45 times 4, and 45 times 4 is 180. And there we go, there's our coefficient of x squared, 180. Right, there we go. So there's our final answer. So in terms of actually what we did there, obviously we had a different piece within our bracket. We had a px, I'm just being careful with that. I think the point where you need to be careful with it is obviously this bit here where we get the p squared x squared. I think other than that, the rest of it was quite nice and simple. And then obviously just reading the wording carefully, it said one coefficient was 9 times the other. So obviously multiplying that by 9 or dividing the other one by 9 there gave us a little equation to solve. We got our value of p and then sub that in to find the coefficient of x squared.
Okay, so when having a look at binomial estimations, we can have questions like this. So it says find the first 4 terms in ascending powers of x of the binomial expansion of, and then we have 1 minus x over 4 to the power of 10, and use your expansion to estimate the value of 0.975, again to the power of 10, giving your answer 3 decimal places. So the first thing we want to do is do our binomial expansion. So for a power of 10, we'll want to use 10c1, which is equal to 1. We're going to want to use 10c2, which is equal to 10, 10c3, which is equal to 45, and then 10c4 for our fourth, which is equal to 120. So putting this into our binomial expansion, our first piece is 1, so we have 1 to the power of 10. Our next piece we're going to have plus 10 lots of, and then we're going to have 1 to the power of 9 plus, multiplied by negative x over 4, and that is to the power of 1. We're now going to move on to our next piece, so plus 45 lots of, 1 drops down to a power of 8, and our negative x over 4 jumps up to a power of 2. And then for our final piece, and it's quite a large question, so let's just try and move some of this out of the way so that we've got enough space there. And for our final piece then, we're going to have 120 lots of, 1 to the power of down to 7, and negative x over 4 is going to go to the power of 3. So we just need to simplify all of this. 1 to the power of 10 at the start is going to stay as 1. Then we have 10 times 1 times the negative 1 on the top there, so that would be 10 over 4. And that is going to come out as 2.5, so it's going to be negative as it is, and let's just highlight that, the negative x over 4. So rather than being a plus, we're going to have a minus, so that'd be minus 2.5, and again you can just type that into your calculator, but minus 2.5x. For the next piece, we have got 45 times 1 times the negative, and obviously we need to expand that bracket as well, so negative x over 4 squared would come out as x squared over, and we can just write this to the side, x squared over 16. So we're going to divide by 16, so 45 divided by 16, and if we type that into our calculator, gives us plus 2.8125, so 2.8125, and that's going to be x squared. And then onto our final piece, x minus x over 4 cubed is going to be negative, and we're going to have x cubed over 4 cubed, which is 64. So we're going to be dividing by 64 on this piece, and it's a negative x cubed at the end there, so it's going to be a minus 120 times 1, and then divided by the 64 gives us negative 1.875, and that is x cubed, and we're only finding the first 4 terms here, but it does continue, so we'll put that it continues there. So that is our binomial expansion, and now we need to go about solving this estimation. So it says in the question here, use your expansion to estimate the value of 0.975 to the power of 10, which matches what's in here. So what we want is that piece in the bracket, the 1 minus x over 4, to be equal to 0.975. So if we set them equal to each other to start with to find out our value of x, and then we can actually sub that into our binomial expansion. So if we set them equal to each other, we get 1 minus x over 4, which has to be equal to, as stated in the question, 0.975. And we just need to go about solving that, and you can do that in 2 ways. We could add the x over 4 to the other side and then subtract the 0.975 from 1, and that leaves us with x over 4, which would be equal to 0.025. Again, multiplying that by 4 then, we would get a value of x, which comes out as 0.1. So x is 0.1. We can now use that to substitute it back into our binomial expansion. So you can write this down, you can write down substitute x equals 0.1 into the expansion, but if we just go about substituting that in, we've got 1 at the start, and again you could write sub x equals 0.1, but 1 minus 0.1 times 2.5 comes out as 0.25. Then sub it into the next part, so 0.1 subbed into x squared gives you 0.01, and then we need to obviously multiply that by 2.8125, and that comes out as 0.028125, and we've got our last piece there, and again you're just typing these all into a calculator. Take away 1.875 multiplied by 0.1 cubed, and that comes out as 0.00, just reading it off the calculator, 1875. There we go. And if we simplify all of that, again just typing it all into the calculator, it comes out as 0.776, quite a lot of decimals here, 0.77625, that comes out as, I've just typed in the 0.975 to the power of 10, which is a lot more decimals. So when we sub that into our binomial expansion, we get 0.77625. Now the question here says giving your answer to 3 decimal places. So if we type in 0.975 to the power of 10 into our calculator, that gives us the answer, and that's where I've got all my decimals from. It comes out as 0.776329. There we go, there are more decimals there, but I'm going to stop there because it only wants it to 3 decimal places. So if we look at these 2 decimals, you can see 0.776 on the top one and 0.776 on the bottom one, and we've got a matching amount of decimal places there, so they round to the same number. So we would give our answer as 0.776 to 3 decimal places. And we've not got much space to write that down, but if we just put it over here to the side, we would just write 0.776 and just put that is to 3 decimal places. And there we go, that would be our final answer for using estimation with binomial expansions. Something a little bit different here, it says calculate the length of QR. Now QR is this length over here, so let's label that. There we go, that's QR. Now at the moment, we don't have the opposite angle. In fact, we don't really have much in this triangle. We have the 14, and that is actually it. But we have got these parallel lines going on, okay? So hopefully we're going to be looking at some parallel line rules here, so something a little bit different. And we have got this right-angled triangle, SPR, on the left there. Now on the right-angled triangle, we've got the length of 8 and an angle. So obviously we can use SOHCAHTOA, or potentially the Sine Rule or something like that, to work out one of the missing lengths. Now this one obviously stands out to me because if we can work that one out, that gives us another length in our little triangle on the right there. So let's think how we could do that. So thinking about some trigonometry again, some SOHCAHTOA, we've got this side here which is our opposite. So we've got the opposite and we're looking for the hypotenuse. So we can definitely use SOHCAHTOA to do this. Again, obviously, if you're using formula triangles, let's have a think, SOH. So if we're looking for the hypotenuse, we're going to do the opposite divided by sine 62. So I can work that out, definitely. Let's call that hypotenuse there. Let's just call it the question mark to be fair. So the question mark is going to equal the opposite, which is 8, divided by sine 62. There we go, so sine 62. So let's type that in, 8 divided by sine 62. And that equals 9.06. Let's have a look. So that equals 9.06. And there's a few more decimals. I'm going to leave it like that. This question doesn't actually say. Let's just go for 2 decimal places. Let's go for that. There we go. We're going to do 2 decimal places. So let's label that on the diagram. So we've got 9.06. And obviously if I'm doing it to 2 decimal places, I should probably keep it a little bit more accurate. So it's 0.6056. There we go. But I'm going to keep the answer on my calculator anyway and use that. Now let's look at this right triangle on the right now. Now I have got 2 sides, but yet I'm still missing the angle opposite the one I'm looking for. So there must be something to do with the parallel lines here. And if we have a look, let's just try and highlight this. We actually do have an alternate angle here. So going along our parallel line, it jumps up to here. Moves along, so we've got an alternate angle there. So this particular angle here is alternate with the 62, so that one is also 62 degrees. And now we have all the information that we need in order to use the cosine rule. So opposite that we've got the little a, so this would be our big A, and then these will be our B and C. Let's have a look, and the one that we've just made there will be our C. So we can type that straight into the cosine rule. Obviously not looking at angles here, but we might be looking at angles potentially. But this one's looking for a side length. So A squared equals B squared, so 14 squared, plus C squared, which isn't that 9.06. And again, I'm going to leave that in my calculator so I can use that in a sec. And that's squared, minus 2 times 14 times C, which is this 9.06 number. 0.06, there we go, and that's going to be cos 62. Right, there we go, so let's try typing this in. So obviously I've left that answer in my calculator, so 14 squared plus answer squared minus 2 times 14 times answer, and then cos 62. Again, you can just write it down and not use the answer button if you want. I just quite like just actually using that. So let's have a look. So let's write what we get here. So A squared equals, press equals, we get 158.9908. There we go, 9908. And there are a few more decimals, but again, we'll leave the answer on my screen. So let's square root that. So our value of A, square root answer, and that leaves us with a final value here of 12.609 with a few more decimals. But if we do have that 2 decimal places for this question, that'd be 12.61. And this is all about centimetres. There we go, so 12.61 centimetres, our final answer. So obviously a lot going on in that question. We had some SOHCAHTOA, which, you know, in a different kind of question, could be looking for an angle, it could be looking for a side length, and then we had to apply some cosine rule, and obviously there was a little bit of parallel lines going on in that one as well, so something a little bit different with a blend of different topics, but just something to be thinking about how you could apply this topic, you know, within a different sort of setting or a different sort of diagram that's not just a plain triangle. Okay, so this question says, work out the size of angle x, give your answer correct to 3 significant figures. Now again, just thinking about the question, look, I know we're finding an angle this time, but look, we have got this pair of opposites here, and also we've got a pair of opposites over here. So if I just label this up just like before, we've got A and big A, and B and big B. Okay, but if I was to plug these into my sine rule, formula like we did before, we'd have 6.7 over sine 95. And that would be equal to 5.4 this time over sine x. Now you can actually use the sine rule like this, and obviously we could actually do quite a bit of rearranging here to get that x on its own. But obviously if what we want to do is we want to get this part on its own, this sine x part, and if we times that to the other side now, it's going to go onto the top of the fraction here, and it's not really going to be on its own in that first step. So there is a really quick step with the sine rule, obviously just to help you with the rearrangement here, and that's just to flip them over. Now the reason we can just flip them over, if we think about a little bit of logic here, if we have 2 fractions that are equal to each other, let's just pick something easy, like 1/2 is equal to 2/4. Now that is a correct statement there. 1/2 is equal to 2/4, and if we flip them over, we get 2 over 1 is equal to 4 over 2. 2 divided by 1 is 2, 4 divided by 2 is 2, and 2 equals 2 is again a correct statement. So you are able to flip fractions over like this when we're equating them to each other. Obviously they equal different things there, but the statement is still correct. They still have to equal each other. So when we're looking for angles, all we're going to do is we're going to flip the fractions over and use the sine rule upside down, so to speak. So we've got sine A over little a is going to equal sine big B over little b. And you're going to see now when we put the numbers in, we get to rearrange this in one step just like we did before. So if we plug all these values in, I've got sine 95 as my big A, and that's over the opposite there, which is 6.7, and that is equal to sine x. I'll put the x in a bracket just like I do with the normal angles, and that is opposite the 5.4. Okay, so now we are actually able to eliminate or isolate the sine x on its own by getting rid of this 5.4 on the bottom. This divide by 5.4. Again, just timesing both sides by 5.4. So when I times this up, and again I'm going to write it in the same way as I did before. So when I times it up to the numerator, look, I'm going to write it just at the start here, and I'll write it down to start with. So that would give me 5.4 sine 95, and that's over 6.7. And that now equals sine x. There we go. So not got the x on its own, but it does equal sine x. Now if I type all of that into the calculator, let's see what we get. So let's type all of that in. So on the top I've got 5.4 sine 95,
and on the bottom I've got 6.7, and if I press equals, let's see what we get. So I get quite a long decimal, so we've got 0.802903, and you know what, we're not going to write it all down, I'm just going to leave it on my calculator screen for the moment, but that is what all of this little bit on the left here equals when I type it all in. Now obviously that equals sine x. It doesn't equal x, it's not our answer, so that equals sine x, and I'll put the x back in a bracket. Now this should hopefully link through to normal trigonometry when we were looking at SOHCAHTOA. If you want to separate these two parts out and obviously figure out what x is, we can do the inverse of sine. So I can press that shift sine button and it will do the inverse, and that'll help me just to figure out what x actually is and not sine x. So obviously thinking about your normal trigonometry there, press shift and then sine, and you get this sine minus 1, your inverse sine. Okay, and we're going to do the inverse of this value here that's on your calculator. So that'll be the inverse sine. I'm just going to press the answer button. So I'm just going to write ANS here rather than that decimal. But obviously that is just that decimal there that I'm writing in the bracket. You can feel free to write it all in if you want, but it seems like an unnecessary step when we can use our calculator a bit more efficiently here. So shift sine, ANS, which is next to the equals button, close the bracket and press equals, and it gives us the size of the angle, which is 53.408 and a few more decimals, but again it wants me to round it to 3 significant figures, so I can chop it after the 4 and we get 53.5. There we go, and this is about degrees this time, so degrees, and there's our final answer. It's obviously a very similar process in terms of the way we use the formula, but we have that final step there of using the inverse of sine to find out the size of the angle. Okay, just like with normal trigonometry when we're looking at right angled triangles, we still use that inverse of sine when we're looking for an angle. Okay, so this question says the area of the triangle is 105, work out the value of x, and in this case the value of x is the angle there sitting at the top. So if we plug these all into the formula again, we've got area equals, so 105 equals, there you go, half AB sine C, so let's just call that C, and then we've got our A and B here, so it's a half times 15 times the 16 there, times the sine C, and that in this case that is x there, so sine x. Now again, this is quite nice. I'm going to take the quicker approach. I'm going to divide all these pieces straight over. A half times 15 times 16. Again, you could work that out and divide it over. But I'm just going to write all the working out. So I'm going to do 105. I'm going to divide it by a half times 15 times 16, and that's going to equal sine C, or sine x in this case. There we go. So let's type that in. So 105 on the top, and we've got 0.5 times 15 times 16 on the bottom, and it gives us 7/8, or the decimal 0.875. So 0.875 equals sine x. And again, we want to know the value of x here, so just like with all the other trigonometry that we've looked at, when you're trying to find the actual x piece here, or isolate and find the angle, we want to do the inverse of sine. So I'm going to leave that 0.875 on the calculator. Again, it's not too difficult to type that in, but I'm just going to leave it in because it could be a nasty one. I'm going to do shift sine, which brings up my sine minus 1, my inverse of sine, and I'm going to put my answer in. So I'm just going to press the answer button, but I'm just going to put 0.875 in there. There we go. So I want to know what angle gives me that value there for sine. So if I type that in, so shift sine, I'm going to press the answer button and close my bracket, and here we go. I get my degrees here, which is 61.0449. There's a few more decimals, but again we are rounding this now to 3 significant figures as it says up there. So that's the 0, and again that 4's not big enough to round it up, so that's going to be 61 point, and I'm going to keep the 0 in there as it wants 3 significant figures. It's just indicating that it wasn't big enough to round it up there. So 61.0 degrees for that question. Very similar process, look, but when you're finding an angle, just like all forms of trigonometry, we have to do that inverse at the end, so the shift sign to get the inverse to get the angle. Okay, so there we go, there's 2 examples. Just plugging it into the formula, dividing everything over to the other side step by step, or you can do it all in one jump like I've done on this one. And then obviously just remember when you're looking for an angle, you have to do that shift sign to get the inverse there to get the angle. Work out the bearing from B to C. So if we have a look at the bearing from B to C, sorry, B from C, then we're going to be having a look at this angle down here, how to get to B from point C. So we're going to try and see if we can work out this angle here. Now we're going to apply a lot of the methods that we did previously in order to get this, because thinking about finding an angle within a non-right angled triangle, we can obviously apply the sine rule or the cosine rule. Now looking at this, if we have a look at this as a triangle, so obviously just highlight some of this, we've obviously got this length here, this length here, we know we can work out this angle here. Okay, this one here, let me just put, I was going to put a little question mark in there, there we go. We know we can work this one out, and then thinking about how we might apply some cosine rule or some sine rule to that or something, how could we actually go about that? Now we worked out that angle, we worked out this length, and as long as I have those two, I can actually do a bit of sine rule. Okay, we can do the opposite pairs here, and we'll have an opposite pair there, or we could actually use the other opposite pair if we were to find the other angle potentially. But the quickest way is going to be for us to just look at a pair that we already have straight away. So actually, if we go about doing some of those steps that we did previously, we should be able to work out any distance or any angle within this triangle. Let's have a look at actually going about doing that, and some of the steps we're going to do pretty quick here because we have already looked at this particular question in this particular format, but let's have a look at how we would go about it. So obviously it said it's due east, so we obviously knew this was 90, and we'd already done 210, take away the 90 to get our little angle inside the triangle, which was 120 degrees, and there we are. So we already know that was 120. We then used the cosine rule to get this one here, so we did a squared equals, let's have a look, the other two lengths squared, so we had 6.4 squared plus 3.8 squared minus 2 times 6.4 times 3.8, there we are, cos 120. Right, there we go. Okay, so I'm going to square root that all in one go, just to get the value of a nice and quick. So I'm going to do the square root of 6.4 squared plus 3.8 squared minus 2 times 6.4 times 3.8 cos 120. Pressing equals, there we go, and we get our value here, which was 8.9286. There we go, 9286. There's a few more decimals after that, but I'm just going to leave it as it is. It only wants my answer to the nearest degree here. But if I label that on there then, so let's get rid of the x, and we've got 8.9286, a few more decimals. There we go, as our little value there. So now that we've got that, now we've used the cosine rule, we've got a pair of opposites. Here we are, those two. And we've got another pair of opposites over here, opposite that angle that we're looking for. So we can use the sine rule now to work out one of the angles, and let's just imagine we could also do the same thing if we wanted to work out this angle over here. Obviously once we've got one of the angles, we can work out all of the angles anyway because it's angles in a triangle. But there we go, let's get rid of that. We'll focus on the actual angle that we're looking for. So when we're looking for an angle, we're going to use the upside down version of the sine rule. So we've got sine A over A equals sine B over B. There we go, sine B over B. So let's just apply all these. So let's say this is A, and this is my little a, and we'll say this is B, and this is my little b. Obviously you can swap and change them if you want. So we've got sine x, our sine A, so sine x, over 6.4. What's opposite that? There we go. And that is equal to sine 120. And that is over, what's opposite the 120? The new 8.9286 that we've just worked out. Right, so we can rearrange that. We want to times that 6.4 up to the other side, up to the top there. So we'll have sine x is equal to 6.4 sine 120 all over the 8.9286. There we go. So let's work that out using the fraction button. So 6.4 sine 120, and that's all over 8.9286. I probably could have used the answer button there just to make sure this is super accurate, but as I've left it to 4 decimal places, it's not going to make much of an impact on my answer here. So we get our value of sine x. So we get sine x equals 0.6207, and again a few more decimals, 6207, but we want to find the value of x, so I'm going to do the inverse of sine. So I'm going to get x equals, remember we're doing sine minus 1 here, so shift sine, answer, and we get 38.37 degrees. There we go, 38.37. A few more decimals after that, but it wants it to the nearest degree, so to the nearest degree x is going to equal 38 degrees. There we go, so 38 degrees. There we are. And it does say work it out as a bearing, so there's one more little step on here. Let's just highlight that down there. There's our last little bit of working out. Right, so now we've got that the angle there is 38 degrees. We need to think about this in terms of a bearing. Now remember the question said the bearing of B from C. Now if we look back at C, there's quite a lot of drawing here, so I might get rid of some of this stuff in a second, and we draw our north line in.
This is where this question gets really quite tricky, because obviously we've got the 38 degrees, we kind of feel like that question's finished there, but it wants the bearing of B from C. So really what we have to have a look at is the total angle from north, okay, because it is a bearing, not just that angle, so we need to know not just the value of x there, which is now 38, but the full angle here. So if we get rid of that x, we'll put our 38 in there as we've worked that out. There we go. And we also need to work out what the rest of the missing angle is there. Now there's nothing actually too tricky with working that out, but I'm just going to get rid of some of this working so we can kind of see this a little better. And we'll have a think about how we're going to actually approach this, just this final step here. So if we get rid of that, we've got all of this information now. We know that x is 38, we've worked that out. And let's just get rid of some of this writing here. Get rid of some of that, there we go. Right, so hopefully you can see this a little bit more clearly now. So in order to find that angle, look, if we think about one of the earlier steps we looked at in one of the bearings videos, and that is just thinking about the angles here within these two north lines, within these parallel lines. And obviously those angles there are co-interior, so we can find this angle here if we can find this angle here, because those two add up to 180. Now that angle there on the right is not too difficult to find, because we've got two of the other angles. We've got that this one's 90, and we've got that this one's 120. We're already told that the full angle there was 210, so we can find this one here by taking that away from 360. So 360, take away the 210 that's given to us, and that leaves us with 150 degrees for that angle there. So let's just get rid of some of this working again. So if that angle there is 150, there we are, that's 150 degrees. Given that these two here now add up to 180, that means that this little angle here has to be 30. There we go, 150 plus the 30 makes them add up to 180, as they are co-interior. Right, so now we've got that that is 30, we can now get the total angle of those two. So let's just get rid of some of this again. And let's just think about what we've got there. There we go, so our full bearing then from north going clockwise from to B, bearing of B from C. So from C here down to that line with the B on, that total angle there is going to be 68 degrees. Right, there we go. So the full angle there, the full bearing is 68 degrees. So obviously our answer is going to be 68 degrees, but not forgetting as well, as a final step, it's got to have 3 digits. So that's going to be 0, 68 degrees, and not forgetting that in the final step there. It's always horrible when you finish up a question like this, you've done all this working out, all those steps, and then you just miss out that one last little mark, making sure it's got 3 digits. But that is our final answer, 068. So there's a lot going on in that question. We had a lot of bearings rules, then we had cosine rule, sine rule, and then obviously finding the missing angles using a few more bearings and actually combining that and all, and actually making sure you get the final answer in the end with 3 digits. There's a hell of a lot to think about in that question there, and there's a lot going on and a lot of maths that you've got to be thinking outside the box with as well, because there's obviously you've got to be able to think in the moment, what do I need to use here? Do I need to use the cosine rule? Do I need to use the sine rule? So always just try and break it down in steps and have a think about what you're actually trying to find and where you're going with the question. So it says here the graph of y equals sine x for x values from minus 270 to plus 270 is shown below. And obviously that is shown on the graph there. We've got minus 270 all the way over to 270 over here. It says on the same axes, draw the graph of, and we've got y equals 1 minus sine x for values from minus 270 to plus 270. So that's the graph we're going to have to draw there, and that doesn't look very nice. Now this is all sort of, this question here is very much linked into graph transformations. We're actually transforming this graph, and we just need to figure out how this graph is transformed, but actually we can actually do this on a calculator. Now this particular graph transformation here has got 2 different transformations going on, and we could rearrange that. We don't have to write 1 minus sine x, we could write negative sine x plus 1, and just sort of rearrange those if we wanted to. So we could do it like this, we could write minus sine x plus 1. Oh, missed my bracket there, let's put that back in. There we go, plus 1. And think about what these transformations actually represent. So that negative in front of the sine x flips the y coordinates from being positive to being negative. Obviously check out my video, and in fact I'll link that in the description below on graph transformations as well, because it's probably worth checking out, because it does link very strongly into these trigonometric graphs. So that negative there relates to a flip or a change of the symbols in front of the y coordinates. We've then got the +1 at the end, and again that's outside the bracket. It changes the y coordinate, it changes the y-intercept, it moves the whole graph up by 1. So you could actually take a graph transformation approach to this. You could try flipping it over and then shifting it up 1, and we could probably do that quite nice and quick. I'm going to do it in 2 different ways though, but just if you are quite keen on your graph transformations, you could first flip it over and just think about that by flip. Oh, that's not my pen, let's just change that. We could take all of these little coordinates here, this one, this one, this one, and this one. I've not bothered with the zeros because they'll stay where they are. And we could just flip them down, change the coordinates there, and that would move the coordinates here. And we actually end up with, and I'll try and draw it. There we go, we end up with that. And then we need to shift it all up by 1. So take all those coordinates, shift them all at 1. That would shift it at 1, that would shift it at 1. Let's have a look. These 0 coordinates need shifting at 1 as well. I'll try and shift them all at 1. It's not the nicest now when you start drawing all over this. There we go. Shift that all at 1. And it makes this sort of curve here. There we go. So drawing it using a graph transformation approach. Let's just get rid of that red one. There we go. That is where our curve ends up following this graph transformation. Okay, not the nicest though, that's quite nasty actually. It's a very sort of horribly difficult graph transformation question, having to sort of flip it over the x-axis there and then actually shift it at 1 as well. But I'm going to take a little bit of a different approach, but just so you know, you could actually take that approach there using graph transformations. So obviously check that video out if you're not sure on that. You can always have a think about what I've actually done there once you've had a look at that. Now instead of doing that, I'm just going to take this nice calculator approach, because this was actually a calculator question as well. So rather than doing that, I'm just going to plug my numbers into this formula here. So I'm going to start with negative 270. So I'm going to do 1 take away, and I'm going to do sine minus 270. There we go. And that's going to give me my first value. So 1 take away sine, and I'll put minus 270 in the bracket, and I get the value of 0. There we go, so that's my 0. Then I'm just going to change that for the negative 180. So I'm just going to put minus 180. I'm just going back into my calculator and changing that value. That gives me that value there. Back in, negative 90. There we go, and that gives me 2. So negative 90 is up here at 2. I'll put 0 in, and that gives me 1. There we go, we'll put 90 in. And that gives me, sorry, I'll put that in, 1 minus 90, yeah, that gives me 0, there we go. Then put 180 in, last one nearly done, and that gives me 1. Where's that gone? 1 is there, and then 270. There we go, and that gives me 2. And that is there. And again, just drawing that up with a nice smooth curve. Best you can. There we go. And there is our transformed graph. But again, 2 different methods that you could take to approach that. Obviously, if you're really good with your graph transformations, you could have flipped it over first, changed the y coordinates, made them positive, negative, and the negative one's positive, and then obviously shifting it up 1, doing that transformation with the 1 at the end, changing the y-intercept. Or you could just take this approach, just plug in the numbers into the calculator, plot them all nice and neat, and connect them all up together. So it's up to you which one you prefer, but just a couple of different ways that you can actually approach that question. Okay, so this says, here is the graph of y equals cos x between the values minus 180 and 180. And again, we can see that on the graph. It does stretch from minus 180 to 180. It says on the grid, sketch the graph of y equals negative 2 cos x, but again, between these values. Okay, so taking a little approach to this then. I'm just going to take the calculator approach. Now again, you could take a graph transformation approach to this, but let's have a look at the end and see what that graph transformation is. We'll take that calculator method to start with and just start plugging the values into this formula. So we've got y equals negative 2 cos x. So on my calculator, I'm just going to type in negative 2 cos. I'm going to start with that first value on the x there, which is negative 180. So minus 2 cos, and then negative 180 in the bracket, and it gives me the value of 2. There we go, that equals 2, and I'm just going to do that same approach for all of them. So that 2 goes up to there, and there we go. So back into the calculator. I'm not going to sort of do all the little sub values in between. I'm just going to go straight for negative 90 and see where that is. So negative 90 ends up at 0. There we go, so that stays where it is. I'm going to go for 0 now, so back in, negative 2 cos 0, and that gives me a value of negative 2. And let's go back for 90, negative 2 cos 90, gives me a value of 0. And negative 2 cos 180
gives me a value of 2. There we go, so that value of 2 is there. And again, we just need to join that up with a nice smooth curve. There we go, and that's our point drawn there. So again, that's one method that you could approach. If I swap to a different colour here, we'll have a think about the graph transformation as well. So negative there flips the coordinates over. So I could have actually started by flipping those coordinates over. So let's go about doing that. We've got this one here, which is going to flip to the other side there. 0 state, that one there stays where it is. This one here on 1 flips down to -1, which I can just about see, it's about there somewhere. We've got the one on the axes then, which stays where it is. And we've got this one down here, which flips up above. So the minus part, okay, just like before, changes the symbols in front of the y coordinates. So we can draw that in. Okay, I'm going to get rid of this in a sec. And just about draw that in, there we go. So that's what the negative part does, and then you've got the 2 there, and again this is all linked to graph transformations, but the 2 is going to double the y coordinates, okay, outside the bracket, not affecting x, it affects the y coordinate, does what we expect, 2 multiplies the y coordinates by 2. So this coordinate here, that's currently at 1, goes up to 2, which is there. 0 stays as it is. This one here, which is at -1, goes down to the -2, which we've got here on our actual graph. Again, 0 stays where it is on the next one, and then again finishing it off with this one, that 1 there goes up to the 2. So you could actually take a graph transformation approach again. Again, I think it is actually a bit harder than just type it in on the calculator, but just so you know that there are multiple methods that you could use here. There isn't just one way to solve these sorts of questions. But there we go, that is our final answer there with our nice green line that we've drawn in. Okay, so when it comes to trigonometric identities and equations, it is essential that you know the trigonometric graphs. So as you can see on the screen, I have 3 of the trigonometric graphs, and it's very important that you are able to do a sketch of these. These are quite accurate, the ones that I've done on the screen, but you need to be able to draw a sketch of them. So you need to know that for y equals sine x, it goes in the origin, and then we have these waves that go up and over every 90, or up and under every 90. So it goes over the 90, down through the 180, under the 270, and then back through the 360. And this graph here goes on infinitely to the left and right of the y-axis, but we need to know how to draw a sketch of that, and you're going to see why in some later questions. For the one below, for the cos graph, this has just been translated, or it's the sine graph which has been translated 90 degrees to the left. So you can see instead it starts at 1 on the y-axis, but then it follows a very similar pattern. It goes down through 90, under 180, up through 270 and up and over 360. And again, this goes on infinitely to the left and right of the y-axis, but it follows this pattern. The tan graph is very different. It does have these waves, and as you can see there are asymptotes at -90 and 90, and then each asymptote follows on every 180 degrees, and again that is to the right and to the left of these curves. So you do need to know these graphs, you need to be able to draw basic sketches of them, and this is going to be very helpful when we are solving our trigonometric equations, as I do use a graphical method. Again, there are other ways of solving trigonometric equations, but I do use this graphical method as I do like them, and I do think that it's important that you know these anyway, so it's always good to be able to use them for further elements. So do make sure that you can draw a basic sketch of all of these graphs and you know them very well. Okay, so within this is also some exact trig values. Now you should know a lot of these exact trig values from GCSE level, but these are just the basic trig values, or the exact trig values. Now some of these can be written slightly differently. For example, 1 over root 3 down here for tan 30, you could actually rationalise that multiplying top and bottom by root 3, and instead you could write it as root 3 over 3. That's absolutely fine, and of course you will have a calculator for all these questions, but there are some exact trig values that you should know, and also you should be able to then relate these to the trigonometric graphs, as we will see on some later questions when we are looking at solving them. So for now, all you need to do is you need to make sure you know these exact trig values, and you also need to know the method for finding them. Again, I'll link the video in the description for how to find these, so if you're not sure on how to find them or how to learn these, then obviously you can go and you can check the full video in the description.
Okay, so the two main trigonometric identities that we need to know are these two. So we'll start with the one on the left. We've got sine squared theta plus cos squared theta is always equal or identical to 1. Now this one is super important, as is the other one, but this one is very important. Now this can also be rearranged. We could minus cos squared theta to the other side, which would tell us that sine squared theta is also equal or identical to 1 minus cos squared theta. So that is another one of our identities. Of course, we could have also rearranged it by minusing sine squared theta to the other side, which would have left us with cos squared theta, which is identical to 1 minus sine squared theta. So you need to know that identity, and you need to also know these two rearrangements, as we'll be using these a lot throughout our trigonometric identities. For the one on the right, when we're looking at tan theta is equal to sine theta over cos theta, we can also do rearrangements of that. So if we multiply cos theta to the other side, we could also say that tan theta multiplied by cos theta, so tan theta cos theta, is equal to sine theta. And again, we could rearrange that by dividing both sides by tan theta, and we could say that cos theta is equal to sine theta over tan theta. So there are rearrangements of this as well that you need to know, but as long as you know the two at the top that I've highlighted, you should be perfectly comfortable rearranging them, and of course that leaves us with quite a few identities here. So really you only have to learn the main two, and then obviously how to rearrange them. But these are very important. I'd make sure that you had these written down on some exam revision flashcards so that you always had these to hand. As we're going to be using these for any trigonometric identity, we'll be using one or the other, and particularly with our trigonometric equations, so do make sure you know these very well. Okay, so looking at a trigonometric identity. Now as you can see here, it says prove that 2 sine theta minus cos theta squared plus sine theta plus 2 cos theta squared is identical to 5, or always equal to 5. Now this is just one example of lots of different types of questions. So of course you do need to practice quite a lot of these, but this is a really good one for us to have a look at. So what we need to show in this is that for all of this on this left hand side is going to be equal to 5, or is going to always equal 5. And we can go about that by using some of our trig identities. Now we don't have a tan theta in this one, but that's not necessarily to say that it won't appear, but obviously we do have our other trig identity that has sine and cosine. So if we're looking at this one, we want to think about how we could change this so that it just becomes one or the other. But maybe we'll have a look at expanding it first and seeing what we get. So if we expand the first one here, that's going to be a double bracket, and that would be 2 sine theta minus cos theta, and we'll go about expanding that. So we would write that twice. So 2 sine theta minus cos theta, and you can already see that we're going to get some squareds involved. So if we expand that, 2 sine theta times 2 sine theta would become 4 sine squared theta, and then 2 sine theta times the minus cos theta, and we're going to do that twice, so that would be minus 4, and you could write either sine or cos first here, but 4 sine theta cos theta. Again, that piece that I've done just there, I have skipped a step in my expansion. I did sine 2 sine theta times the minus cos theta, and the minus cos theta times the 2 sine theta. So just doubled that up in one step. We now have to do the negative cos theta times the negative cos theta, which gives us plus cos squared theta. Now we can move on to our second bracket. Now we've fully expanded that one, and our second bracket is this one here. So if we expand that as well, that is again 2 of those brackets. So sine theta plus 2 cos theta, and we're going to multiply that by another sine theta plus 2 cos theta. Okay, so if we expand this one, sine theta times sine theta gives us sine squared theta. Then we've got sine theta times the 2 cos theta, and we've got that twice. So again, that's going to be plus 4 sine theta cos theta. There we go. And then we have the 2 cos theta times the 2 cos theta, which gives us plus 4 cos squared theta. So we've got our 2 pieces and we need to add them together. So we had a plus sign between these 2. So if we add those 2 pieces together, and let's see what we get. So we've got the 4 sine squared theta and a 1 sine squared theta here. So that would be equal to 5 sine squared theta. We've then got these middle pieces. So we've got the negative 4 sine theta cos theta and the positive 4 sine theta cos theta. So they would just cancel out. And then we have the plus cos squared theta and the plus 4 cos squared theta. So that would be equal to 5 cos squared theta. Now we need to figure out how we're going to make this always equal to 5. So we have 2 options. We could change the sine squared theta into a cos, or we could change the cos squared theta into a sine. So let's just think about our identity, and we'll put one of our rearrangements. So let's change one of them. We'll say that sine squared theta, or we could go, in fact, let's just go with cos squared theta. We'll say that cos squared theta is equal to, always equal to 1 minus sine squared theta. And that's going to allow us to change this cos squared theta here into 1 minus sine squared theta. So if we go about doing that, we would still have the 5 sine squared theta at the start, but we would now have 5 lots of 1 minus sine squared theta. So just replacing the cos squared theta with 1 minus sine squared theta has now eliminated cos from our identity that we're looking at here. So again, we could have done it the other way around. We could have got rid of sine and replaced that with cos using our other rearrangement, but it's absolutely fine for this one either way, as long as we just have sine. So now we could expand that bracket. So we would have 5 sine squared theta, and that would be plus 5 minus 5 sine squared theta. There we go. So where are we going to go from here? Now, if we bring that up to the top, let's just have a look at what we've got there. We have got and let's just highlight it, 5 sine squared theta and a minus 5 sine squared theta, which means they're going to cancel out, which just leaves us with the plus 5. So we just have the answer 5. So because we've got the answer 5 there, we have obviously proved that all of that just simplified down to 5. So therefore we have proved our identity that the 2 sine theta minus cos theta squared plus the sine theta plus 2 cos theta squared is identical to 5, and we've proved all of that. So there we go, that's all we had to do. Obviously we only had to use one of our identities. We use this one just here, and again you could have done that a slightly different way by rearranging it, but again you'd have just got to the answer 5 because you would have had a 5 cos squared theta and a minus 5 cos squared theta, and it would have all just cancelled out and you'd have been left with 5. Okay, so moving on to our first trigonometric equation. This is going to be quite a tricky one, quite a long one and quite tricky to fit all on the screen, but I think we'll just manage to fit it in. So the first part here says, show that 4 sine squared x minus 3 cos squared x is equal to 2 can be written as 7 sine squared x is equal to 5. So the first thing to notice here is that in our second part, we only have sine. So in our first piece here, we're going to want to try and eliminate this cos. So if we eliminate that, we're going to want to think about which identity would help us to eliminate that, and that is that cos squared theta is equal or identical to 1 minus sine squared theta. So if we replace that cos squared theta with 1 minus sine squared theta, it's obviously going to start getting us towards our final answer. So if we go about doing that, we have 4 sine squared theta, or sine squared x, sorry, because we've got an x in this as we're looking at an equation. That is going to be now minus 3 lots of 1 minus sine squared x. There we go, and that is equal to 2. Now if we expand that bracket, we've got 4 sine squared x minus 3, that's negative 3 times negative sine squared x, so plus 3 sine squared x is equal to 2. There we go. Now we can add together our sine squared x. We've got 4 sine squared x plus 3 sine squared x. That adds together to make 7 sine squared x. So you can already see we've got something which is matching that 7 sine squared x. We also have that minus 3 is equal to 2. And now we could minus 2 from both sides, or we could add 3 to the other side. Now looking at the equation up here, what it wants us to be written as, it says it's equal to 5. So we want to add 3 to the other side, which would give us 7 sine squared x is equal to 5. And there we are, we have showed that it equals that. So that would be our final answer, and we have shown that correctly using our trigonometric identity. Part B here says, hence solve for values between 0 and 360, including 0 and 360, that this equation here is equal to 2. So we're going to solve this equation and we're going to give our answer to 1 decimal place, or our answers to 1 decimal place. So we'll have a look at this and think about how we'll go about answering this. Now, of course, this equation here we have just shown can be written as this equation here. Now that we would not be asked to do that unless it was going to be useful. Now the reason it's useful is the second equation that we have shown only has sine in. So we're going to be able to use our sine graph to find our solutions and how we'll go about doing that. So at the moment we have 7 sine squared x is equal to 5, and we're going to go about solving it. And you'll notice this with a lot of these questions, that part that it's asking you to show it as how it can be written is going to be used in the second part of the question. So to go about solving this, we want to get what sine x is equal to. So if we divide both sides by 7, we'll know what sine squared x is equal to. So sine squared x is equal to 5 over 7. Now to get what sine x is equal to, we just need to square root both sides. So we're going to have that sine x is equal to, and don't forget when you square root you have plus and minus, so plus and minus the square root of 5 over 7. So there we go, that's what sine x is equal to, and now we can actually use our calculator to do shift sine and find the values there. And if we put that into our calculator, let's do the positive one to start with. So sine minus 1 of, and let me just type it in, the square root of 5 over 7. Let's have a look, let's just write this down. So sine minus 1 of 5 over 7 is equal to, and we get 57.688. So it wanted it all to 1 decimal place, so 57.7 degrees. If we do the same for our next one, so sine minus 1 of negative 5 over 7, and again just go into your calculator, sorry, the square root of, I've just realised I forgot to put the square root symbol there. Put that in, I had to type that in on the calculator. We'll go back, we'll put the negative 5 over 7, close our bracket, and for this one we get the same answer but the negative version, so negative 57.7 degrees. So we have actually solved our equation here. We've got two answers. We've got 57.7, and refer back to our ranges here. So it's between 0 and 360. But this negative 57.7 falls outside of that. So that's not going to be one of our solutions. However, it is going to be able to help us to find all of our solutions on our sine graph. So we're going to use these answers to see if we've got any other solutions. And this is where it comes into play that it helps to be able to draw the sine graph. And again, this is where you can use different solutions. You can use your quadrant method if you would prefer to. That's absolutely fine. But as I've said before, I think it's really important you know these graphs, so I always like to discuss them. So if we look at the sine graph and we draw a basic sketch of what it looks like, if we actually draw that, sine starts in the origin, obviously it goes up to 1 and down to minus 1, and it goes along from 90, 180, 270, 360, and we'll go back a little bit as well as we have that negative value. And if I was to draw that in, and again it's just a little sketch just so we can visualize it, it would look something like that. So if we label on our points negative and the positive side, 90, 180, 270 and 360, and then we'll have negative 90 and also negative 180, and let's just imagine where these points are. So the points that we have, we've got 57.7, which would lie between 0 and 90, so that would be just there. and we've got the negative 57.7, which is between 0 and negative 90 just here. So in order to find all of our solutions, all we have to do is trace along between 0 and 360 and see where these points hit any other point on the curve. So we obviously have our 57.7 just here, and if we go to the right, we obviously hit the curve at another point just here. So in order to find that one, we can just think about on the graph. Now 57.7 is 57.7 away from 0, so to find that one on the right, we would just do 180 and take away 57.7. And if we work that out and turn it into a decimal, that comes out as 122.3. And there's one of our other solutions, and that's between 0 and 360. If we go down to the bottom one at the negative 57.7, and we go across from that, we hit the curve here, and if we keep on going, we hit the curve again here, and that is between 0 and 360. So we have two more solutions just there. So to find that one, if we add 57.7 to the 180, then that is going to find our next solution. So if we do 180, add 57.7, and make sure you type that in correctly, and there we go, that comes out as this one here, 237.7, and again we can do that for the reverse. For the one next to it we can do 360, take away 57.7, and that gives us our final answer there of 302.3. Now of course there is another point on the graph, as I've obviously gone into the negatives, there is another point just here, but obviously that falls outside of our 0 to 360 range, so that's not going to be a solution that we can use. So the negative 57.7 we can't use, but we have got the 57.7, the 122.3 just here on that top part of the curve, and then we had also the 237.7 and the 302.3. So we have four answers for this particular question. So we would give them, we would say that x is going to equal 57.7, and paired with that we've got x is equal to 122.3 on the top part, and then down the bottom we had x was equal to 237.7, and matched with that on the right there, on the right of that was 302.3. These are all degrees, so we would put degrees with all of them, and there we go, they would be our four answers for this question, all given to one decimal place. So as you can see, very important to know these trigonometric graphs, and obviously knowing how to do your inverse of sine, and just getting that to the point where it was sine x was equal to a number, so that we could actually find that amount in degrees and relate it to the trigonometric graph. So that's one type of question, and obviously you can have harder ones than this, and we're going to have a look at some harder ones as well. Okay, so looking at one of our harder trigonometric equations, you can see that it obviously doesn't look very nice. It says show that 10 sine squared theta minus 7 cos squared theta plus 2 over 3 plus 2 cos theta is always identical to or equal to 4 minus 4 cos theta. Then it asks us hence solve, and we've got a very similar question to what we've looked at before. But we're going to start with this first part and show that all of this comes out as 4 minus cos theta. Now straight away you can see that in our answer part there that we're looking to show that it's identical to, it has a cos in. So for all of the pieces that have a sine in or a sine squared theta in, we're going to want to turn that into a cos. So straight away we'll write down our identity for that, and that is that sine squared theta is identical to 1 minus cos squared theta. And we'll plug that in and see where we get to. So if we start by replacing the sine squared theta, we have 10 lots of 1 minus cos squared theta minus 7 cos theta plus 2, and that's all over 3 plus 2 cos theta, but we'll just go about simplifying the numerator to start with. So the next step for the numerator would be to expand that bracket, so we would have 10 minus 10 cos squared theta, and that is then minus 7 cos theta plus 2. So that's our next step, and now we're just going to think about whether we can simplify this. Now the only thing we can really do to simplify this is obviously to add the 10 and the 2 together. So we'll add those two together as they are our only like pieces on the top, and that would leave us with 12 minus 10 cos squared theta minus 7 cos theta. Okay, there we go. So at this point we need to think about whether this factorizes. This is just like a trigonometric quadratic. If we think back to obviously looking at quadratics, we could rewrite this in terms of x. So rather than writing cos, I'm just going to replace that with the letter x and rewrite this as a quadratic. So if I was to rewrite that, it would look like this. It would look like 12 minus 10, and that's cos squared, so I would have 10x squared minus 7x. And I probably want to rearrange that so it looks like a normal negative quadratic, which is 12 minus, and then put the 7x, and then minus 10x squared. So this is going to really help if you are struggling to factorize trigonometrics when we have the quadratics and we're trying to actually factorize them. You can just write that the cos or sine or whatever we're using in terms of x and then look at it from there. So if we go about factorising that, we want to think about those numbers that multiply to make 12, but of course we can actually change this quadratic and swap back our brackets at the end. So just to make it a little bit easier, I'm going to write it as positive 10x squared plus 7x minus 12, as this is really nice and quick to factorise. Our factors here would be 1 and 12, 3 and 4, or 2 and 6. And you can obviously see that that is going to be one of those numbers, but we need to think about our brackets. Now it's unlikely that it's going to be 10 and 1, so we'll go with 2x and 5x and see if it factorises from there. Of course, if you don't want to factorise, you could type these into your calculator to get your solutions, but nice and easy for us to factorise. We have 2 times 4, so it's going to be that one there. 3 and 4, again take your time with this, but 2 times 4 would equal 8, and 3 times 3 times 5 on the other one would be 15, and 15 and 8 we can make 7 with. We're trying to make positive 7, so we'd want positive here and negative here, as that is going to make negative 8 plus 15, which makes plus 7. So we've managed to factorise it. All you have to do, because we swapped over the negative quadratic and made it positive, you just swap these brackets or the pieces in the bracket over. So we would have, and it doesn't matter when there's a plus, but I'll swap it over anyway, 3 plus 2x. And over here we have 4 minus 5x. Okay, so there are our brackets done, but obviously these pieces, the x's, should have been a cos, so we just want to replace that, which would mean that our numerator now wouldn't have the x there, but would have the cos, so our numerator would be 3 plus 2 cos theta, and next to that 4 minus 5 cos theta. There we go. And our denominator, if we write that in as well, was 3 plus 2 cos theta. Now if you have a look, obviously looking at this fraction here, you can see that we have a matching factor on the top and the bottom, which is the 3 plus 2 cos theta. So they can both be cancelled out, which means all we are left with is the 4 minus 5 cos theta. So all of that would go down to 4 minus 5 cos theta. And as you can see, that matches what we're being asked to find in the question, where we're being asked to show that it was always equal to 4 minus 5 cos theta. So we've managed to prove that for step 1. So this would be the first stage of this question. Obviously you can see that I've run out of a lot of space here, so I am going to have to get rid of this working, but we're going to have a look now at the second part of the question. So we'll get rid of all this working and we will have a look at the second part. Okay, so for the second part of this question, it says hence solve between 0 and 360, including 0 but not 360, the equation, and then it gives us the original equation, or the original pieces that we had there, but instead of putting theta, they've put x, but this time it doesn't say that it equals 4 minus 5 cos theta, it says that it is equal to 4 plus 3 sine x. Now we already know from the first part that all of that is going to be equal to 4 minus cos theta. And if we were to write that using the letter x, that would just be 4 minus 5 cos x. So we know that if both of them are equal to one another, that 4 minus 5 cos x is going to be equal to 4 plus 3 sine x. And that's going to be a little bit easier for us to use than that fraction. And again, you're seeing in this question, we're using the piece from the start to help us with the second part here. So the first thing we're going to want to do is set them equal to each other. So if we say that 4 plus, it doesn't matter which one we write first, let's just go for 4 plus 3 sine x. And that is going to be equal to 4 minus 5 cos x. Now again, we want to obviously solve this, so we want to get this to a point where it only has sin, cos or tan, and we'll think about how we could maybe get there. Now the first thing that you might notice here is there's a 4 on both sides, so we could minus 4 from both sides, and that would just leave us with 3 sine x, which is going to be equal to negative 5 cos x. So that would be our first step. That's gotten rid of a 4 from both sides. What we could now do to get it so it's just sine x or just cos x, and I'm just going to divide both sides by 3. That's going to remove the 3 from the start, and then we'll think about where we could go with next. So if we divide both sides by 3, that leaves us with sine x equals, which is going to be helpful, is equal to, and I'll just divide the negative 5 by the 3, so negative 5 thirds cos x. Now at this point here, you'd hopefully notice that one of our trig identities is going to get involved, and that is if we divide both sides by cos x, we're going to have sine x over cos x. Now we know from our trig identity that sine x divided by cos x is equal to tan x. So that is going to eliminate our two different trig pieces there, because now we're just going to have tan x. So if we do that, we would have sine x over tan x, when we divide by cos x, sine x over cos x is going to equal negative 5 over 3. And again, you could write in what you've done there, we've just divided by cos x. There we go. And of course, sine x over cos x is equal to tan x, so we could just rewrite this that tan x is equal to minus 5 over 3. So that's going to be very important there, because now we're in a position where we can solve it. So at this point we can do the inverse of tan and get our solution. So for tan minus 1, so we get our angle, and that's tan minus 1 of negative 5 over 3. If we type that into our calculator, we get the answer, and it comes out as minus 59.0. So we've got our first solution. Now, of course, that has fallen outside of our range that we were looking at, as we're only looking between 0 and 360. So for this, we are going to have to draw our tan graph, and we're going to have to visualize where those solutions are. So if we get rid of some of this working, and we can just draw the graph over here, and that's going to help us just to visualize that. So here we go, let's just get rid of all of this, lots of pieces there. But we want to draw this tan graph, we want to draw a nice sketch of that. So if we draw some axes, again our first wave goes through the origin, and then we have our asymptote at 90, and our next one goes up then through the 180, and our next asymptote is at 270. So that's going to go up through the centre there, and I've drawn that very badly, so we should probably draw that again. Again, it is just a sketch just to help you to visualise it, but it's good to draw it quite well. And our next one would start at 270, and it goes up through 360, so we could stop there, but of course that does actually carry on, but we don't need to draw the rest in because we're only going up to 360. So let's think about where that solution would lie. We've got negative 59.0, and that would go between 0 and the negative 90, where our other asymptote is. So it's going to be somewhere in the middle. Let's just imagine it falls just there if we were to trace that down. And then of course all we're going to do is go across, so we would go across, we'll hit the next curve just here, and then we're going to go across again, and we'll hit the next curve just there. Again, you might know some quick ways of jumping between these tan values, and again, if you use any of your quadrants and things like that, that's absolutely fine. But again, as I've explained before, I do like to visualize what these graphs look like just to imagine where they're going to go.
So for the first one, to jump between these two, it is just a jump of 180 degrees. So if this one here is negative 59, and let me just check it on the calculator because it doesn't say in this question how to round it. It did come out as negative 59.04, so I'm going to give it to 2 decimal places just to make it a little bit more accurate. So negative 59.04, to jump to the next one there, all I need to do is add 180. So if we add 180 to that, it comes out as 120 point and then 96 it comes out as. And there we go. So jumping on to the next one, I would go another 180, so plus 180 again, and that comes out as, on the calculator, that comes out as 300.96. And of course, if we jump to 180 again, it would go over our limit, which is 360 degrees. So these solutions here, we've got 3 solutions, negative 59.04, which is below 0, so we can't have that one, but we do have 120.96 and also 300.96. So we do have 2 solutions there. Again, we would round that as we see appropriate, so we could say that x is equal to 120.96. Of course, we could write that is equal to, or we could say 121 degrees to the nearest degree, and we also have x is equal to 300.96, or we could write that that is equal to 301 degrees, again just being to the nearest degree there. So obviously you can see this one is pretty tough. There was quite a lot of steps, but you can see a lot of similarity between these trigonometric equations, whereby we are isolating it down to either sin, cos or tan. We're doing the inverse to find the angle, and then we're just sketching it onto the graph so we can see how many solutions we've got. Given that a equals 3i plus 4j and b equals I minus 2j, find lambda if lambda a minus b is parallel to the vector I plus 3j. Now straight away before we get started, you can see this time the coefficients of I and j are not equal. The coefficients of j in this particular instance right here are 3 times bigger than the coefficients of I. And we're going to bring that concept in the last step, back when we were making them equal to each other. We're just going to think about how we're going to approach that, so we'll come back to that right at the end. So we've got lambda lots of a, and a is 3i plus 4j. So we've got lambda lots of 3i plus 4j, and then we're going to take away from that, you've got to be careful with this one, b, and b is I minus 2j. Now as we're taking it away, I'm going to put this one I minus 2j into a bracket. Obviously it doesn't matter if it's a plus between them, but when we're taking away, as we're taking away both of those, we don't want to forget to take away the negative 2, and otherwise we might only take away the I. So do be careful when you're doing takeaways, particularly when you've got more than one piece that you're taking away, that you put those pieces in a bracket just to avoid any mistakes there. So let's expand this bracket out and then obviously change the signs on that second one. So we have 3 lambda I plus 4 lambda j, and then we're going to take away I and also take away the negative 2, which makes it plus 2j. And there we go, that's all of those pieces listed out. Now again, we want to have a look at the coefficients of I and the coefficients of j separately, so let's join them together. So we've got the 3 lambda I, and we've also got the minus I, so we'll just put minus I, and then we've got plus 4 lambda j plus the 2j. And if we have a look at the coefficients that we've got here, we've got 3 lambda and also a negative 1 in front of the other one. A little bit hard to highlight that one there when we don't write the 1 in, but we know that that's a 1 and we can write that in as when we get to it. Now the coefficients of the other one, we've got 4 lambda being positive again, plus 2. So let's write these out and see what we've got. Now I'm going to do it like we did before. I'm going to change this in a sec because what I'm about to write isn't entirely correct, but I'm going to say, okay, well let's set these equal to each other. So we've got 3 lambda minus 1, and we'll set that equal to 4 lambda plus 2. Now technically what I've written there is not mathematically correct, and this is where we're going to have to look back towards this just here. And that's because we know that the coefficients of j are 3 times the size of the coefficients of I. And at the moment we've said that they're equal. Now in order to work around that, what we could do is we could say, okay, well this side here, we need to divide that by 3. You can do that, and that's absolutely fine. Ultimately, you're going to get to this next step that we're going to write, but we could say, okay, well, we need to divide that side by 3. Or what we could say is, okay, well, actually the coefficients of I, we're going to have to multiply by 3. And if we make the coefficients of I 3 times bigger, they would then match the coefficients of j, which are already 3 times bigger, if that makes sense. So let's just times this side by 3, so we'll stick it in a bracket, we'll times it by 3, and then the coefficients would be equal. So let's go about timesing that by 3, so the 3 lambda would become 9 lambda, and the minus 1 would become minus 3. So 9 lambda take away 3 has to be equal to 4 lambda plus 2. And now we've got a nice easy equation to solve. So let's solve this over here. So let's minus 4 lambda from both sides. That would leave us with 5 lambda. And let's add 3 to the other side, and that's going to equal 5. So 5 lambda equals 5, so 1 lambda when we divide by 5 has to equal 1. And there's our final answer. Right, there we go. So that's how we're going to approach these questions, and it's all about looking at the coefficients and making this little equation and making them comparable. So if the coefficients, or if there is only one letter, then we need to eliminate one of the other letters or one of the other directions. If the coefficients are equal, we can set them equal to each other and solve it. And obviously then if the coefficients are different, so we have something like I plus 3j, or maybe you could have, I don't know, 5i plus j, you would actually have to multiply one of the sides to obviously make them equatable, and then obviously you can do your equation from there. So this one says we've got 3 vectors. We've got A, which is p over minus q, we've got B, which is q over p, and C is 7 over 4. Given that A plus 2B is equal to C, find the values of p and q. Well, first of all, let's work out what A plus 2B is. So we've got A, which is p over minus q, and we're going to add to that 2 lots of q over p. And it says that that is equal to C, which is 7 over 4. Now, first thing to note here is obviously we have 2 unknowns. We've got a p and we've got a q. And there's a little hint in that, and whenever we do have 2 unknowns, sometimes we may have to look at simultaneous equations. There's a little bit of a hint in here that we may have to involve another topic within this question. So let's have a look. Now we need to do 2 lots of p and q. So we've got p on the top, and let's just add together that top line there, but also timesing that right vector there, the 2 lots of p over q by 2 at the same time. So we have p plus, and we're going to have 2 q's, as we're going to multiply that one by 2, and that's going to equal the top number over there, which is 7. Now if we have a look at the bottom line, we've got negative q plus 2 lots of p, which is going to equal 4. So negative q plus 2 lots of p is going to be equal to 4. And there we go, we've got 2 equations, both with p and q in, and we can use simultaneous equations to solve that. Now, just for the purpose of making this look a little bit nicer, what I'm going to do is I'm going to swap over the q and the p just to make sure that they're aligned with our simultaneous equations. You certainly don't have to, but I think it looks a bit nicer when we line them up in the same way. So rather than writing minus q plus 2p, I'll write 2p minus q. So let's get rid of that, and we'll write 2p minus q. There we go, so we've got our simultaneous equations. Now in order to solve our simultaneous equation, obviously we need a similar numbered coefficient with either p's or q's. I tend to like to make the second one the same, so I'm going to times the bottom equation by 2, so that we have 2q for both of our equations. So I'll times that one by 2 and rewrite it. So let's have a look. When we times that by 2, we get 4p minus 2q, and that now equals 8. There we go, so we've got our 2 equations. We can forget about the one in the middle. In fact, let's just get rid of that one. We lost the q there. Let's get rid of that. There we go. And we'll solve it from there. Let's move this up just above. There we go. And we have different signs in these simultaneous equations, so we'll add them together. And let's have a look. We get 5p. The 2 and the minus 2q obviously disappear there, they cancel each other out. And we have 7 plus 8, which is 15. And there we go, nice and easy to solve then. P is equal to 3, 15 divided by 5. Now we've got our value of p. Just like with normal simultaneous equations, we're just going to substitute that back into one of these equations up here. So we'll sub it into the top one. So if p is 3, we get 3 plus 2q is equal to 7. We can subtract 3 from both sides. So 2q is equal to 4, and divide by 2, q equals 2. And there we go, we've solved that question. Just highlight our 2 answers there, because we've got p equals 3 and we've got q equals 2. So something a little bit different there. Obviously we didn't write it in our normal vector way with our i's and our j's, but just goes to show you that we can actually have these questions involved with normal column vectors as well, with something a little bit different with simultaneous equations there. Now with this question here, we're going to have a look at the magnitude, which is essentially the distance that two vectors actually travel when we combine them together. And we're going to have a look at drawing that down and writing a little sketch of them to see what it looks like. So as always, grab a piece of paper, grab a pen, make some notes, and we're going to start with this question on the screen. So it says, given that A is 3i plus 4j and B is negative 2i minus 4j, and we're going to find two different things here. Now already you might have noticed there's a little bit of new notation to write, and that is this bit here where we have it says find A, and it's between these two lines. Now those two lines just mean the magnitude of whatever's inside it. So this means the magnitude of A. And if we visualise what A would look like, I'm going to have a look at what the magnitude actually is in terms of a visual picture. So for A, it goes 3i and 4j. Now that means it goes 3 across, if we just pick any particular direction, and then it goes 4 up, obviously not drawing this to scale. So that's what our vector looks like. Now in terms of our starting point, we started over here and we finished up there. So our vector has actually gone in this direction that I'm drawing in with that green line. And as you can see, that forms a right-angled triangle. Now the topics that are going to be involved in this, obviously when we're looking at right-angled triangles, we can have either Pythagoras or potentially we could use some SOHCAHTOA. And if we want to find the length of that line, which is what the magnitude is in this case, the actual distance that we've travelled by going 3 across and 4 up, we're going to use Pythagoras to work that out. So we can draw a right angle in if we want, but ultimately if we're going to use Pythagoras to find this magnitude, we just need to go about using Pythagoras' theorem. So for part A here, we have a length of 3 and a length of 4. So we're going to do 3 squared plus 4 squared, and then we're going to square root our answer. Now, rather than doing this in 2 steps, let's just stick our square root right over the top, and there we go, we can stick that straight into the calculator, and we get the answer of 5. So the magnitude of the vector A is 5, or in other words, it travels an actual distance of 5 units, whatever those units may be. Now, for part B, it says find the exact value of, and exact there, giving us a hint that our answer is going to be in surd form, which we'll hopefully see in a sec, and it wants us to find the magnitude of 2a plus b. Now, it's completely up to you. If you want to find 2a plus b by writing these in column vector, like we went over in part 1, you can do, or you can just use your sort of mathematical logic here to get two a's together. So 2 lots of A, well if we deal with the i's to start with, we'll have 2 of these 3i's, that gives us 6i, and then we've got a b that we're going to add to that, and in that we've got negative 2i. So we've got 6i, take away 2i, and that's going to leave us with 4i, so that's going to go 4 across. Then we've got to do the j's, so if we do those separately, we've got 2 lots of the 4j, which is 8j, and then we're going to add to that the minus 4j over here, and that leaves us with 4j. So we have 4i plus 4j. So that is our vector 2a plus b. Of course, we're going to find the exact value of the magnitude of that vector. So for part B, we're going to take the same approach and we're going to use Pythagoras again. Again, you could draw a sketch of this 4 across 4 up, but once you get your head around this, hopefully you can avoid potentially having to draw some of these sketches when they are slightly easier like these ones here. So in terms of using Pythagoras, we know that that goes 4 across, so we'll do 4 squared, it goes 4 up, so we're going to do another 4 squared, and we're going to square root our answer. Now 4 squared plus 4 squared is 32, so we have the square root of 32, and to be fair, that is the exact value there, although when it comes to surds, we should always look to simplify them wherever possible, and considering you have a calculator for these questions, it's easy enough just to type it into the calculator, and it's 4 root 2. There we go, it's root 16 root 2, root 16 goes down to 4, so 4 root 2 there being our final answer, 4 root 2. So there we go, that's what we mean by the magnitude of a vector. Okay, so on to our last little bit here. It says in a triangle, PQR, P to Q is 4i plus j and P to R is 6i minus 8j. Find the size of the angle, QPR, in degrees to 1 decimal place. And it also wants us to find the area of the triangle. So let's go about drawing this. Now let's start with P, as both of these vectors are going from P. So let's call this point here P. Now the first vector there is going 4 across and 1 up, so let's just imagine that 1, 2, 3, 4 across, 1 up. So let's just imagine it's here. There we go, and we'll call that point Q. Now to find point R, that's going 6 across and 8 down. So let's do it again. 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6, 7, 8. Right, okay, there we go. Not to scale, but just to give us a general idea of what it looks like. And that is our point R. Now let's join these all together. So P to Q, Q to R, and R back up to P. There we go. So this wants us to find the size of angle QPR. So QPR is just over here, and again let's call that theta. There we go. And it wants us to find it in degrees to 1 decimal place. Now in order to find an angle within a triangle like this, as this is not necessarily a right angled triangle, we actually don't know, we can't really tell just by looking at it like that, we would need to use the cosine rule or potentially the sine rule. So we are going to involve another topic here, and again things like the sine and cosine rule I'll link in the description below just to make sure that you're nice and clued up on those if it's something that slipped your mind. So looking at this then, what sizes or what sides can we find the length of, or in other words the magnitude? Well, we can do that for P to Q, and we can do it from P to R. So let's start with one of them. Let's go for P to Q to start with. Now here's our little notation here. We've got 4i plus j, so we've got a distance of 4 and 1. So for P to Q, and let's write it in proper vector notation, let's find the magnitude of PQ. So we've got 4 squared plus 1 squared, and we're going to square root that. So 4 squared is 16, plus the 1 is 17, so we have the square root of 17. There we go. So the square root of 17 for our first one. For P to R, we have 6i minus 8j, so let's find the magnitude of P to R. Well, that's going to be 6 squared plus the 8 squared, and we're going to square root that again. Okay, so let's stop doing these in our head, let's get them typed in. So 6 squared plus 8 squared, square rooted, there we go, gives us the answer 10. One that we should know actually there, 36 and 64. So there we go, there is the length of 10. There we are. Now, have we got enough information to find the angle? Now, if we had the length Q to R, we could actually use the cosine rule, okay? But we don't have the length Q to R just yet. But actually looking at our diagram, it's not that difficult to find. There's two ways that we could do this. We could either take the vector P to R and take away the vector P to Q, or we could do it vice versa and just be very careful in the direction that we're going in. Or to be fair, we could just use a bit of a logical approach. Now to get from P to Q, we've had to go 4 to the right, if you remember drawing those dots. And we've got an extra 2 dots across to get from Q to R. So in order to do the vector from Q to R, we could actually just take this logical approach. If we've gone 4 across from P to Q and an extra then 2, obviously because we've gone 6 across to R, then we know that must have been 2i across. And we can take the same approach going down. From P to Q, we went up by 1, but from P to R, we went down by 8. So if we went up by 1 to get to Q, but down by 8 to get to R in total, that's going to have to go down by 9. So minus 9j. Now, you may not like that logical approach, so you don't have to use that. You can actually just take one of the vectors and subtract the other one. If you have a look, and let's just highlight it, the vector P to R, 6i minus 8j. If we do 6i, take away the 4i in the previous one, that leaves us with 2i. And if we do minus 8j, take away the 1j, that also leaves us with minus 9. So you can just take that approach as well, but I do think it is worthwhile just thinking about logically why you get the answer, and not just simply taking one away from the other and not really understanding why. But it is a nice little shortcut there to actually get these vectors when you're trying to find them. So there we go, we've got enough information now to also find the magnitude of Q to R. And we can take the same approach, just using Pythagoras again. So from Q to R, we can do the square root of 2 squared plus 9 squared. 2 squared is 4, 9 squared is 81, so that is 85, or the square root of 85. Right, so we've got all the side lengths now. All we need to do is go about actually finding this particular angle. So let's get rid of all of this working out. Now obviously we need our magnitudes there, so we'll have to leave those, or we can just draw that onto the diagram now, root 85, and we'll get rid of all that working out. There we go, so let's get rid of all of that and just work with our diagram.
Quite a lot working out up to this point, but to be fair, we've only had to use Pythagoras a few times, so nothing too bad. So to find the size of that angle, we obviously need to know the cosine rule. And obviously in this particular instance, we're looking at the cosine rule for the angle. So the cosine rule for the angle is going to be cos theta, and you do need to know these well. And we're going to do b squared plus c squared minus a squared all over 2bc, or whatever variation we're looking at. I'm treating theta as being our big A in this case. But let's go for it. 10 squared plus, we've got root 17 squared, which is just 17, but I'm going to write it in anyway, just to make sure we don't get confused with any of this. And then we're going to take away the root 85 squared, which again is just 85, but we'll write it all in as normal. And that's all over 2bc. So 2 times 10 times root 17. Now I'm going to do a little bit of a cheat here. Before I type that calculation in, I am just going to press Shift Cos and do the inverse straight away. So just a little step that I am skipping here. Rather than writing it all down, I'm just going to do the inverse straight away. So on the top then, 10 squared plus root 17 squared plus root 85 squared all over 2 times 10 times the square root of 17. There we go. Close your brackets on your calculator, and we should, let's have a look, if you type it in correctly, we should get 67.16. So there we go, our angle to one decimal place is going to be 67, it's 0.16, so 67.2 degrees. And again, just remember, I have skipped a step in my writing there just to reduce the amount of working out that's on our screen. So there we go, there is our angle, and the second part is asking us to find the area of the triangle. So we've got another bit of trigonometry coming in here. We're going to have to use half AB sine C. And just as a little tip here, I'm going to keep the original answer on my calculator, so the 67.16634,582. So if you're not going to keep that on your calculator, do make sure you have written down the full number there, because we don't want that to affect our area and part B. So for working out the area, we're going to do half AB sine C. Again, we now know the angle here, so we can get rid of theta. Oh, not the whole triangle there. We might be able to do it. There we go. And we can put the angle in. So 67, in fact, let's just write the whole angle in. 67.16634,582. And now we can do half AB sine C. So the area is going to be a half times our two adjacent sides there, so 10 times root 17 times sine of this angle, 67.16, and the rest of those decimals. I'm just going to use the answer button on my calculator. So 0.5 times 10 times root 17 times by the answer. And there we go. Obviously typed it in wrong, so we're going to have to go right back to the beginning and just retype that in just to get that full angle back. In fact, no, we've written it down, so we can actually go ahead and do it, and there is the benefit to writing the full angle down. If you do type something in wrong in your calculator, like I have just done, then you can go back and you can type it back in without having to worry about getting that full answer back on your calculator. So 67.16634,582. There we go, and there's our answer, and that comes out as 19. There we go. Obviously, we don't know what the units are here, so we could say 19 units squared, but I'm not going to worry too much just here when we're practicing on this one, but 19 units squared, whatever they are. Okay, so let's highlight that off, and there is our final answer. So just making sure that you're very careful with these. Obviously we had to involve the cosine rule to find an angle, we had magnitudes, we had obviously that bit of logical thinking to find that missing vector there from Q to R, and then also we had using half AB sine C, or our area of a triangle formula as well. Okay, so when it comes to geometric vector proofs, a lot of the proofs are very similar to those we've learnt at GCSE level. So I'm going to go through this one quite quickly, assuming that you have knowledge of vector proofs from GCSE. Again, if you're not sure, you can always check out the full video in the description on that, but otherwise we're going to have a look at this question. So it says OAB is a triangle, O to A is A, and O to B is B. It says the point M divides O to A in the ratio 2 to 1, and M to N is parallel to O to B at the bottom. So first things first, we should label those on our diagram. So O to A, and we'll put the direction in, is the vector A, and O to B is the vector B. Now what we can do is we can split that up into the ratio. So O to A was 2 to 1. So this is going to be 2/3 A for this part, and this part will be 1/3 A. Now for the first part of the question, it says express the vector O to N in terms of A and B. So we want to get from O at our starting point here all the way over to N. So we're going to look at some vectors to start with. Now moving from O to A is easy enough, but A to N is a little bit trickier. So we're going to need to look at this and think about the fact that M to N is parallel to O to B. And looking at O to B, which only has a B in its vector, means that M to N must be a fraction of B, so it won't have any A's in. That should help us to work it out. So the first vector we're going to find here is A to B. So if we look at the vector A to B, that means we're going to have to go from A down to O and then over to B. So that is going to be minus A plus B. And just to make that look a little bit neater, we'll write that as B minus A, just so we reduce our amount of negatives. Now on to the next part, we can think about how we get from A to N. Now we don't know what the ratio of A to N and N to B is, so we're going to have to use some algebra, or of course you can use lambda in this instance, but I'm going to use the letter X. So we're going to say that A to N is some amount of B minus A. And we're going to find out what X is. Now if that is the case, let's have a look at M to N and think about potentially what that fraction will have to be. So to get from M to N, we know that that is going to have to be a multiple of B. So if we were to expand this bracket, we would have to do A to N plus M to A. So M to A is already drawn on the diagram, that is 1/3 A. That gets us from the point M to the point A, and then we're going to add to that x lots of B minus x lots of A. Again, that's just the vector above here, but just expanded. So that would be xb minus xa. Now we need to just have a look at this, look at those A pieces. We've got 1/3 A minus xa. Now obviously in order to eliminate the A's there, that means that x has to be 1/3. So x will have to be 1/3, and that allows us to put our x in. So M to N is going to be 1/3 B. Obviously the A's there have just cancelled each other out. So now we have the vector M to N, we can get the vector O to N. So now we've got M to N, we need to think about how we get from A to N. Okay, so that's going to allow us to go from O to A using the vector A, and then down from A to N. Okay, so A to N we have already worked out. And if we just highlight that so we remember where it was this vector here, xb minus xa. Of course, we already know that x is 1/3, so we could write that A to N is equal to 1/3 B minus 1/3 A. And again, let's just write that a little bit clearer there. So that is 1/3 B minus 1/3 A. Okay, so that is A to N, and obviously we want to get from O to N. So O to N, if we were to write that in terms of the vectors, O to N is going to be equal to O to A plus A to N. There we go. Now we have both of those vectors. O to A is just the letter A, so that one is going to be A, and we're going to add to that A to N, which we've just worked out, and A to N is 1/3 B minus 1/3 A. There we go. And if we simplify all of that, that is going to be, let's just highlight what we have. We've got the A and minus 1/3 A, and that is going to go down to 2/3 A, which we can write first. So 2/3 A. And then we also have the 1/3 B, that's positive 1/3 B, so plus 1/3 B. So there we go, that is our vector. We have 2/3 A plus 1/3 B. Now we'll highlight that because that's finished, but of course you could factorise out 1/3, it doesn't ask us to, so it is fine to leave it in that form, but our final answer there is 2/3 A plus 1/3 B. Now for part B, it says show that A to N, N to B is in the ratio 1 to 2. So we're going to need a little bit more space for this, but in order to do this, we're going to think about some of these vectors. Now, if it is in the ratio 1 to 2, then we just need to think about some of these vectors that we've got. And we've already worked out the a to n, and we'll write that down just up here so we don't lose it, because I'm going to have to rub some of this off the screen. But a to n was equal to 1/3 b minus 1/3 a. So there we go. And we can also think about the overall vector of a to b, the full length of the line. Now a to b we wrote down at the very start, and that was b minus a, and we've got that just over here. So we're going to need that vector a to b, and we're going to need this vector a to n, and then we can think about the other portion of that and why it's going to be in this ratio. So if we get rid of some of this working out, and there's quite a lot of it, so let's just get rid of all of that, and now we can go about actually tackling this question. So we've got that a to n is 1/3 b minus 1/3 a, and the full vector a to b is b minus a. Now you can already see that a to n, if we were to factorise that, would be 1/3 of b minus a. So if the full line is b minus a to n is only 1/3 of that, then n to b will have to be 2/3 of the line, so that would be 2/3 of b minus a. Now ultimately what we have shown there is that a to n is 1/3 of the line and n to b is 2/3 of the line. So as a ratio of a to n, n to b, that has come out as a fraction which would be 1/3 to 2/3. And that is obviously can be divided by 1/3, and that is the ratio 1 to 2. So there we go, we have shown that that would have to be the ratio 1 to 2 by looking at the full length of the line and the first part of the line. Okay, so when it comes to modelling with vectors, the questions are quite in depth. Now some of the other questions that we've looked at are quite similar to this, but we're going to have to draw some bearing diagrams for this. So it says a man leaves a starting point O and walks 15 kilometres on a bearing of 120 degrees to reach A. So if we imagine that O is just over here by our question, and obviously with bearings we need to draw in our north line, then we need to think about what 120 degrees would look like. So it's a little bit past 90 and it would go down to here. We would then reach point A, so we should label this up and again draw in another north line. So this is going to be point A, and we've now got that this is 120 degrees. If we move on to our next piece of information, it then says from A he walks 9 kilometres on a bearing of 240 degrees to point B. So if he's standing at A, he's going to go 240, which goes past 180, but not past 270, so it's going to go somewhere down here. Now at the first point it said he walked 15 kilometres, this one was only 9, so it's not going to go too far, but again we are just drawing a sketch. So again, let's just write that in, make sure we have this all labelled nicely, and also we're going to want to show that that right there was 240 degrees. So we're getting there with our diagram. It then says in the final part of this that he then returns directly to O. So he's down here at point B and he's going to walk straight back to O. So as you can see, this has created a triangle. We could also put a north line in at B, but we'll see how much of this we're going to need in the question. Now looking at what we have here, we want to find the position vector O to A. Now that can also be phrased in a slightly different way. It could say the position vector of A relative to O, which just means starting at O and going to A. So if we're going to work this out, we need to think how we're going to get there. So in order to do a position vector, we want to know how far it's gone across and how far it's gone down. And if we think about that in terms of from O, we're going to go across, and let's do this in a different colour so we can see this. It goes across from O over to this north line, and then it's going to go down. Now by doing that I have created a right angled triangle. So we can use some trigonometry to figure out these lengths. So if I move this 15 kilometres and we just put that above the line, as that is going to be in our way a little bit, so we'll put that just below this line just here, as that was the 15 kilometre line, and now we can go about working this out. So for that particular line going across, we can use some SOHCAHTOA. Now that right angled triangle does split that 120 degree angle. As we are going perfectly to the right there, then that is going to be 90 just above it, which means that just in the triangle here, that would be 90 plus 30, which would make that add up to the 120. So if we use SOHCAHTOA, we can work out both of these lengths, and we'll write that using then I and j. So the length across the top of the triangle we would use cos for, as we have the hypotenuse and we're looking for the adjacent. So for this line just here on the top, we would actually do 15 cos 30. Again, you can slow this down a little bit and think about why it's 15 cos 30 there, but hopefully you're happy with your SOHCAHTOA. Onto the one going down, this is the opposite, so we will use sine as we already have the hypotenuse. The hypotenuse again is 15, so that would be 15 sine 30. So the distance is there, we could just type into our calculator. Now of course we're going to write this as a position vector, so for part A here, we would want to say that it is going to be 15, and then going across was the cos 30, so 15 cos 30, we can put that in a bracket if you want, I, and then we're going to take away from that as we are going downwards, 15 sine 30. So that's going to be 15 sine 30, and that is going to be a j. So if we type that into our calculator to work it out, 15 cos 30 to one decimal place comes out as 13.0, and that is going to be our vector I, and then we're going to go down by, and if we type in 15 sine 30, that comes out to one decimal place as 7.5, obviously, and that is going to be our vector j. So that is the first part of our question there. We have found the position vector O to A. Part B here asks us to work out the magnitude, but this time it asks us to work out from O to B. So if we go over and think about our triangle and think about how we would work that out. So if we're trying to work out the distance from O to B, we are looking at this line just here, and we want to work out the length of that line. So to work out the length of that line, we could use either sine rule or cosine rule. So if we look at what we have in the triangle at the moment, can we work out anything in this question? So we need to have an angle. Now what you will see in the green triangle that I have drawn, we already had a 30 degree, a 90 degree, and therefore this angle in the green triangle would have to be 60. And of course that bearing around A has to fully add up to 360. Now there's 240 on the outside, 60 just in here, so this angle inside the triangle will have to be 60 degrees as well. Now we can't actually get any of the other angles, but do we have any pairs of opposites? Do we have anything that we can use potentially with the cosine rule? Now we don't have any pairs of opposites, but we do have the angle, and we have the 15 and the 9 just next to it. So we'll be able to work out the length of that line using the cosine rule. So for part B here, to get the length of that line, O to B, which we can just say OB, so OB, we'll put that in brackets because that's squared, is going to be equal to A squared plus B squared, so 15 squared plus 9 squared, minus 2AB cos C, or depending on which way you write your cosine rule, but minus 2 times 15 times 9 cos 60. So if we type that in, we get that OB squared is equal to, and all of that simplifies down to 171. So there we go. To get OB, we would just have to square root our answer. So OB is going to be the square root of 171, which comes out as, and if we do it to one decimal place again, it comes out as 13.1 kilometers. And there we go, that is the length of O to B, or in this case we are calling that the magnitude of O to B. Again, they mean the same thing when we're looking at this vector. Okay, so if we move on to part C here, it says find the bearing of B from O. So if we're looking from O, to get down to B, we already have part of that angle. We have the 120 degrees leading up to the start of our triangle. The only thing that we're missing here is this angle here within this triangle. So if we call that theta, and we'll think about what we could use here. So in order to get the angle, again, we could use sine rule or cosine rule. Now let's label on this 13.1. Actually, instead of putting 13.1, let's put the exact value in, because we did round part B, so that is the square root of 171. Now, in order to work this out, let's just have a quick look and see if we can use the sine rule. And for this particular question, we have the length opposite the angle we're looking for, and opposite that root 171, we have the angle of 60. So for this question here, we can use the sine rule, so let's use that as it's a little bit quicker. So we've got sine theta, we're looking for the angle, so angle on top. Sine theta over 9 is going to be equal to, let's have a look, sine 60 over the square root of 171. Now if we rearrange that, multiplying both sides by 9, we get that sine theta, and let's just type that in on the top, 9 sine 60 over the square root of 171 comes out as 0.59. There's a few more decimals here, it is 6, but then there's a few more decimals. And in order to work this out now, we need to do the inverse, so we'll do sine minus 1 of the 0.59, again putting the full digits in there using your answer button, and it comes out as, and let's do it to one decimal place, that comes out as 36.6 degrees. So we've worked out the angle in the triangle there. There's quite a lot going on the page, but that angle just there is going to be 36.6 degrees. Now obviously the bearing is the overall angle, so we need to add that onto the 120. So to get the final bearing, we would do 120, and we've kind of run out of space here, so I'll put it over to here, 120 plus the 36.6, and that comes out as 156.6 degrees, and that would be our final answer there for part C. Okay, so on to our final part of this question, we've got part D. Now in order to answer this, we're going to need to get rid of a lot of this information, but it is very similar to part A. So if I get rid of a lot of this information, let's have a look. Okay, so now we've got a little bit more space, let's think about this diagram. Now we've still got quite a lot drawn on the diagram there, but if we just draw a little sketch of this triangle just to the side, and we'll imagine again that this is O, this is A, and this is B, and we can think about obviously what we need to do here. Now in order to get the position vector from O to B, again we're going to need to draw in a right angle triangle. So if we go across from O and then down to B, again it would form this right angle triangle. And all we need to do is think about one of the angles within that triangle, and we should hopefully be able to use SOHCAHTOA again to find our distances. So for this particular one here, let's not forget we already have the length of the hypotenuse, and that was the square root of 171. We then also need to figure out an angle, and if you look back in our diagram, we actually have this angle here. So for that particular angle there, obviously our right angle triangle goes just above it, but we already know that that's an angle of 30 degrees, plus we have the 36.6 degrees, so the full angle within the triangle just there would have to be 36.6 plus the 30, which comes out as 66.6. So the angle within the triangle, and again you could always just draw that triangle separately to the side, but what we have is a length of 171, and we have an angle of 66.6. Now what I'm going to do for this one, I'm just going to round that to 67. You could keep it accurate to be fair, and you could write 66.6. Either one of those is absolutely fine. So in order to work through this, again we're going to write our vectors in terms of I and j. So to get from O to B, we would have to do, let's just have a think about this. For I, we want to work out this length just here. Now in regards to the angle, we have the hypotenuse and we are working out the adjacent, so we're going to use cos. So we're going to do the hypotenuse, which is the square root of 171, cos of the angle, which is 66.6. And if we type that in, the square root of 171, and then cos 66.6 comes out as 5.19. So that is going to be 5.19. So we'll write this in, and we'll just write it straight in as we've done the working out just on the diagram there. So for I, we would have, and let's just put it below where I've drawn the OB, we would have 5.2, if I round that to one decimal place, I, and then we are going down, so we're going to minus j here. To work out j, this length just here, again, we are going to use sine. So for sine for that one, we can use root 171 sine of the angle, so 66.6. And if we type that into our calculator, root 171, and all I'm going to do is get rid of cos, replace it with sine, and press equals, and we get 12.00. So for that one there, again, we'll just write this in, so that would be 12.0 to 1 decimal place, and that would go with our j. So there is our answer, 5.2i minus 12.0j. Of course, that could come out slightly differently if you use rounded answers. So if you had used the rounded version of root 171, which came out as 13.1 kilometers, or if you used the rounded version of 66.6 and you instead used 67, you would get a slightly different answer. But that is an overview question that covers a lot of modelling with vectors.
So when it comes to differentiation, essentially what we're actually doing is we are finding an expression that allows us to get the gradient at a point on a curve, okay, the gradient of the tangent to the point of the curve. So with this particular graph that I've got on the screen, this is the graph of y equals x squared. Okay, now if we find any point on this curve, so let's go for this one here. Normally, and particularly at GCSE level, what we'd have done is we would have drawn in a tangent as best as we could, and then we'd have worked out the gradient of that by doing change in y over change in x. So we'd have drawn a little triangle in, we'd have got our rise over our run, our change in y over change in x, and we'd have used that to find out an estimate for the gradient. Now when it comes to differentiation, the process is quite simple. All we actually do, and we write dy over dx, which kind of just stands for the difference in y divided by the difference in x. Like we do at GCSE, we do change in y over change in x. Okay, but obviously we're actually trying to find the expression for it rather than a numerical value. And it's quite simple. All that you actually do is you have a look at what the power is, and the power here is 2. We multiply that by the coefficient of x that's before it. Now the coefficient of x squared is 1 at the moment, so 1 times 2 gives us 2. Okay, and then we reduce this power here by 1, so it's currently a power of 2, and that just goes down to a power of 1, so it's 2x to the power of 1, and obviously when we have a power of 1 we don't need to write it. So there we go, for a nice simple graph like x squared, that would be our expression. That is our value of dy over dx there, 2x, and we can use that to find out the gradient at that point on a curve, and we're going to look at all of these steps as we move along, but here's a bit of an overview on a nice simple one. If I wanted to find the gradient at that point there that we've already highlighted, that has an x coordinate of 2. Okay, so we take 2 and we'd sub it in, and when x equals 2, 2x or dy over dx equals 2 lots of 2, or 2 times 2, which is 4. So the gradient at that point would equal 4. Now these are all the things that we're going to have a look at throughout this video. We're going to have a look at obviously differentiating much harder graph equations than this one, and then we're going to have a look at subbing some values in to work out the value at those particular points. Okay, but that's a bit of an overview of what we're going to look at and the process that we're going to go through, obviously, if you've never seen differentiation before, but it's quite nice and simple. Multiply the coefficient by the power and reduce the power by 1. That is pretty much all we're going to need to do. So let's not forget our little formula that we're going to use, which is the function of f of x plus h, take away the function of x, and that's all going to be divided by h. So that's the formula there that you're going to use. Okay, in this particular question, our function of x is 5x squared, and we're going to show that it goes down to 10x. So there we go. Obviously, if you're going to have a go, pause the video there and see what you get. But otherwise, let's carry on with this question. Okay, so this time our function of x is 5x squared. So we've got a little bit more working out when we put this piece in here, because obviously we've got the first piece to work out, which is where we're going to work out the function of x plus h. And if we sub x plus h into 5x squared, we're going to get this. We get 5 lots of x plus h, and that's going to be squared. And then we're going to take away the function of x, which in this case is 5x squared. And again, that's all going to be over h. So there's our pieces subbed into the formula there. Now we just need to simplify it all down and see what we get. So if we expand that double bracket x plus h squared, we've got 5 lots of that, so we'll sort that out in a sec. But if we expand that out, we get the same as before. We get x squared plus 2xh plus h squared. And then we're going to take away 5x squared and again divide it all by h. Now we can go about multiplying everything in this bracket here by 5. So we end up with 5x squared plus 5 lots of 2xh is 10xh. And then 5 lots of h squared will give us 5h squared. And then again we've got minus 5x squared at the end. And again all over h. Okay, so we've got 2 pieces that cancel each other out. They've got the 5x squared and the minus 5x squared. So if we get rid of those, what have we got left? We'll have 10xh plus 5h squared all over h. We can divide the top and bottom by h there. So the h will disappear off the 10xh, so we get 10x. One of the h's is going to disappear off the 5h squared, so 5h. And there we go, there's our final piece. Now again, we're going to say as the limit of h approaches 0, we're going to change that h for a 0, so what we end up with is 10x plus 5 lots of 0, which is just plus 0. And obviously you don't need to write plus 0, so we can just get rid of that. And we just end up with this 10x piece, which is exactly what we're looking for. And there we go, there's our final answer. So let's just highlight that. And there we go, that's how we go about that question. Part of the process, look, we've got y equals 5x squared minus 3x plus 7. Find the value of dy over dx when x equals 1. Well, that's okay, because all we have to do is differentiate and then substitute this value of 1 in. Now, it doesn't ask it in this question, but that is what we're doing. We are finding the gradient of the tangent at that point where x equals 1. But obviously, we're not going to have a look at the graphical element or aspect of it just yet. We're just going to focus on part of the process, and obviously some of these are just mathematical processes at the moment. So for that first one up there, times the 5 by 2 gives us 10, so we get 10 x, and the power gets reduced to 1. And then for the next bit, we have minus 3, and that power of x there is going to disappear. So we have 10x minus 3. And let's just label that. So dy over dx equals 10x minus 3. So when x is 1, all we need to do is substitute 1 in. So when x equals 1, we are going to get 10 times 1 minus 3, okay, which equals 10 minus 3, which equals 7. There we go. So that is our value there when x equals 1. There we go, so quite nice and simple, hopefully. Okay, so this one here does look a lot nastier than the last one we just looked at, and that's primarily because we have this root x here. Now obviously remember, when you have a root, there's another way of writing that as a power, and that is that the square root of x is also equal to x to the power of a half. So don't be put off by a square root, it shouldn't throw you at all. It's just that we're going to write it in a slightly different way. And if we go about actually writing that, instead of writing it like that, let's write it as 9x to the power of 4, take away 4x to the power of a half, divided by x squared. There we go. So that shouldn't really put us off, and now we can obviously get this into a single line, because we can look at obviously subtracting this power of x from the one on the top. And if we do that, let's see what we get. We get 9x to the power of 4, take away. Now technically there's a 1 in front of the x squared, so 4 divided by 1 is still 4. And we're still going to have an x, and we've got to do a half take away 2. Now obviously just a little thing here, obviously you can type that into your calculator, but 2 as a power, in terms of halves, 2 is 4 halves. So we're taking away 4 halves from the 1 half, and that leaves us with negative 3 halves, or 3 over 2. So there we go, that's obviously now written as a single line, obviously just subtracting the powers there when doing that division. And now we can go about actually differentiating this. So we get dy over dx, and that's going to equal, and let's have a look, 9 times the 4 is 36x, reduce that down to a power of 3, and then we have negative 3 halves times negative 4 at the front. So that's going to become positive, because we've got negative 4 there, and we're going to times by that negative power, and that's going to become 12 over 2. 4 times 3 is 12 over 2, and that's going to be x. And if we subtract 1 from that power now, that's going to go down to minus 5 over 2. And there we go, just taking away 1 from negative 3 over 2. Or in essence, taking away another 1 equals 2 halves. Okay, so taking away another 2 halves from that power. Obviously you can type some of these into your calculator, but there we go, we should be able to hopefully do some of these without a calculator. Now there's obviously one thing to sort out, and that again is that 12 over 2 there, and 12 over 2 is a whole number, it's 6, so we would write that as 6 there rather than 12 over 2. So if we put that in instead, and there we go, there is that differentiated. Okay, so hopefully just a few little questions there that just show you obviously not to be put off by some of these questions. Sometimes they don't look the nicest, but it's all about getting it into that straight line there, and obviously just being very careful with your powers when you multiply them by the coefficient and then reducing it by 1.
Okay, so when we are finding equations of normals, we just need to remember that a normal is perpendicular to the tangent at a particular point. So in order to find the equation of the normal, we need to find the equation of the gradient of the tangent, then we can find the gradient of the normal, and then we can find the equation of that line. So if we go about this, in order to find the gradient of the tangent, we'll first differentiate our equation. So if we differentiate this equation, we're going to find dy by dx. Now in order to find dy by dx, that's quite nice and easy for this particular equation. Multiplying the x in the coefficient by 2 would give us 2, decreasing the power just gives us a power of 1. Then doing the same with the negative 5x over there would just give us negative 5. So we have done differentiating that equation. Now we can substitute in our coordinates, and it asks us to use the coordinate 6, 6. So if we put in the value when x equals 6, we get a gradient, which I'm going to label as m, and our gradient comes out as 12 minus 5, so our gradient is 7. For our perpendicular gradient, which will be the gradient of the normal, we just do our negative reciprocal, so the gradient of the normal will be negative 1 over 7. Now we have the gradient of the normal, we can just put it into the equation of a line. So if we use y minus y1, so y minus the y coordinate of 6 is going to be equal to negative 1 over 7 multiplied by x minus x1, so x minus 6. We'll expand that bracket out, so we have y minus 6 is going to be equal to negative 1 over 7x plus 6 times the 7th is 6 over 7. Now it doesn't say what form it wants this equation in, so it's best that we get rid of the fraction. So if we just multiply everything by 7 on the left and the right, that will give us quite a nice equation to move around. So that would be 7y minus 42 will be equal to negative 1x plus 6. Now we may as well just move everything to the left hand side as it doesn't specify. So if we add the x over, we'll have 7y, and then add the x next to that would be plus x, and then at the end we've got to take away 6 from both sides, so we'd have negative 48, and that is equal to 0. Now of course you can write that equation in any form you like for this particular question as it doesn't specify, but that's probably the easiest way to do that. So when it comes to looking at normals, don't forget you have to differentiate to find the gradient of the tangent, and then use your negative reciprocal for the gradient of the normal. Okay, so when we're looking at increasing and decreasing functions, we're going to want to differentiate the function. Now instead of writing dy by dx, we'll write f dash of x to do our differentiation here, just another way of writing dy by dx. So if we differentiate this function, and we're just looking at this one here, we'll start with the 2x cubed, so that becomes 6x squared. We'll then move on to the negative 15x squared, which becomes negative 30x. And then moving on to the final piece, that just becomes 36. So that'll be plus 36 at the end, and we have found our differentiated function. Now, in order to find when this is increasing, which is what this question is asked, we're going to find whereby this differentiated function is greater than or equal to 0. So if we just write it as an inequality, when is 6x squared minus 30x plus 36, when is that greater than or equal to 0? Again, don't forget that just means when is the gradient going to be bigger than 0? Or in other words, when is it sloping upwards? So in order to solve this, we need to just solve it as a quadratic inequality. This one does simplify, so all of those pieces divide by 6. So we can make it a little bit easier to simplify by doing that. And if we divide everything by 6, we get x squared minus 5x plus 6. And we're just trying to find where that's greater than or equal to 0. So if we factorise that, we get x minus 3 and x minus 2. Again in either order. And again we're looking at when that is greater than or equal to 0. So we've got our two solutions, x is equal to 3 and x is equal to 2. And then as this is a quadratic inequality, we'll just quickly imagine what the curve looks like. It goes through 2 and 3. So 2 here, 3 here. We are looking at when it is greater than 0. So we have this part and this part of the curve. And therefore that's going to be when x is less than or equal to 2, and also when x is greater than or equal to 3. So there we go, there are our two solutions. They are the intervals for when this function is increasing. Okay, so when we're looking at our second derivative, we just need to differentiate and then differentiate again. So at the moment, y is equal to the square root of x minus 3 over x squared. Now again, thinking about indices here, we just want to write this in a different way. So instead of writing it like that, let's change the root x to x to the power of a half, and let's change the minus 3 over x squared to 3x to the power of negative 2. That makes it easier for us now to differentiate. So if we find our first differential, we're just going to multiply the coefficient by the power and decrease the power by 1. So that becomes 9 times a half, which we can just write as 9 over 2, x to the power of minus a half when we take away 1. We've then got negative 3 times negative 2, so that becomes plus 6, and x to the power of negative 3. So there's our first differential. To find our second differential, which we write as d squared y over dx squared, then we just have to differentiate this once more. So 9 over 2 times negative a half becomes negative 9 over 4. Again, that's to x, and if we decrease that power by 1, it becomes negative 3 over 2. We then have 6 times negative 3, which becomes negative 18, and again then that is going to be x to the negative 4 when we decrease the power by 1. So there we go, that is called our second differential, and we're going to use that to find rates of change. But there we go, that's all you need to do. You just need to differentiate and differentiate again. Okay, so when we are looking for the coordinates of a stationary point on a curve, we are going to have a look at the point whereby the gradient is 0. So if we were to draw any basic curve, and let's just think about a quadratic, then we have this point right down the bottom whereby the gradient is equal to 0. And if I was to draw a tangent at that point, the gradient of that tangent would have a gradient of 0. So that's what we're looking at when we're finding stationary points, but of course we have more curves than just a quadratic. So when we go about doing this, what we are going to do is differentiate the equation, and then we will just set it equal to 0 and see what coordinates that becomes. So we're looking at this equation to start with, and then we'll have a look at the nature of the stationary points using our second derivative. But to start with, let's differentiate this. So if we do dy by dx, and again we've got lots of differentiation here, but that just becomes 6x squared minus 30x and then plus 24. So again we just need to solve this, as we are going to look when that is equal to 0. You could write that all out again. I'm just going to put equals 0 over here just to avoid writing it down lots of times. Now the first thing I notice is that everything divides by 6. So if we divide both sides of this by 6, it's going to make it easier to factorise. So we have x squared minus 5x plus 4 is equal to 0. And if we factorise that, we get x minus 4 and x minus 1. So we've solved that for when it is equal to 0. That gives us two x coordinates, an x coordinate of 4 and an x coordinate of 1. Now we just want to find the y coordinate for those, as we are finding an actual coordinate here. So if we look when x is equal to 4, all we're going to do is substitute 4 into our equation. So if we put 4 into there, and you can do that on a calculator, 2 times 4 cubed minus 15 times 4 squared plus 24 times 4 and then plus 6. And if we substitute that in, we get a y value which is equal to negative 10. So our coordinate there is going to be 4 and negative 10. If we do the same for when x is equal to 1, again we're going to get a y value. So we're going to want to put x is equal to 1 into our original equation that says y equals. Now if we substitute that in, again doing 2 times 1 cubed, take away 15 times 1 squared, plus 24 times 1, plus 6, we get a y coordinate that is equal to 17. And again that gives us then a coordinate of 1 and 17. So these are the coordinates of the stationary points. They are the points at which on our curve there is a gradient of 0. Now when we're looking at using the second derivative to determine the nature of the stationary points, we're going to find whether there is a local minimum point or a local maximum point. So first things first, we need to find the second derivative. So for this one that we've already differentiated, the first derivative, we're going to find d squared y over dx squared, and that becomes
Let's have a look. 2 times 6 is 12, so 12x, and then just minus 30. So that's our second derivative. We'll just take our x coordinates and substitute them in. So when x is equal to 1, the second derivative, dx squared minus, d squared y over dx squared, is equal to negative 18. Now, if that number is less than 0, it is a local maximum point. So at the coordinate 117, that is a local maximum point. And we'll just write that down. Local maximum point. We're going to do the same with the other x coordinate and see what we get for that. So when x is equal to, and where was the other x coordinate? 4. When x is equal to 4, d squared y over dx squared is equal to, and that comes out as positive 18. So when it is greater than 0, it is a local minimum point. So, and I should have added over here that this one was less than 0, this one is going to be greater than 0. So when it's greater than 0, this coordinate here, 4 and negative 10, is a local minimum point. There we go, local minimum point. So there we go, there's our answers. Because the second derivative was less than 0, when x was 1, 117 was a local maximum point, and for x equals 4, we got 18, which was greater than 0, so 4 and negative 10 was a local minimum point. Okay, so when we're having a look at modelling with differentiation, we're going to use a lot of the skills that we've already looked at. So this question here says a car is driven from Edinburgh to Manchester. The cost of the journey is in £C when the car is driven at a steady speed of v kilometres per hour. It says it's modelled here, so the cost is equal to 1,500 v, 1,500 over v plus 2/11, or 2v over 11, plus 60. So this is our model just here, and then it asks us to do a few things. So the first thing that it asks us to do is find, according to the model, the value of v that minimises the cost of the journey. So if we want to find the minimum point or the minimum cost of the journey here, then we're going to want to differentiate this model. And if we differentiate the model, we can set it equal to 0 to find that point where the gradient is 0. And if we imagine what this would look like in terms of a graph, if we were to draw a little sketch of this, as it is 1,500 over v, is a reciprocal graph. Now we have the plus 60 at the end, so it hasn't been raised or translated upwards, so it wouldn't be that close to the x-axis, but if we were to draw a little sketch, it would look something like this. And again, that's moved up 60 on the left. And if we think about where the minimum point is, it's going to be as it approaches 0. So it'd be somewhere down here, and if we were to draw a gradient there, then we would have a gradient of 0. So that's what we're finding, that kind of minimum point there on the reciprocal graph. So if we go about actually trying to find that, then we just need to differentiate our model. So if we differentiate and it's c equals, so we will differentiate c with respect to v. And to do that, first of all, we probably want to write this in a slightly different way. So let's write that c is equal to 1,500, it's v on the bottom on its own, so v to the minus 1, plus, and then we have 2/11 v, which we could write as just 2/11 v, and then plus 60. So if we go ahead and differentiate that, negative 1 times the 1,500 is minus 1,500 v. The v is going to go down to a minus 2, plus, and then 2/11 times 1 is just 2 over 11. The v goes down to a power of 0, so we end up with just 2 over 11. So this is our differentiated part here, and again we want to set that equal to 0. So we should write that as a new line, but just to save a bit of space here, we'll set it equal to 0 just there. Now we want to go about solving this, so we want it to say v equals. So if we minus the 2/11 to the other side, we'll have 1,500 v to the minus 2, which is equal to negative 2 over 11.
That's our first step there. Again, it might just help here to rewrite negative 1500v to the minus 2. Again, you don't really necessarily have to. You could take different steps or different approaches here, but I'm going to rewrite this back to 1500 over v squared, which is equal to the 2 over 11. So that's equal to a negative 2 over 11. That is technically negative over here and negative 2 over 11 here. Now what we can do is times both sides by negative 1. That's going to get rid of these negatives. So I could just go and erase them, but let's write the whole thing out. So 1500 over v squared is equal to positive 2 over 11. So that's the next step. Now we want to get it to say v squared. So if we move the v squared to the right and divide by 2/11, then we'll know what v squared is equal to. So multiplying the v squared over 1500 equals 2/11 v squared. And now I can divide by 2 over 11, which just leaves me with v squared being equal to, typing that in on your calculator, gets you 8250. And now for our final step, we just need to write our answer to square root v and square root 8250, which gives us 90.829, quite a lot of decimals here, 8295 and a few more decimals, but of course v is talking about a speed as mentioned in the question, so speeds we would just give to an appropriate degree of accuracy. So v as a speed, it would be fine to say 90.8 kilometers per hour. So there we go, that would be a value of v that minimises the cost of the journey. So now we have that, we're going to have a look at finding the actual minimum cost of the journey. Okay, so for part 2, where we're finding the minimum cost of the journey, we're going to obviously want to keep this minimum speed. So if we get rid of everything on the screen, but we'll keep that minimum speed, and we'll move that up so we can keep that answer. Okay, so I've kept my answer, and I've also kept the full rounded decimal. So I'm going to keep that answer just up here so that we don't lose that, and I've kept the full rounded answer there because that's the number we're going to use if we are going to use this number. So putting this into our cost equation there, it says that the cost is equal to 1500 over v, so I would do that the cost is equal to 1500 over my full decimal there, 90.8295, and I'm going to add that to 2v over 11, so 2 lots of 90.8295 all over 11 plus 60. So I just need to type that into my calculator, and if you type that into your calculator you get a cost that comes out as 93.0289 as our cost. So if we round that to the nearest penny, as the cost is in pounds, that would come out as £93 and 3 pence. And that would be our answer there for the minimum cost of the journey. Okay, so moving on to part B, it says prove by using the second derivative that cost is minimised at the speed found in part AI. So we don't actually need this cost here for the second part of our question, so let's get rid of all of this, but we will keep our answer there for part 2, and we'll just keep it up there, and we'll get rid of the rest of our working. Okay, so now we've got rid of that, we can have a look at part B. So if we're going to find the second derivative, we do actually need that first derivative so that we can actually use it. Now the first derivative from earlier in the question, let's have a look, was dc over dv, and I'm going to have to differentiate that again because I've forgotten what it was, but it was negative 1500 v to the minus 2, and then it was plus 2 over 11. So if we're going to find the second derivative, so d squared c over dv squared, then we're going to want to just do the same again. So multiplying negative 1500 by negative 2 gives us positive 3000, and that becomes v to the minus 3. 2 over 11 is gone, so that is our second derivative. Now as it is v to the minus 3, that could be written as 3000 over v cubed. And you can write this either way, but I do like to rewrite it as the fraction when we can. So for this question here, the value of v that we got in part AI was the 90.8295. So what we're going to do is substitute that into our second derivative. So 3000 divided by 0.9825 cubed, there we go, and if you type that into your calculator you get the answer and it comes out as 0.040035. There's some more decimals there, but of course we're looking here whether it is a local minimum or a local maximum point. Now this number here is greater than 0, so we would write therefore it is a minimum cost because as 0.040035 is greater than 0, and you could even put therefore it is a local minimum point. Okay, so let's have a look at the last part of this question. So part C here says state one limitation of this model. Now this is where we're going to be thinking about real life, and this question here is about driving a car. And of course what we worked out is that in order to achieve our minimum cost we would have to drive at 90.8 kilometers per hour for a steady speed for our entire journey. Now in real life that's not necessarily possible for us to do, so we would write for a limitation it would be very difficult for us to drive at 90.8 kilometers per hour for an entire journey. So I'm not going to write that down, but just a discussion there, that would be the limitation of our model, that it would be near enough impossible for us to drive at a steady speed of 90.8 kilometers per hour for our entire journey. When we looked at differentiation, we looked at this particular graph, and this is the graph of y equals x squared. So we had a look at this and we had a look at how to differentiate that. And when we differentiate it, okay, we multiply the coefficient of x there by the power. Okay, so when we differentiate it, we wrote it like this, dy over dx. There we go, and we multiply the coefficient of x there, which is 1, so we multiply that by 2, so we've got 2x, and then we reduce the power by 1, so we reduce that power of 2 down to a power of 1, and we got this here, 2x. Now when we're looking at integrating, we're essentially looking at doing the complete opposite here. We're just going to reverse this process. So instead of multiplying the coefficient and reducing the power, we're essentially going to increase the power and divide the coefficient. And when we write this out, we write it out like this. Okay, and this little symbol here, which I'm going to have better in a second, but it looks something like that. We say to do the opposite, that means integrate. We put in the bracket what we want to integrate, which in this case is 2x, and then we say dx after that, just means with respect to x. So that just means obviously do the opposite. That means integrate 2x with respect to x, and we're going to look at how we go about actually doing that. So obviously, as we've said, we're going to increase the power. So at the moment, that power of 2x there, the power of x is a power of 1. So if we increase that, it becomes 2x squared. And then rather than multiplying by that coefficient, we're now going to divide by that. Sorry, rather than multiplying the coefficient by that power, we're going to divide the coefficient by that power. And the power is 2, so we're going to divide it by 2. And you'll see when we do 2x squared divided by 2, we get back to that original x squared that we had up the top there. Okay. Now the problem with this is, and obviously this isn't going to be the final answer here, the problem with this is that there's quite a lot of different graph equations here that are going to give us 2x when we differentiate it. So if I have a look at another example up here, we could have y equals, and let's just imagine it's x squared plus 5. Now when we differentiate that, obviously we multiply the x squared by the coefficient by 2, and we get 2x. So when we differentiate it, we get 2x, and the 5 then disappears, so that gives us 2x as well. Likewise, we could have something like y equals x squared minus 19. When we differentiate that, multiply the x squared by 2, reduce the power, you get 2x, and the 19 disappears. So again, we get 2x. So the problem here with the integration is that we don't actually know what that constant is at the end, what that number is at the end. And because of that, we have to add something onto our answer when we're integrating, and that is that we have to put plus c at the end, and that is called our constant of integration. Again, that just obviously says that we don't actually know what the constant is, so we always have to put plus c at the end, and that's going to be absolutely essential as we move through this video. Every time we integrate, we're going to have to put that plus c at the end because we just don't know what that constant was unless we have any specific values on our graph. And obviously with the x squared graph, that's quite a nice one, but let's just imagine
just to sort of give you an overview of everything we're going to be looking at. If I imagine that I say, okay, well on this particular graph that we've just integrated, so this x squared plus c, we have an x and a y value. Let's imagine we say, okay, well y equals 5 when x equals 2. Okay, so if y equals 5 when x equals 2, what is that equation going to be? Well, if we sub those values in, x squared is going to be 4, so that would be 4 plus c, and that has to equal 5. So we know in that case there, c would have to equal 1, and the equation of this line in particular would be x squared plus 1, or y equals x squared plus 1. Okay, so something here that looks a lot more complicated, and let's see how we go about this one. So we've got these three pieces that we're going to integrate this time. So we're going to start off with this 12x cubed. So again, we're going to increase the power. So we have 12x to the power of 4, and then we're going to divide by that new power, so divide by 4. Then we're going to add to that. We've got 6x, so that's going to go up to 6x squared, and then we're going to divide by that new power, which is 2. And then we're going to take away, and this one's not as nice here because we've got a power of 2/3 there, but we have 15x, and we need to figure out what that power is going to be. So we need to add 1 to 2/3. Well, 1 in terms of thirds is 3/3, so if we add 3/3 to 2/3, we get 5/3. There we go, and that's not a 5, so let's rewrite that. We get 5/3. There we go. So 15x to the power of 5/3, and then we need to divide by that new power. So we're dividing by 5/3, not very nice there. There we go, but divide by 5/3. And then at the end of that, plus c, okay, because we don't know what that constant would have been at the end. But there we go, we just need to simplify this all down, see what we get. These first two look okay. We've got 12 divided by 4, which is 3, so that's quite nice. We get 3x to the power of 4 for the first bit. The next bit, we've got 6 divided by 2, which is 3 again, so 3x squared. And then this bit isn't so nice here. You've got 15x to the power of 5/3 divided by 5/3. And obviously, if you've got your calculator, obviously you can work this out quite nice and easy. But don't forget, it's not too difficult just to do 15 over 1 divided by 5/3. So times it by the flip version, 3/5. And there you go, that equals 45 on the top over 5, which is 9. There we go, so 15 divided by 5/3 is 9. Just a nice little bit of working out there, obviously not always having to rely on your calculator if you've got some nice quick working out that you can do. So there we go, take away, that becomes 9x to the power of 5/3. There we go, and not forgetting plus c at the end. There we go. And there we go, that's that integrated, okay? Not forgetting that plus c again, that's so important. Obviously something that's obviously new with this, even though we're doing the reverse process of differentiating, that plus c there is so important to make sure that you add on the end. But there we go, that's again how we're going to integrate. So increase the power by 1, divide by that new power, and then simplify all your terms and just watch out for any sort of complications when you've got fractions in the powers there, and just being careful with that. Okay, so this question here looks very similar to one we looked at earlier in the video. We've got dy over dx equals x squared plus 5 in brackets squared all over x squared, where x cannot equal 0. Obviously we can't divide by 0, so we can't have x is 0 on the bottom. And it says given that y equals 13 and x equals 1, find y in terms of x, giving each term in its simplest form. So obviously you've got a few little bits to sort out here. You've got a bracket on the top that needs expanding. You're going to have to turn this into a single line, so dividing all of those pieces by x squared and getting those obviously rewritten. But obviously you need to get that into a single line, integrate it, sub these values in, find that value of c. So have a go, see if you can get this question done, see how far you can get. We'll go over the answer in a sec, so pause the video there and have a go. Right, okay, so we need to sort out what's on the top to start with them. So x squared plus 5, obviously squared means we've got to do a double bracket, so we have x squared plus 5 and another x squared plus 5. There we go, so if we expand this all out, we get x to the power of 4, and then we get plus 5x squared plus another 5x squared, so that's plus 10x squared. There we go, and then 5 times 5, we get plus 25. So that's what we've got on the top, and that's all being divided by x squared. So obviously we just need to then divide all of these powers by x squared. It's actually not too bad if you've obviously got to this point already. The first piece there, x to the power of 4 divided by x squared. Well, I'll subtract the powers, we get x squared. There we are, the next piece, 10x squared divided by x squared is just 10, so plus 10. And then the last piece there, 25 divided by x squared. Well, subtract the power from x to the power of 0, gives x to the power of minus 2. So we get 25x to the minus 2. There we go. And now it's at a point where we can actually integrate it. So if we bring this up and integrate that, let's see what we get. So x squared, well, we'll obviously increase the power, so we get x cubed divided by 3. There we are. plus 10x, increasing the power of x there. Obviously there's no x before, so we'll introduce the x. And then for the last piece there, if we increase the power, it goes to minus 1. So we get 25x to the minus 1 divided by the minus 1. And then we get plus c at the end. Right, okay, so nearly done. We obviously just need to simplify this down. So we get at the start there, we can obviously write it as a third if you want. You've got 1 in front of the x cubed there. So we've got 1/3 x cubed plus 10x. And then we have 25 divided by minus 1, so it becomes minus 25x to the minus 1 plus c. And now we can go about subbing these values in. So it says over here, y equals 13 at the point where x equals 1. So if we obviously write this as an equation now, let's just get rid of this because we could have put our y equals at the start of that one. Obviously have decided not to as we were integrating it at that point, but now we're looking at it in terms of y equals y in terms of x. We can write that out. So we've got minus 13 is equal to 1/3 times 1 cubed, so 1/3 times 1, which is just 1/3. You can put the 1 in if you want, let's just write that in anyway, 1 cubed, plus, then we've got 10 lots of 1, which is just 10, take away 25 lots of 1 to the power of minus 1. There we go, 1 to the power of minus 1. You can put in the bracket, and then plus c. Right, so simplifying this down then, we've got minus 13 at the start obviously, equals, and we have 1/3 times 1, which is 1/3, plus 10 times 1, which is 10, take away 25, and then 1 to the power of anything is 1, so it's just take away 25 plus c. Obviously we just need to simplify this little bit down and see what we get. So we've got 1/3 plus 10 take away 25. Alright, so if we work that out then, we've got minus 13 equals 10 take away 25 is minus 15. Add the third to that is minus 14 2/3. There we go, 14 2/3. Obviously you can check that on the calculator, but there we go, minus 14 2/3 plus c. So not the nicest here. How do we get from minus 14 2/3 to minus 13? Well, we're going to have to add in those extra 2/3 to get back to minus 14, and then add an extra 1, which is 3/3. So there's 5/3 there that we need to add for c. So our value of c is going to be 5/3. There we go, that would have to be 5/3, there we go. Obviously you could add 14 2/3 to negative 13 there, and you'll get your 5/3, or 1 2/3. There we go, there's our value of c, and obviously to finish this off we just need to plug it back into the original equation up there for our value of c. So for our final answer here, let's just write this up here, we get y equals 1/3 x cubed plus 10x minus 25x to the minus 1, and then plus 5/3. There we go. And obviously you could write that as a decimal as well if you wanted, but obviously when it comes to thirds I tend to just leave it as a fraction rather than having any recurring decimals in there. But there we go, there's our final answer. Okay, so when having a look at definite integrals, let's have a look at the process for going about that. So this particular question, first of all we need to integrate 2x minus 3 root x. Now again I'm going to write that in a slightly different way. I'm going to write the root x as x to the power of a half. So I'm going to write this as 2x minus 3x to the power of a half. Now to start with, all we're going to do is integrate here. So if we integrate that, we will have, and let's just have a look at what we get. We get 2x squared over 2, and then increasing the power there for the power of a half, we get 3x to the power of 3 over 2, and we're going to divide that by 3 over 2. Now at this point here you are okay to simplify this, so we'll simplify this a little bit. Now you don't have to because we're going to type this into a calculator anyway when we go about this, but we can simplify that. So the first piece there, if we divide that by 2 we get x squared, and for the second piece when we divide that by 3 over 2 we get 2x to the power of 3 over 2. So now we have integrated it, what we are going to do is do a definite integral. So for this, what we are going to do is we are going to substitute the number 9, the first number on the top of the integral. We're going to substitute the number 1 in, and we're going to subtract them away from each other. So when we write this, we put our integrated piece into a squared bracket,
And you will also notice that I haven't put the plus c on the end. Now you're going to see here why I haven't put the plus c, so we'll come back to that in just a second. So the first number we're going to use is the 9, the second number we're going to use is 1. And if I go about doing that, I'll get something that looks like this. So I will put 9 in to start with, so that will be 9 squared, take away 2 times 9 to the power of 3 over 2. And there we go. And then we are going to take away whatever it is when we substitute 1 in. So if I substitute 1 in, we'll get 1 squared, take away 2 times 1 to the power of 3 over 2. And there we go. That is going to work out our answer. Now you'll notice that we didn't need to put the plus c in, because we are going to take these away from each other when doing a definite integral. You'll notice that if I had have put a plus c in the first bracket, I would be taking away a plus c in the second bracket, and therefore they would cancel out anyway. So putting that in is kind of pointless. So if we work this out and type that into a calculator, you will see that I get the answer 28. So our final answer for this is 28. Now on a later question you are going to see what we use this for, but this was just a practice at going over how to go about doing this. So as you can see, we integrate it, we put it into the squared bracket showing the 9 and the 1, and then we substitute 9 in, substitute 1 in, and take them away from each other. And again, if we had different numbers there, we would sub those numbers in, but again we would just take them away from each other, and we're looking to see what our answer is. Okay, so in this question we are going to see what we use definite integrals for, and this question here says find the area of the finite region between the curve with equation y equals x brackets x minus 4 squared and the x-axis. So this is going to show you what we use definite integration for. Now if we were to draw this curve and think what it looks like, it would be a cubic graph, and it is a positive cubic graph as well. Now you can see here we get our solutions of x equals 0, and we've also got an x equals 4 solution there, and that's a repeated solution, so it's going to bounce on the axes. So our graph would come up through 0, bounce on 4, and then go back up. So if we label that on, we've got 0 here and 4 just here, and hopefully now you can see that finite region between the curve and the x-axis. So if I highlight that, we are looking at this region here. So when we are using definite integrals, we use it to find the region bounded between two of these points. So in order to do this, we're going to have a look at the equation of the curve. We are going to do our definite integrals between 0 and 4, and that will tell us the area that is bounded between those points. Again, it does tell us the area as it is bounded towards the x-axis, so we would have to do something different if it was bounded between the curve and another line, but again we will look at that as well. So in order to integrate this, we'd probably want to expand that equation. So if we expand that equation, if we do the double bracket first, we would get y is equal to x lots of, if we expand that double bracket, we get x squared minus 8x plus 16. Now we'll multiply it by the x as well, so we're going to get y is equal to x cubed minus 8x squared plus 16x. Now we can go about actually integrating this, and if we integrate that, and again we're going to do it between these 2 points, so we'll write that we're going to do it between 4 and 0. So when we integrate that, we get x, let's have a look. In fact, let's just write down on what we're going to integrate. We're going to integrate x cubed minus 8x squared plus 16x. And when we integrate it, then we can just go ahead and write it in our squared bracket. So increasing the power then, we get x to the power of 4 over 4, take away 8x to the power of 3, all over 3. Let's just make sure I write that 3 a little bit better. And then that is going to be plus 16x over 2. And of course you could write that as 8x squared. Sorry, 16x squared over 2. You could write that as 8x squared. Now that's what we're going to be using for our limits here, so we'll put that into our squared bracket, and we're going to use 4 first and 0 second. It's quite a nice one when it does have 0, it does make this second step quite nice. So when we put the numbers in, let's have a look at what we get. Putting 4 in to start with, and again let's just write it in because we're just going to type this in on our calculator. So we have 4 to the power of 4 divided by 4, take away 8 times 4 cubed, all over 3, and then plus 16 times 4 squared, all over 2. And we're going to take away the second one, which is substituting in 0. Now if you have a look, if you substitute 0 into the first piece, you get 0 over 4, so that's 0. The second piece, you get 0 over 3, and the third piece, you get 0 over 2. So all of that just comes out as 0. Again, you can substitute 0 in if you want, but just looking at it, you can see they all come out as 0. So if you type all of that into your calculator, we get the answer, and it comes out as 64 over 3. And there we go, that is our area. So the area that we are looking at there is 64 over 3. You could convert that into a mixed number if you want, so you could write that as 21 and a third, but either of those answers are fine, and we could leave our answer in either form. So there we go, that is our final answer. That's what we use this definite integration for. We find the 2 points that are bounded by the curve and the axes, and using this we can work out the area underneath. Okay, so when looking at specific areas, sometimes we'll be looking at areas that are also under the x-axis, and we just have to take something into account when we do this. So if we think about what this curve would look like for this particular question, we will have something going under the x-axis. So you will see when I expand this bracket and or if I draw a sketch of it, what it would look like. So if we draw a little sketch to the side and think about our solutions, we've got x equals 0, and again we're just looking at this curve here. We have got x is equal to 1, and we have x is equal to negative 3. So again, the question just says to find the finite region between the curve and the x-axis, but you will see when I draw this, we have a point at negative 3, we have a point at 1, and we have a point at 0. And when I draw this curve in, again just drawing a sketch of it, so it's not to scale, but it is going to go up through negative 3, down through 0, and then up through 1. And you can see here that we have a finite region above the x-axis here, and we have another one below the x-axis here. And when we are working this out, something's going to change in our answer. We'll have a look at that when we get to it, but for now we just need to follow very similar steps. We're going to integrate our equation, and then we are going to use our definite integration between these 2 points, but we're going to do them separately. So we're first going to have a look at between negative 3 and 0, and then we're going to have a look between 0 and 1. So first of all, let's expand our equation. If I expand the first 2 brackets there, or the x by the x minus 1, we get y is equal to x squared minus 1 that we're going to multiply by x plus 3. So if we stick that first part into a bracket and we'll expand that out, we get y is equal to x squared times x is x cubed. Then we get a plus 3x squared and a minus x squared, so plus 2x squared, and then we have minus 3. So that right there is what we're going to integrate. So if we integrate that, let's have a look. We get, and let's just figure this out, so increase the power, x over 4, x to the power of 4 divided by 4, and then we get 2x cubed divided by 3, and then minus 3. I've just realised we've forgotten an x at the end there, so minus 3. Okay, so now we're going to integrate the equation of our curve. So first of all, let's expand those first 2 brackets. So that would give us y is equal to x squared minus x. And we're going to multiply that by the third bracket there, or the third piece. Obviously the first piece wasn't a bracket, but we're going to multiply that by x plus 3. If we expand that out, we're going to get y is equal to x squared times x is x cubed. Then we get plus 3x squared minus 2x squared, so plus 2x squared. And the negative x times 3 is minus 3x. So that is our equation expanded. Now we're going to integrate it. So if we integrate that, we get x to the power of 4 over 4. Then we get plus 2x cubed over 3.
And then for the final piece there, we get minus 3x squared over 2. Again, we're not going to put our plus c in there because we are going to be using our limits, and therefore that plus c is going to disappear anyway. So we'll put this in brackets, we'll put our dx at the end, as we know that is what we are using. So when we put our limits in, we're going to do this in two parts. To start with, we will have a look at the first part here, and then we will have a look at the second part. So if we start by having a look at the first part, we are going to put our limits in now, so that is between 0 and -3. And if we substitute our numbers, and we're doing this with respect to the y equation, so we'll put y dx here, and then we'll substitute our numbers in. So when we go about doing this, just so that we don't have to rewrite that full equation, then we can put 0 in to start with, which if you have a look just comes out as 0, and then we're going to take away, and we need to now substitute -3 in, so we have -3 to the power of 4 all over 4 plus, in our second fraction, 2 times -3 cubed all over 3, and then take away 3 times -3 squared all over 2. And there we go. If we work that out and type that into our calculator, for that we get the answer, and let's just put this up here. So for our first one, we get the answer 45 over 4. So that area comes out as 45 over 4, which you can leave like that for the moment, and that is our first area. Moving on to the second one, and this time we are going to integrate between the points 1 and 0. Let's just change that naught there, so that this time is between 1 and 0. Again, so we don't have to write the full equation, we'll put y dx, and this time, when we substitute 1 in, let's have a think, we get 1 to the power of 4 over 4, so that's just a quarter, plus 2 times 1 cubed is just 2, so it's plus 2 over 3, take away 3 times 1 squared, so 3 over 2, there we go, and we are going to subtract, when we sub-0 into all of it, we already know that comes out as 0, so that comes out as 0, and that comes out as -7 over 12. Now this is the important part, and this is where something changes when it's under the axes. An area cannot be negative, but when it comes out in this form in integration, it knows that it's under the axes, and it gives us the area as a -7 over 12. So all we have to do is we change that area to a positive number, so we write that it's +7 over 12. And that is literally it for this extra element when it is under the axes or under the x-axis. So when you get a negative area, you know it's under the x-axis, and as an area, we just write it as the positive version. So to finish this question off, now we know that the area is positive, we just add them together. So 45 over 4 plus the +7 over 12, and that comes out as, and you can do this on the calculator, it comes out as 71 over 6. So there we go, that is our final answer, 71 over 6. Again, you could turn it into a mixed number if you want, but it's not required and it's not necessary, so we can leave that as 71 over 6. Okay, so looking at this question, it says the curve C has equation y equals x squared plus 2. It says the line y equals 6 intersects curve C at the points A and B. Find the area of the finite region bounded by the curve C and the line AB. So if we draw a sketch of this to see what it looks like, the x squared plus 2 is just an x squared graph that's been translated up by 2. So it would look something like that. Now if it's been translated up by 2, it does cross through the x-axis at point 2 just here, and that will also help us to draw the line y equals 6, as we know it has to be above that. So if we draw that line in as well, it goes across here, through the point 6, and it crosses over here and here. So we can call that point A, and we can call this one point B. So we are looking at the area that is bounded by the curve and the line AB. So that is going to be this area just here.
So again, this is above the x-axis, but it is bounded by that line y equals 6. So this is an area between a curve and a line. Now when we go about doing this, we just need to think logically about how we would work that out. If we can find the coordinates of A and B, we can go down and we can imagine where the x coordinate would be just here. If we do the same with B, we know the x coordinate is going to be just there. And that is going to form a rectangle. Now if we were to work out the area of that rectangle and then subtract the area underneath the curve just here and over here, then that would just leave us with the shaded region that is bounded by the curve and the line. So to start with, we can take many multiple steps here, but I'm going to start with solving to find the coordinates where they cross over, and we can do that by setting these equations equal to each other. So if we take the equation of the curve, x squared plus 2, set it equal to the equation of the line, which is 6, and now we can solve that. So if we solve this, we get x squared is equal to 4, and therefore if we square root both sides, x has to be equal to plus or minus 2. So if x is equal to plus or minus 2, we can see that the x coordinate will be 2 over here. It will be negative 2 just over there. So now we can work out one of two things. We can either work out the area under the curve, or we can work out the area of the rectangle. Probably easier for us to just get the area of the rectangle so we don't forget. So for the rectangle, there we go. That has a base length across here of negative 2 to 2. So that is a base length of 4. And it has a height going up here, going from the x-axis up to the y equals 6 line, so it has a height of 6. So the area of our rectangle is going to be 4 along the bottom multiplied by 6, which is equal to 24. So I'm going to underline that so we don't forget about that one. Now we want to find the area under the curve. This is quite nice as it's just between negative 2 and 2, so we're not going to have to do this twice like on some of the other questions. So if we write this out, we are going to integrate between 2 and negative 2, and the piece we're going to integrate is x squared plus 2. So we just write x squared plus 2 dx. Now we can actually go about integrating that. So if we go about writing this out, we could put it into our squared brackets, and we would say, and let's just integrate that now, so that would become x cubed over 3 plus, and then increasing the power of 2 just makes it 2x, and again we'll just write the limits there, which is 2 and negative 2. So now we just need to go about actually substituting those numbers in. So if we substitute 2 in, let's see what we get. So for the first one here, if we substitute 2, we get 2 cubed divided by 3 plus 2 times 2. For the next one, which we're going to take away, we've got something very similar looking, and that is negative 2 cubed divided by 3. And then that is going to be plus 2 times minus 2. There we go. And that is what we need to work out. So if we type that into our calculator, let's see what we get. We get the answer 40 divided by 3, or 40 over 3. Now that again could be written as a mixed number, but of course you don't need to write it, we can just leave it as 40 over 3. So we have the pieces that we need. We know that the area of the rectangle was 24, and the area under the curve there, bounded by the x-axis, is 40 over 3. So we already discussed at the start that to get this area here that is between them, we just need to subtract them away from each other. So we'll take the area of the curve, the area of the rectangle, which is 24, and subtract the area under the curve, which was 40 over 3. And if we just typing that into our calculator, we get the answer that comes out as 32 over 3. Or of course, you could write that as a mixed number. You could write it as 10 and 2/3, but 32 over 3 is fine. So 32 over 3 would be the final answer for the area that's bounded by the line y equals 6 and the curve. So something like this, 2 to the power of x equals 8. This isn't built to be particularly difficult. Hopefully you can spot here that 2 to the power of 3 is equal to 8. Or in other words, 2 times 2 times 2.
And we could write that, we could write 2 to the power of 3 is equal to 8. Now when it comes to logarithms, there is another way of writing this. Now just like when we're looking at these powers here, we know that this number here, this 2, is called the base number. And that's going to apply when we look at a logarithm. Now what we say for a logarithm, and this is going to mean exactly the same thing, it's just a different way of writing it. We're going to say that log with a base of 2, just like here we've got our base number of 2. What log with a base of 2 gives us the answer 8? So log base 2 of 8. And we might say that equals x or something, or we're trying to find out what that answer is. So what power of 2 gives us the answer 8? And we know that the answer is 3. Okay, we've just worked that out. And that would be the answer there. If we wrote log base 2 of 8, our answer would be 3. So all that this means here is essentially what power of 2? What power of 2 is equal to 8? There we go. And that is really the fundamentals here behind logarithms. And as long as we can understand that concept, we can look at it in all different types of ways. But all we're going to be looking at here is basically what powers of certain numbers equal particular answers, and sort of mixing those and sort of rearranging that in certain ways. Now we could write this as a sort of, not as a formula, but we could write this obviously with letters rather than having the numbers here, and looking at how obviously we rearrange this. So we could say that log base of, and let's just call it a, with this letter b here, is equal to x. And what that means in terms of a power. And that means that, and again the base of a is our main number here, or in this term obviously writing a letter at the moment, but a to the power of x equals b. And that there is obviously something pretty key to write down, because that's how we're going to be sort of writing these and writing them in sort of different ways as we move through this video. But obviously just thinking about this logically, log base 2 just means the number 2 to the power of something gives us this answer here. Okay, so what power of 2 gives us the answer 8? And that power there is 3. So let's think about a different example before we move on. I could say something like this, obviously rather than writing it as a power, we could say log, and let's go for base 3 this time. So what power of 3 gives us the answer 9? So we'll go log base 3 of 9 equals x. And I might ask you here to find the value of x. So if we've got this little problem in front of us, we would say, okay, well 3 to the power of something, and we've obviously got the letter x there, is equal to 9. So what power of 3 gives us the answer 9? And hopefully that's nice and easy for you to spot. We know that it's 3 squared that equals 9. So we would say x equals 2. Or we could say, you know, log base 3 of 9 equals 2. But that's really the fundamentals here behind what logs mean and how we're going to use them. Okay, so something a little trickier here. We've got find the value of x such that log base 4 of a 1 over 64 is equal to x. Or in other words, what power of 4 gives us 1 over 64? Well, let's write this out. So we have the base of 4. So 4 is our base number. 4 to the power of something, which is our x this time, is equal to 1 over 64. So we know from the last one, again, obviously depending on how comfortable you are with your negative indices, we know that in order for it to be a 1 over as the answer, it's going to have to be a negative power. So we already know part of the power here. We know it's going to be 4 to the power of minus something. And we need to get to 1 over 64. So what power gets us from 4 to 64? Well, we can work that out just down below. Let's have a look. 4 times 4 is 16. And if we times that by 4 again, isn't the nicest one to do in your head, but 16 times 2 is 32. Double that again, we'll times it by 4, and that gets us to 64. So it's 4 times 4 times 4, or in other words, 4 cubed. So it's going to be 4 to the power of minus 3. So there we go. We know 4 to the power of minus 3 gives us 1 over 64. So we could say log base 4 of 1 over 64 is equal to negative 3, the power there. Or in other words, x equals negative 3. And there we go, there's our final answer. So that's all that this means when we're looking at logs, okay? So it's just about looking at the way that the log is written and reading it just like we recognised before. Log base, and then we have our base number. Then it gives us our answer, 1 over 64, is equal to what power, or in other words, what power of 4 gets us 1 over 64.
Okay, so as long as you read it like that and sort of understand the way that that writing translates to that wording, you should be absolutely fine working through some of these problems. Okay, so this question here will show you how obviously we can use logarithms to actually solve some of these indices problems. So we've got here, find, giving your answer, three significant figures, the value of x for which 5 to the power of something equals 10. Now this is quite nice, and this will show you why logarithms are so useful, because we can actually just type these in straight into the calculator, but obviously it does mean that we have to know how to write this power as a logarithm. Now if we write it out, so we're going to have log, there we go, and then we need to put our base number in. So here we've got our base number of 5, so log base 5, and our answer is 10. So what power of 5 gives us 10? Now you can type this straight into your calculator and we'll be able to get our answer straight away. So if you have a look on your calculator, and everyone has different calculators, so you can need to find your button, but there is going to be a button on your calculator. I'm using a Casio ClassWiz, which again I really recommend, and I'll link that in the description, but just underneath the on button or somewhere on your calculator there's a little button that looks like this, and it normally looks like log, and it has like a little coloured in square and then a little open square. And if you can find that button, you'll be able to do these no problem. So find that button, press that, but get 5 in your little base square and then 10 in your larger open square there, and type that in, and let's have a look. We get the answer, and I get on my calculator 1.4306765558, which again, if we give that to three significant figures, chop it after the 3, we get 1.43 as our answer. And there we go, it's as easy as that. And you can even test that out if you want. You can press 5 to the power of and then put the answer in, and you will get the answer 10, obviously if you don't put the rounded answer in, but you put the original one in. So this question says express log 2 or log base 2 of 4 plus log base 2 of 16 as a single logarithm to base 2. And a lot of these links here come to our basic understanding of our laws of indices. And if I talk about this sort of logically, and it will require you to obviously understand what we went over in part 1, but if we look at log base 2 of 4, and we actually calculate that, and that means what power of 2 gives us the answer 4. And if we write that down, let's go for this here, so for this part here, what power of 2 gives us the answer 4? And hopefully we're happy to know that is a power of 2. So let's just give that the answer, x equals 2, if we obviously incorporate that x into our calculation there. For the second part, we've got log base 2 of 16, and again that means what power of 2 gives us 16. Okay, and that power of 2 that gives us 16 is 4, so x equals 4, or the answer's 4. So really what this question is asking us to do, it's asking us to add these two numbers together. So we have 2 plus 4, and let's keep it all in the same colour there, and we know that the answer for that is 6. 2 plus 4 is 6, but obviously it wants it as a single logarithm to base 2. Now in other words, and there is a little quick trick to this, we don't have to do this for every question, you'll see the little trick here, but in other words it wants us to write which log with a base 2 has an answer that's going to come out as 6. So log base 2 of what number is equal to 6? And we can reverse that, okay? So we can think about this as we did in part 1. We can say, okay, well 2 to the power of 6 is going to equal that number that's going to go with our log there. And all we need to do is actually work that out. So 2 times 2 is 4, times 2 is 8, times 2 again is 16, times 2 again is 32, and then times 2 again is 64. So x there equals 64. Or in other words, if we're going to write this log as a single logarithm to base 2, we would write log base 2 of 64. Okay, now let's think about how this links to what we've learnt already looking at laws of indices. Okay, so if we look at these two numbers that were in our logs, 4 and 16, well there's a link between 4 and 16 and the one that we have now, 64. And that link is essentially, we just have to multiply these numbers together, 4 times 16. And that's going to incorporate our first rule here that we're going to look at with logarithms. Let's just get rid of this little bit on the right here, and let's have a look at what we're talking about. So in other words, if we have log, and let's just put base x, and then a number, so let's have it as a for this one, and we add to that another log, and what is key here is it does have to have the same base, and we'll talk about how that links through to our indices as well, with another number, let's call that b. Our resultant log,
Okay, the log that we're going to get from that is going to be log with the same base x, but it'll be a multiplied by b, or ab. So all we actually have to do when we're adding these logs together, so long as they have the same base, and that's absolutely key, we just multiply together those numbers at the end. And if we think about how that links back to some of the algebra that we've done at GCSE level, if we have something like a squared, and we multiply that by a to the power of 4, multiplication being involved there, we add the powers, and we got a to the power of 2 plus 4, which would give us a to the power of 6. And hopefully you can see, look, those little numbers, 2 and 4, link back to our 2 and 4 here, and our 6 and our 6, and it kind of all links together back from what we've learnt on obviously our laws of indices there. Okay, so that's essentially all we're going to do when we're adding logs together. One thing obviously that's very important here, this is when we have the same base number. Just like when we learnt this with our laws of indices, these powers here with our a's can only add together as long as we have the same base letter there, and in this case that was the base letter a. So a to the power of 2 times a to the power of 4, we can add those powers together, but not if we change that base number. And that rule's going to apply with these logs here, and in both of these we had a log base of 2, so we're able to just multiply those numbers to get our final log. Hopefully nice and simple, and obviously you can obviously think about it logically like I did in this first scenario here and working it out like that, but it's much quicker if we have the same base numbers just to multiply those numbers together at the end. So there we go, there is our first rule. This is your key piece of information to make sure you have written down, and that is what we're going to do for adding logs. Now we're going to have a look at taking away, so let's look at that one now. Okay, so you're going to see a lot of links between obviously what we've just looked at and this one here, except this time we are taking logs away. Now again, something to note, we have the same base number. In this case, they are log base 3s, and there's going to be a lot of links back to that process that we've done with our powers of indices again. Now, if you think about, again, just thinking about our laws of indices, if we have something like, and let's go with a to the power of 4, and we divide that by a to the power of 1, what do you actually do with the powers? Well, not forgetting obviously that we have that power of 1 in there, even though it's not written, but when we've done this before, we would subtract those powers, and that would come out as a to the power of 3. Now, if this is something that slipped your mind, these laws of indices, I'll make sure I'll link the video for that in the description so you can check that one out and make sure that you're sort of clued up on your laws of indices there, but that sort of idea there is going to link through. The powers in this case were subtracted, and that was when we were doing a division. This time here in our logs, we are subtracting those logs, and you might be able to guess that we're going to end up dividing these numbers, 81 divided by 3, the opposite of what we just did. But let's have a look at how that works with our logical approach. So log base 3 of 81, that means what power of 3 gives us the answer 81, and that's going to be 3 to the power of 4. So in this case, x equals 4, or the answer to that log is 4. For our second log there, we've got, and this is always an interesting little log as well, we've got 3 to the power of something equals 3. So log base 3 of 3 is 1, and that little relationship there is going to apply to any log. If we have log base 4 of 4, that's going to be 1, log base 5 of 5. Any log base that has the same number after it, our power there or our answer there is always going to be 1. So we've got our two numbers, we've got 4 and 1, and it's as simple as 4 take away 1, and that would give us our final answer, which for this one comes out as 3. And obviously we're not trying to work out that answer there, we're trying to know as a single logarithm to base 3. And if we think about that, we are trying to work out, therefore, that which log with a base of 3, okay, what's the answer if the power is 3? And that means what base of 3, okay, with a power of 3 equals x, there we go, or in other words 3 to the power of 3 equals that x value there. So we know that 3 cubed is equal to 27, and there we go, that's the number that needs to go with our log. So if we write that out as a single log to the base of 3, we have log base 3 of 27 is going to be our final answer. And let's just have a look at how that all links through. So again, thinking about those original numbers, we had 81 and 3. And 81 divided by 3 is 27. So it follows that kind of idea that we were talking about just here when we were dividing with powers, looking at our laws of indices, and we ended up subtracting them. It's kind of like the opposite of that. When we're subtracting our logs, we can divide those numbers at the end of the log. So log base 3 of 27. So hopefully that's okay. It's just the opposite of when we were adding.
Okay, but I just wanted to show you there the logical way of why it works, and obviously the link between that and our laws of indices that we've looked at previously. So again, two little notes. One is the logs have to be the same base. When we're adding, we can times the numbers at the end. When we're subtracting, we can divide the numbers at the end. But just making sure that we write this down and thinking about this for any kind of logs here, as long as we have log, and I'm going to use the same letters here, base x of a, and we take away log with the same base, so base x of b, our resultant log there, we get log base x of a over b. I'm going to put that a over b there in a bracket. So there we go, that is adding and subtracting logs. We've got one more thing to have a look at before we look at our final questions here, so let's have a look at that one now. So for our final little rule on logarithms, we're going to look at something like this, and it says express 2 log base 2 of 8 as a single logarithm to base 2. And this links nicely into one of our other little rules of indices that we've looked at in the past. And if we think about something like this, where we've had a, and let's just go for a cubed to the power of 2, and we have something like that, what is it we do with the powers? Well, hopefully we remember we multiply the powers. So something like that, we would do a to the power of 3 times 2. Which would end up resulting in a to the power of 6. Now this is obviously when we multiply the powers, and it's when we have sort of a power to another power in the bracket, just like that. And that's going to link through quite nicely to this. Now this is at the moment is not a single logarithm, because what we have here is 2 lots of log base 2 of 8. Okay, we've got this little 2 at the start. Or in other words, we're multiplying that by 2. And what we can do is we can manipulate this logarithm, we can write it in a slightly different way, and I'll show you why it works. So at the moment, we've obviously got it written as 2 log base 2 of 8. Now all we do is we can take this number at the start, this number 2 here, and we can put it as a power at the end of the logarithm. Or in other words, I'm just going to write it here, we can say that it's also equal to log base 2 of 8 squared. I mean, that's obviously we can write that as an actual number, we can write that out, and we'll write that out in a second, but we're going to have a look at why this works at the moment. Obviously 8 squared is 64, but we'll have a look at that just now. Now if we look at this first logarithm, so it's 2 log base 2 of 8. Now at the moment, forgetting about the 2 for the moment, because we'll look at 2 lots of it in a second, but just this log base 2 of 8, that means what power of 2 gives us the answer 8? And hopefully we know that that is actually 3, isn't it? Okay, so we can say x equals 3. 2 cubed equals 3. But we also have 2 lots of that. Okay, so not forgetting about the fact we have the 2 there, we've got 2 lots of x equals 3, or 2 lots of 3. And if we write that out, 2 times 3 equals 6. So our answer just there would be 6. Now let's have a look at our other one over here. We have log base 2 of 8 squared. Or in other words, what power of 2 is going to give us the answer to 8 squared, which we already know or we've established is 64. Not the nicest one there, but the power of 2 that gives us 64, and you're happy to check this, the answer is 6. We get x equals 6. So both of these give us the answer 6, and that's just going to show you obviously that they mean the same thing essentially. But again, this is just another way that we're able to manipulate the way that we write logs. So this number at the front can be taken as a power at the end. Okay, so we've moved that to just to being a power here with the 8. And obviously we could do that vice versa as well. If I had originally log base 2 of 8 squared, I could bring that 2 to the front. Okay, I could just put that at the front like we've done just there. Okay, so again, this is just another way that we're able to write logs, and this is important, as you're going to see on the final question that I'm going to show you, because the only time we can add and subtract logs is when they are written as a single logarithm. So having it written this first way that we have in the question is not very good to us if we're looking to do some calculations with it. We always want to bring that number back up to the power. So that's something very important to make sure that you've got there as well. Okay, but it's just another way of writing the logs. And if we were to kind of write it out, we could say something like this: a log base x of b can also be written as log base x of b to the power of a, and again vice versa. So there's another little rule that you're going to want to have written down, but hopefully just with a little bit of practice they'll sort of ingrain into your memory anyway. But this is our final little piece that I needed to show you. So we're going to have a look at a final question whereby we first have to change the logs and then apply some of the other rules that we've looked at, but hopefully this here shows you obviously how to go about that. Now, not forgetting here we need to get our final answer down, so our final answer instead would have been log base 2, not of 8 squared, but of 64, and there's our final answer. Okay, so let's highlight that off. And now we're going to have a look at putting this all together. Okay, so on to our next question. It says solve the equation 2 log base 5 of x, take away log base 5 of 3x equals 2. So slightly different, we don't have a log on the right hand side of the equation here, but we do have some other little bits to deal with. And again, just taking note, these logs do have the same base, so we can apply all of these little rules. But this log on the left is not a single logarithm, we have 2 log base 5 of x. So in order to do our subtraction rule here, we're going to have to use our little power rule, and we're going to have to move that 2 up to the x, or actually just our rearrangement of logs there, potentially bringing in our power rule later on. So in order to get that log on the left to become a single log, we can bring that 2 at the front up to the power with x. And again, thinking about that from some of our earlier videos, and do make sure you check those out first if any of these little bits with the logs are sort of going past you. So let's bring that 2 up. So that would become log base 5 of x squared rather than 2 log base 5 of x. Take away log base 5 of 3x, and that is equal to 2. Now they are both single logarithms with the same base. We can apply our subtraction rule like we did before. So we're going to divide those pieces. So we're going to have here log base 5 of x squared over the 3x. And again, you can put that in brackets if you want. Put that in a bracket, and that is equal to 2. Okay, so we're going to have to deal with this log now. As we only have the log on the one side, we can't just cancel it out from both sides. We're going to use our power rule here. I'm thinking about what this means, and it's a little bit more abstract than when we have just a numerical value here, but we have what power of 5 gives us the answer x squared over 3x. And it tells us here that that answer is 2. So in other words, 5 to the power of 2 is equal to this, x squared over 3x. What power of 5 gives us that? And it tells us the power is 2. So that's 5 squared. So in other words, if we write that out, in order to remove our log here, we can write that x squared over 3x is equal to 5 squared. And obviously we don't need to write 5 squared there, we can actually remove that and write the answer as 25. So let's just get rid of that. Obviously you leave that for your working, but let's just turn that into 25, as we know 5 squared is 25. Right, so from here we can actually form our equation now. Oh wow, we've actually already formed our equation, but we can get it into a singular line. So the first thing we need to do is we need to remove this 3x. At the moment it's being divided by 3x. So let's multiply that over to the other side. And once we do that, let's bring this up here, we get x squared is equal, not quite drawing the 2 in there, we go, is equal to 75x. And there we go. Now obviously we have a quadratic as we have an x squared in there, so we want to get everything on the same side so it equals 0. So let's minus 75x to the other side. So we get x squared minus 75x equals 0. There we go. And just like with any quadratic, we need to factorise it. This quadratic here has no number at the end, so in order to factorise that, we're going to want to put it into a single bracket. So let's take out a factor of x. So we get x brackets x minus 75, and that equals 0. There we go. So we get our 2 solutions here. We've got 2 possible solutions. We've got the x on the outside, which gives us x equals 0, and we've got the bracket there, which gives us x equals positive 75. Now we've got 2 solutions, and when we've got 2 solutions, we definitely need to check these out. Now when we're looking at a log, we can't have log base of 0. Okay, we can't have log base of 0, because that means what power of whatever the base is, in this case 5, what power of 5 gives you the answer 0. And there is no number that you can put to a power of 5 or a power of anything to get the answer 0, just like you can't get a negative number. You can get very small numbers, fractions, you can get very large numbers, but you can't get negatives and zeros. So 0, this one here, if we think about that in terms of substituting it back into either of our logs here, if we were to put it into this log on the right, we would have log base 5 of 3 lots of 0, which would be 0. And that's not possible. Okay, we can't have that. So 0 here is not going to be included.
We can have 75 though. If we were to put 75 in there, we'd get some very large numbers. Okay, we'd get 225 for the one on the right and 75 squared on the one on the left. So 75 would be fine. It would give us a positive whole number. So x equals 75 in this case is our final answer for that question. And there we go. Let's have a look at our next one.
Okay, so when having a look at exponential graphs, it's important that we're able to sketch them. So this question says on the same axes, sketch the graphs of y equals 2 to the power of x and y equals a half to the power of x. So if we draw a little sketch of some axes, we can think about what these would look like. Now for the first one, we will sketch y equals 2 to the power of x. Now this is an increasing function here, so it would be sloping upwards, and again with an exponential function, the graph approaches but never touches 0. So this would be our y equals 2 to the power of x, and now we'll have a look at y equals a half to the power of x. So for y equals a half to the power of x, that is a decreasing function. So it would be sloping downwards. Now it would look very similar to this, but it would just be sloping the other way. And as you can see, it is decreasing and again getting closer and closer to, it approaches but never touches 0. So this one here would be y equals 1/2 to the power of x. There we go, put that in a bracket, and to the power of x. Now, as with all exponential functions, there are a couple of things that you need to be aware of. So for these exponentials here, if we were to put in an x value of 0, which is what's on the y-axis there, we would get a y-coordinate just here of 1. Anything to the power of 0 is 1, so that's something to be aware of. Another thing that we should be aware of as well is that we have an asymptote. Now this here never actually touches the x-axis, so the x-axis is our asymptote. Now for this one here, the equation of the x-axis is y equals 0, so our asymptote of these graphs, and we'll just label that there, asymptote, there we go, is y is equal to 0. Of course that would change if we put a graph transformation in. Something like 2 to the power of x plus 5 would move the graph upwards by 5, which would move our y-intercept and would also change our asymptote. But there we go, that is looking at sketching exponential graphs. So when it comes to differentiating an exponential, there is just a few rules that we need to know. So this question here says to differentiate y equals 2e to the power of 3x with respect to x. Now if we are going to differentiate this, all we actually have to do is do it in a similar way to how we differentiate, but just one little thing changes. So when we do the differential, so dy over dx, of this exponential, we multiply the coefficient of e by the coefficient of the x. So that means we are just going to multiply the 2 by the 3 this time, which makes it 6. We still have e and the power stays the same. So that is just still going to be a power of 3x. So if at any point you have to differentiate an exponential, this is all that you need to do. Multiply the coefficient of e by the coefficient of the x in the power, and then keep the power the same. So differentiating an exponential is quite nice and simple. Okay, so when we are solving an equation with an exponential, and this question here says to solve the equation e to the power of 2x plus 3 is equal to 7, and we're going to give our answer in exact form. And this is when we start to use natural logarithms. So in order to remove the e at the start, we take the natural logarithm of both sides. Now the natural logarithm is just the inverse of our exponential there, so if we write this out, e to the power of 2x plus 3 is equal to 7. When we take our natural log of both sides, the e disappears, we get 2x plus 3, and that is going to be equal to the natural log of 7. So it's quite nice and easy to get rid of the exponential. All you need to do is take the natural log of both sides, and essentially it just drops the power down. Now we can just solve it like a normal equation. So we would take away 3 from both sides, which would leave us with 2x is equal to the natural log of 7, take away 3, and then we would divide both sides by 2. So x is equal to the natural log of 7 minus 3, all divided by 2. Of course, that could be written in a different way. We could put that divided by 2 in front of both. So we could say a half of log 7 minus a half of 3, which is just could just be written as 3 over 2. So either one of those would be fine as our answer. I tend to write my answer like this most of the time, so I do prefer that one on the right, but both of those answers there are fine, and we have given our answer in exact form as we have left the natural log within our answer. Okay, so another type of equation where we're going to be using natural logs. So for this particular one here, you can see what we actually have is an exponential quadratic here, and we're just going to have a look at factorising it in order to find our solutions. So it says solve that equation e to the power of 2x minus e to the power of x plus 12 is equal to 0, and again giving your answers in exact form. So for this question here, it does give us a bit of a hint that we're going to be using natural logs, and to start with we just need to factorise it. So at the start of both of our brackets we will have e to the power of x, as when you expand that, e to the power of x multiplied by e to the power of x would equal e to the power of 2x, and that is all equal to 0. Of course, if it wasn't equal to 0 you may just have to rearrange these first, but once we've got it into that form we can now factorise. So looking at the 12 there, we could have some factors. We're trying to make 8 in the middle, so 2 and 6 is going to work. So in our bracket we'll have minus 2 and minus 6, and that would equate to negative 8e to the power of x in the centre there. So we have two solutions. For the first one, we have e to the power of x has to be equal to positive 2, and here we have e to the power of x has to be equal to positive 6. Now before we just go ahead and solve that, just as a side note, when we have this here, e to the power of x has to be positive. Okay, e to the power of x must be positive, and that means if we do get an answer which says e to the power of x is equal to negative 3, for example, we would have to discard that answer and we would just use the 1. But this one here, we have both being positive, e to the power of x equals 2 and e to the power of x equals 6. So these are both going to be solutions, and it does give you a little bit of a hint here as it says the word answers. So for this one, we will now just take the natural log of both sides. So for the first one on the left there, x would equal the natural log of 2, and x would equal the natural log of 6, and again they are both in exact form, so we would leave our answers like that. So x equals the natural log of 2 and the natural log of 6. Okay, so when we are having a look at modelling with exponentials, the questions do get quite tricky. So it says here the value of a car, and that is in V pounds, can be modelled by the equation V is equal to 15,700 e to the power of minus 0.25t plus 2,300, where t is a real number and t is greater than or equal to 0, where the age of the car is given to us in t years. Always worth highlighting that the age of the car is t years, just so we don't forget about that. So it says here, using the model, find the initial value of the car. Now the initial value of the car would be found when t is equal to 0. So all we need to do to find the initial value of the car is substitute t equals 0 into our equation and see what we get. Now if we do substitute t equals 0, we would have 15,700 e to the power of, and negative 0.25t times 0 is just going to equal 0. Now anything to the power of 0 is 1, so that is just going to be 15,700. We then have to add 2,300 to that, and that means we just have 15,700 plus the 2,300, which gives us a final answer of, and it's in pounds, so we would say £18,000. And that would be the initial value of the car. So we'll just underline that as that's our first answer. On to part B, it says given the model predicts that the value of the car is decreasing at a rate of £500 per year at the instant where the time is equal to capital T, show that 3,000, and let's just highlight this, 3,925 e to the power of negative 0.25 capital T is equal to 500. So in order to look at this, we would want to differentiate that, as we are looking at the rate of change or the gradient there when it is going down by 500. Now also just taking note here, if it is going down by £500 per year, that would be a negative 500 as our gradient. So in order to find this, we're just going to want to differentiate it to start with. So we're going to differentiate v, and we're going to do that with respect to t. So if we differentiate dv by dt, and we are going to be doing this at the instant where t is equal to capital T. So we're just going to replace the little t with big T in our differential. So if we go about doing that here, let's have a look at what we get. So we're going to multiply 15,700 by negative 0.25. And if we type that into our calculator, we get negative 3,925 e to the power of, and don't forget when you're differentiating an exponential, the power's not going to change, so it will be to the power of negative 0.25, and it says that little t is equal to big T, so big T. Now we have got that, all we need to do is think about setting this equal to the gradient that we've been told, and that is that it's going down by 500. So if we set that equal to 500, we would have negative 3,925 e to the power of negative 0.25t, and that is equal to negative 500. Now we've got one step in order to make it look like how we've been asked to make it look like, and that is to divide both sides by negative 1. Well, that would remove the negative from both sides, so our final answer would be positive 3,925e to the power of negative 0.25t, and that is going to be equal to positive 500. That is exactly what the question has asked us to show, so we have finished off our answer, and we have shown what the question was asking for. Okay, so on to part 2. It says here, hence find the age of the car at this instant, giving your answer in years and months to the nearest month. So for this particular part of the question, we have our equation to solve. We've just got that 3,925e to the negative 0.25t is equal to 500. So we want to know the value of t at this instant. So the first thing that we can do, and if we carry on from our part 1, and we'll just label this as part 1, part I, and then we'll carry on here with part 2. So the first thing that we're going to do is divide by the 3,925. And if we go about doing that, then we will get, and let's just have a look, we will have, if we type it into our calculator, e to the power of negative 0.25t, and in fact we don't really need to type it in because we can just write it as 500 over 3,925. Let's actually put the correct number there, 3,925. So for the next step, we want to remove the exponential. So if we take the natural log of both sides, we will have that negative 0.25t is equal to the natural log of, and we'll put this in brackets, 500 over 3,925. We now have one more step to get our value of t, and that is to divide by negative 0.25. And if we do that, we'll write that over here, divide by negative 0.25, and we get a value of t that is equal to, and what would it be? Let's type it into our calculator. So the natural log of 500 over 3,925, and then divide that by negative 0.25, and we get the answer 8.242. A few more decimals here, so we'll leave it at 8.242. And if we look at that there, that is in years. And remember it said that in the question, and we highlighted that at the start. So that is 8 1/4, or almost 8 1/4 years. And it does say give it to the nearest month. So a quarter of a year would be equal to 3 months. So our answer for this here would be 8 years. There we go, 3 months. And that would be our final answer for part 2 of part B. So 8 years, 3 months, and we'll just highlight that, and that part is finished. Now for part C, it says the model predicts that the value of the car approaches but does not fall below A. State the value of A. Now in order to do this, we need to think about what the exponential graph actually looks like. So if we do this, and we can just about fit it in at the top here, if I get rid of t equals 0, if we draw a small sketch of an exponential graph up here, and we think about what it would look like, we know it is decreasing in value, so it would come down something like this. Now we would have an asymptote just up here, and if we draw this in and think about the reason that I have drawn it up at the top there, the reason I have drawn it up at the top is because our exponential has this plus 2,300 just at the end. Now that means it has been translated upwards, and this value here would be 2,300. So, as it has moved up from 2,300, that means it is never going to approach, well, it's going to approach, but it is never going to fall below 2,300. So the value of A to finish this question would be £2,300, and we'll write this down the bottom, we'll highlight that as our final answer, and there we go, and that is looking at modelling with exponentials. Okay, well done if you have made it this far. It means that you've managed to sit through 7 hours of this video and 7 hours of me talking. So I do certainly congratulate you on that, and I do hope this was useful and helpful. If it was, please do like the video, please leave me a comment, don't forget to subscribe to the channel, but otherwise I will have to see you for the next one.